can take a picture of it too.
Look, Mommy, we took a picture of the moon.
That's one small step for man, one giant leap for mankind.
Look, Dad, there's the moon.
Let's take a closer look.
Awesome!
We can take a picture of it too.
Look, Mommy, we took a picture of the moon.
To go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Ladies and gentlemen, please welcome Mr. Joe Rayo.
Morning, everybody. Nice to see you all here again at NEAF. Is it NEAF or NEAF? I just say the forum. If you're into astronomy and you say the forum, you know immediately what it's all about. In fact, it is difficult for me, I don't know for you, it's difficult for me to realize that this whole thing started 25 years ago, inclusive now, this is the 26th NEAF. But in 1992, this whole thing began, and I must tell you, how many people here were at the very first one? Anybody? A few people? I was here, and I learned about it. I'm a member of a couple of astronomy groups based on Long Island, the Amateur Observer Society, or AOS, and the Astronomical Society of Long Island, ASLE, and it was just through the grapevine. They said, hey, the Rockland Astronomy Club is going to do, they're calling it the Northeast Astronomy Forum, and it's going to be at Rockland Community College. We never had anything like that before, and it was only a one-day event. It lasted from about 9 o'clock to 5 o'clock in the afternoon, and we had a few speakers. And, you know, we came, those of us who attended the first one thought so highly of it. They said, hey, this really went on very well. Look, we'll do it again next year. And it was just like a rolling snowball. In fact, in 1999, the forum was not even here. It was at the hotel. And back then, the hotel, I believe, was a Holiday Inn. But there were so many people who were coming, we literally overflowed the ballroom there at the hotel. And so we came back here to Rockland Community College. It's been our home ever since. So and you think about it, 1992. I mean, to me, this started like just a few years ago. I can't believe it's been 25 years. I thought just to refresh your memories as to what it was like when this whole thing started in 1992, I did a little bit of research. Astronomy, for example, has changed certainly. Certainly a lot of astronomy books are already outdated from 1992. For example, the number of planets in 1992 was 9. Now, of course, the number of planets in 2017 is 8, and people are still upset about that. The number of moons in 1992, or known satellites, 61, and I think Jupiter only had 14 moons at the time, 14 or 15 moons. I go back to the days when Jupiter only had 12 and Saturn had 10. Now we have 61 moons in 1992. In 2017, this year, 181 moons. Now, 173 belong to, quote, classic planets, the 8 planets that are recognized as planets. 8 of those moons belong to dwarf worlds. And we didn't even have dwarf planets back in 1992. Now we have a whole new category here. Number of dwarf planets in 1992, 0. Number of dwarf planets in 2017, we have 5. We have Pluto, we have Haumea, Ceres, which back in the day was an asteroid when I was growing up. Now it's a dwarf planet, Eris, and Makemake. The number of exoplanets. Back then, in 1992, the very first exoplanet was confirmed, and believe it or not, it was going around a pulsar. Now we have, as of April 1st, as of last weekend, 3,607 exoplanets. And of course, about a month ago, we found one star that had 7 of those exoplanets going around it, 3 or 4 of which may very well be in the, quote, Goldilocks or habitable zone. So we're making a lot of progress, a lot of headway. The Lord only knows how many exoplanets are going to be known 25 years from now. The Hubble Space Telescope was launched just 2 years earlier, in 1990. But the mirror was flawed. So when we came together at NEAF back in 1992, we were still working with a bum mirror. But then in 1993, they sent a servicing mission up, and now, of course, we have all these beautiful photographs from the Hubble Space Telescope. Believe it or not, the Hubble Space Telescope was only supposed to last 10 years. And now it's going into, this December, it will be going into its 27th year of service. And one of the keynote speaker in 1992 was Dr. Bill Gutsch. Do you remember Dr. Bill? He used to do the weather on Channel 7. He was also the chairman of the Hayden Planetarium. One of the speakers was John Bortle, the comet expert. He lives not too far from here in Stormville. And John gave a talk on great comets of the last 400 years, and he was lamenting at the end of his talk, well, at the moment we don't have anything to look forward to. There might be a great comet out there, but we have no clue. Who would have known 3 years later, Hale-Bopp was discovered. And 2 years after that became a spectacular object. While we were waiting for Hale-Bopp, the year before, we had Yakutaki. So we had 2 great comets. So you never know in astronomy how things change. In terms of popular culture, in 1992, Microsoft introduced Windows 3.1. Neil Papworth. Anybody know who Neil Papworth is? He's very special. He used his personal computer to send the very first text message to the phone of Richard Jarvis. And now, of course, you know, I have 2 kids at home. They never talk to me or my wife. They want something, they text. Even when they're upstairs in their rooms, you know, that's how they communicate. The first unofficial smartphone was developed in 1992 by IBM. The computer virus, yes, number 1 on the list of viruses, and so many of them now, that one comes out every other day, Michelangelo, activated on PCs. On April the 6th of 1992, a piece of sad news, Isaac Asimov passed away at the age of 72. On the very same day that that happened, though, Barney, remember Barney? And kids used to go crazy over Barney. First televised on the PBS network, and in May of 1992, The Tonight Show starring Johnny Carson aired its final show. All I can say is, boy, can we use Johnny now, couldn't we? TWA declared bankruptcy. Year-end the Dow Jones Industrials in 1992, at the end of that year, closed out at 3,301. Average cost of a new house, $122,500. The average income per year of an American, $30,030. The average monthly rent was $519, and gas only sold for $1.05 per gallon. Ah, the good old days. Anyway, enough with all of that. Here we are 25 years later, getting ready for NEAF number 26. And just very quickly, we have a number of great speakers. Ben Houlihan is going to announce our first speaker today, which is Roberto Abraham from the University of Toronto. After Roberto, we'll have Frank Demoro, who will talk about the Cygnus and Antares program. At 1:15, James Albury and Dean Regis will talk about the PBS series Stargazers. 2:30, Todd May. 3:45, Sarah Seeger. And 5 o'clock, Principal Investigator for the Juno mission, Scott Bolton. And then tomorrow, we have speakers such as Robert Reeves, who will talk about the Moon Lover's Guide to the Night Sky. You might call tomorrow Eclipse Day, because we're going to kick off at 1:30 with Mike Reynolds, talking about the big eclipse coming. There's an eclipse coming up later this year? 1:30, Mike Reynolds. And then at 2:45, some guy named Rayo is going to talk about how to survive the August eclipse. And believe me, you're going to need to know. If any of you are physics majors, I predict that on the roadways leading up to that day, it's going to look like Brownian motion. It's going to everything's going in all different directions. Caleb Weiss from ULA, Commercial Crew Program Manager, preparing to launch astronauts atop the Atlas V. And of course, we also have the Northeast Pro AM Conference featuring free walk-in classes. We have the Fieldhouse Theater Talks. We have, of course, the vendors. You can buy your husband or wife a Nabler or whatever you want to buy for Christmas or Mother's or Father's Day, whatever. Everything that you want in astronomy is out there. So we hope that you're going to enjoy these 2 days here at NEAF. I know I'm going to enjoy it. I always look forward to this. To me, this is the benchmark of spring. I don't care about March 20th. I don't care about a number of other items, like St. Patrick's Day or whatever. When this comes around, I know spring is finally here. And it looks like a great day out there today, and it will be tomorrow. You go outside, you can do some solar observing as well. I'm going to bring out now Vince Houlihan. He is going to introduce our first speaker, and I thank you very much. We look forward to having all of you for the next couple of days, and just get out and enjoy. Thank you.
Thank you. Hey, good morning, everybody. Welcome to NEAF 2017. We have a great crowd here today. Thank you so much for all being here. Who's here for the first time at NEAF? Well, welcome. You certainly will not be disappointed. We have a great program, like Joe said, we have lined up for you. We have excellent speakers. You certainly will be thrilled, to say the least. We have with us James Albury here in the audience with us right now. He's here. Friends, Kim and Dennis, good to see you. So, before we get started, though, I'd like to get a big shout out to the person who's the driver behind this entire program. Mr. Ed Siemens put this program together for us and for you, and if it wasn't for you, we would not be here. So I'd like to give a big shout out and applause for Ed Siemens and his staff from the Northeast Astronomical Forum. Thank you, Ed. Thank you, Jose. Thank you, Frankie out in the Fieldhouse, and all the other folks. So our first speaker today comes to us from the University of Toronto. He's a professor of astronomy and astrophysics. He is studying and looking at cosmological observing, and he is the principal leader in the Dragonfly program. How many have heard of the Dragonfly program? So this is kind of cool. It really is kind of cool because it talks about how you can take something literally as a paradigm shift and apply tools that any one of us can use to make serious advances in astronomy. Please give me a warm welcome and hello to NEAF 2017, Roberto Abraham. Welcome.
Thank you. Hi, everybody. Hear me okay? So I want to tell you about a really crazy project, okay? And this has an origin story. So the origin story really goes back to the very first day of graduate school for me back in 1988 when Ronald Reagan was your president, and I just turned up at Oxford University, not really knowing what I was doing. Okay, my undergraduate degree was in laser physics, and if you get a PhD from the UK, you do it through a program that has no courses. So here I am trying to do a PhD in astrophysics with basically 0 courses in astrophysics, and not really knowing what I'm doing. So what do you do with that circumstance? You panic. Okay, so I panicked. My way of handling this panic was to go to the nearest bookstore, and Oxford has awesome bookstores, and I bought a book, okay, and here's the book I bought. And I read that thing cover to cover. I read the hell out of that book, okay? And while reading that book, there was one figure that just captured my imagination, and I just haven't been able to let it go, okay? And here's the figure. So this is now, ridiculously out of date, yet the fundamental, basis for this figure remains, okay? And that is if you plot the sizes of galaxies along one axis and how bright they are along another axis, then all galaxies in the universe will exist in a band. And so above that band, you'll have things that are very star-like, and so you could envision ways where you could miss galaxies by confusing them for stars. And below that band, you will be missing things, or potentially could be missing things, because they're at too low a surface brightness. So what does that mean? So surface brightness is actually a kind of a tricky concept, okay? So everybody can get a handle on brightness, but surface brightness is the brightness per unit area. So imagine I have, say, 1,000 stars, and I've arranged them in a disk, and I take a picture. So easily visible. So this is obviously a toy model I produced on a computer. If I take those 1,000 stars and then I distribute them over a bigger area, what I find is it becomes a lot harder to see, okay? And if I make it even bigger, harder still. And eventually I will make it so big, I've spread all the light out, I've diffused it away, and I just can't detect a thing. So what this diagram was saying back in 1988 is that the universe could be hiding tons of galaxies out there that nobody has been able to see, simply because they're too big. So for me, that was like a red rag to a bull. People want to do science for various reasons. Some people really want to understand things. Other people want to find new things. So I have a little of both, but mostly I think I'm kind of a latter. I have this vision, that I want to be an explorer, discovering things, finding new things. And so the idea that you could be hiding masses of bizarre phenomena in the universe and nobody's ever been able to figure out how to find them has just obsessed me, okay? So still, it's not good to be driven by your obsessions, right? And so, I've built a career in astrophysics, and only recently have I gone back to this diagram. And I spent most of the last, nearly 30 years, okay, focused on other things, all right? And most of what I've been focusing on is testing the central model for how we form galaxies. How do we build galaxies? And this model is just based around the idea of dark matter. Okay, so 97% of the universe is in a hidden form. It's either dark matter or dark energy. And the idea, okay, that the 3% of the universe that you can actually see drives your interpretation of phenomena is a problem, right? So the way we handle it, of course, is theorists can build models, using computers. Ori, can you advance the slide? If you look at a just standard model for how the universe operates, it operates on the basis of the majority of the dark matter being located in these things called dark matter halos. So these are basically big spheres that contain mostly dark matter, and at their very centers, you have the stars and the gas that make up the galaxies. So Ori, can you advance? Great. Okay, so that's the basic idea, okay? And the notion of dark matter is wonderful. It explains so many things, but it's also sort of bugged me, okay? Because it's fundamentally not an observable thing. The observable things that we see are the stars. So recent progress is that we can now put stars into these simulations by using some physics that's not very well understood. So this is a computer simulation showing what you get when you put the physics of forming stars in dark matter halos into a computer model, and we're looking at the development of galaxies. Now, look what happens when the universe gets to about 3.5 billion years old. Can you see this stuff going on? So what's happening there is the galaxies are basically blowing up, okay? And this is a new thing that I contributed to, okay? About 10 years ago, I was the leader of this thing called the Gemini Deep Survey. And we were trying to test these models. And in order to test these models, we needed to be able to obtain distances for galaxies that were pretty far away. So we're looking at the universe. The scale here is given at the bottom left. And it's a young universe. The universe is 13.8 billion years old, and we're looking at it when it's just a few billion years old. And the predictions were that because in this picture you're assembling big galaxies by crashing together little things, eventually you would look so far out into space and back in time, you wouldn't see any big galaxies. And what we did when we undertook this experiment with the Gemini telescope on the summit of Mauna Kea was we found loads of massive galaxies where they should not be. So at that point, I was like, this is going to be the highlight of my life, okay? I've basically falsified, this central theory for how to form galaxies. And the amount of time it took theorists to be able to explain what we discovered with the Gemini telescope was maybe a month, okay? And what they did was they added this, exploding galaxies component to the model. So the explosion is really, you added supermassive black holes to the centers of the galaxies, the gas floods in, and eventually gets blasted out. So that wasn't in the models. So I spent years of my life modifying the Gemini telescope to, find this phenomenon, and it only took like a month for the theorists to add something additional to the models. And that has always bothered me, right? That isn't how we're told science works. Right? We're told science works by somebody making a prediction and somebody going out and testing it, and if the prediction's wrong, then the model's falsified. But this class of models was basically so ill-constrained, you could just add physics anytime something didn't agree with your model. And that bugs me. I don't think that that's the right way for us to be doing science. Yet, it works, okay? Ori, could you advance to the next slide? So, and the reason I think it basically works, and that at its heart this idea is probably right, but I'm not sure, is because with these computer models you get things that ultimately look like real galaxies. So these are not real galaxies. These are produced as the end product of the simulation that I just showed you. And I think these look pretty good. So I think there's something to this, okay? But still it's unsatisfying. This isn't the way science ought to work. You ought to be able to come up with a class of predictions and a thing you can test that doesn't rely on theorists being able to, anytime they want, just add new physics into it. So the question then is there a observable, okay, that I could go up to a telescope and measure something to test that would say this model is right or wrong, that would give theorists zero freedom to basically add additional things. So it's tricky, okay, but I think that the answer is yes, and it goes to the heart of these models. So at the heart of these models, what you've got are these dark matter halos that have little dark matter halos around them, and then little dark matter halos around the littler dark matter halos ad infinitum. Okay, so this is a thing that's basically a scale-free theory. So if I look, okay, at these models of dark matter halos, I can zoom in on them, and what I get looks like the original thing that I zoomed into. So to make that even more explicit, this is a dark matter halo of a galaxy, and this is a dark matter halo distribution of a cluster of galaxies, or did I get it wrong? I don't know. Unless I go down here and I read the caption, okay, that says it's a cluster on the top and the galaxy on the bottom. Okay, because it's a scale-free theory, you can't tell unless somebody gives you the scale. Okay, so that's profound, right? It means that, you know, big things look like little things if you have dark matter eyes. But we don't, okay? We don't have dark matter eyes. We can only see light from stars and gas, okay? So, right. So does this model work? Does this model work? Well, we can test it, okay, by looking at the number of galaxies as a function of mass. This parameter is basically mass. And this is for a cluster of galaxies. This is the Virgo cluster. This is data, and this is a model prediction. So for a cluster of galaxies, this idea seems to work. But then if you look at the Milky Way, which after all ought to be described exactly the same way as a cluster of galaxies, this is what we find. All right, so there's like a factor of 100 too few galaxies around the Milky Way if this model is right. So for me, that sounds pretty bad, okay? But if you're a theorist, you just basically say, those stupid observers, okay, they don't know how to find galaxies. And you can point to things like, you know, the diagram I showed first of all, and say that's an example of how you can hide galaxies. You can just make them have really low surface brightness. And so this problem, it gets a name, okay? It's called the missing satellite problem. It's part of the motivation for the construction of telescopes like this. So this is the Large Synoptic Survey Telescope, presently under construction in Chile. And when you look at this, it looks, well, my kids think it looks like a Pokeball from Pokemon. I don't know if, but in any case, it looks very unfamiliar as a telescope, right? It's incredibly stubby, and it's incredibly fast as an optical system. And that's a theme I'm going to return to. So, it has been constructed largely to try and, you know, get to grips with this missing satellite problem, okay? So here's an example of what you get when you plot the size versus the luminosity of the satellite galaxies to the Milky Way. And once again, they live in a band. Now, in this case, okay, because the axes have been reversed, the low surface brightness things are up here, and you see that there are no satellite galaxies to the Milky Way whose surface brightness is fainter than 30th magnitude per square arc second. So those are funny astronomer units, but I assume because you're a NEAF, you understand what a magnitude is. So really the key thing here is it's a brightness per unit area. So galaxies up here are basically too big for the number of stars they contain to be detectable. Okay, so that's the missing satellite problem. Now, there are other aspects to this problem. So Ori, can you advance? But it all gets down to that. Okay, you want to distribute light over a large area, and then things become undetectable. And that's how, if you're a theorist and you're desperate to always have observations agree with your data, you can explain anything. So your job as an observer is to outsmart the theorists, okay? And to come up with a way of observing what they say is out there. So those theorists are really pretty cunning, because there are two problems, okay? It's not just the missing satellite problem, there's another one, okay? And this is called the missing substructure problem, which is that if you imagine that what you're doing is you're building up big galaxies by crashing together little things, well, what happens when you crash things together? When you crash your cars together, basically, you get pieces of the car flying out everywhere, right? So similarly with the galaxies, when you crash the galaxies together, the debris from the crash goes everywhere. So in this picture for building up galaxies, if you look at a low enough surface brightness, then all galaxies should look like squash bugs, Okay, galaxies should just basically be nothing but a debris field when you look at low enough surface brightness. So these don't look like familiar galaxies. Like I showed you, these computer simulations are quite capable of producing beautiful spirals and things. But if you take it to the next level and you look at galaxies at fainter levels than that, lower surface brightness levels, every galaxy ought to be surrounded by this bizarre debris field that thus far nobody has ever seen, because it's at a level that's undetectable. So, those clever theorists. Can we observers outsmart the clever theorists? Well, and hey, so Johnny at the back, can you start making slides a little darker? Or the room a little darker if you can. Thank you. So this is an example, okay, of a beautiful image obtained by an amateur astronomer with a backyard telescope. Theme of this talk, okay, is that if you want beautiful astronomical imagery, we should turn to you guys, not to the professional astronomers. You guys know what you're doing in terms of making beautiful images. And some people will point to these sorts of structures, barely visible, but you can see that this thing has got sort of a loopy tail that winds around it, and say that that's an example of the debris you get from this model, you know, lots of little things crashing to make big things. That's actually not true, okay? This thing is the product of a merger of, you know, two pretty big galaxies. And what you're seeing up there is about a factor of 100 times too bright to be the debris field that's associated with this problem of missing substructure. So that ain't it, okay, that ain't it. So, Maureen, could you advance? Right, that ain't it, okay? So we have to figure out a way to go way deeper than even the deepest images that anybody has been producing. So, it's a problem, okay, it's a problem. So, let's wind, you know, a theme, I guess, given the introductory remarks, is, you know, looking, you know, back with nostalgia at the, 30 or 40 years. So 30 or 40 years ago, okay, when we were doing our astronomy with photographic plates, and, you know, the world's best telescope was a 200-inch on Mount Palomar, these two astronomers, okay, John Cormany and John Bacall, published a paper with the Palomar 200-inch, and they have defined the limiting surface brightness threshold that has been with us for 40 years, or more than 40 years. So how can that be? Okay, so back in 1974, the Palomar 200-inch, you know, if it tried pretty hard, could get down to, say, 23rd magnitude. And today, with Hubble, you know, if we try pretty hard, we can get down to, 30th. Okay, so that's many hundreds of times fainter, you know, in terms of galaxies today than we were able to do in 1974. So how can it be that the surface brightness threshold in this paper, which is about 29th magnitude per square arc second, is a surface brightness threshold today for all telescopes? We've made zero progress in getting to lower surface brightnesses in the last 40 years. How can that be? So, okay, so before you do anything in life, I think you should ask whether or not it's important. Okay? So before I try and answer why that is, let's try and persuade you that you should care. Okay? And so the real reason I care, okay, is because, you know, I really want to test these models for forming galaxies. So the missing substructure and the missing satellite problems are the things I really care about. But other people care about getting to low surface brightness for other reasons. So for example, many of you don't know that we discovered a new ring around a planet in our own solar system just a couple of years ago. Okay, it was discovered by Cassini around Saturn. And that ring, discovered with a spacecraft, ought to be visible from Earth, okay, if you could just get to low enough surface brightness. And furthermore, the theory that explains that ring says that every outer planet ought to have a giant dust ring as well. So there are rings around planets in our own solar system just waiting to be discovered. the back on a reasonable amateur, mount. So this project was concocted by Peter Van Dockum at Yale and myself. And within a week of us deciding that we were going to tackle this project, we, purchased a lens, and we, assembled the equipment, and we've gone out and we just tested it. And you have no idea how fun that was. So this is going to be a 30-second digression. Peter was the chairman of the astronomy department at Yale. I was am actually on pretty much every committee known to humanity. Okay, I was on at the time I was running our graduate program. I'm on the Gemini board of directors. I'm on the science advisory committee for the 30-meter telescope. I'm on the James Webb Space Telescope advisory committee. And here's a secret: eventually, that sucks. Okay? And the people that are having the fun are the graduate students and the postdocs and the amateur astronomers. Okay, so when Peter and I had our, little angst-filled conversation that led to this project, what we were trying to do was to capture some of the fun that you guys experience, every weekend, and that we had as graduate students and postdocs. So we did this. We just decided we were just going to do this. So why would telephoto lenses be good for this? Well, it turns out that we're living, in a wonderful time. And one aspect of the wonderful time we're living in is that there are some terrific advances being made in optics. So you can walk around NEAF and you'll see many of those before your eyes. But one of them that you might not be aware of is, can you back up one? Thanks. One more. One more. One more. No, sorry, go forward. Sorry, we're having trouble with this thing. Okay, keep going forward, please. I just have to show you this picture, okay? Forward. Forward. Okay, one more. Okay, thanks, Ori, stop. Okay, so the advance we're currently living through, okay, is revolution in material science mean that we can generate essentially perfect optical coatings. Okay, so the Canon Corporation has come up with this technology for laying down nanostructures, okay, on glass. So the material of regular optical coatings, but geometrically arranged, okay, so that they look like little cones or little pyramids. And there are multiple little cones or little pyramids per unit wavelength of light. Okay, so it's fantastic technology, and I have no idea how it's done. It's secret. Okay, but if you believe the engineers and marketers for the Canon Corporation, these magic coatings are fantastically transmissive, which means that you can have multiple pieces of glass coated with this stuff. And its transitivity is incredibly high. Okay, so if it's incredibly high, it's relatively light that gets scattered around. And it also means that you don't need to have any mirrors. Okay, so mirrors are 99% black, 95% black. But what happens with the 10%, 5% of the light isn't reflected back in a nice way. Well, a lot of that is getting scattered. Okay, so that's why, for example, the solar astronomers who really care about scattering light mostly use refractors. So our big idea, okay, was that we want to talk 100 years to the golden era of refracting telescopes, and maybe see if this latest generation of telephoto lenses could take pictures of things with hardly any scattered light. So we made some measurements with this thing, and found that if you look at the scattered light on scales of about a degree, so I won't bore you with details, these are scales of about a degree, we're about a factor of 10 better than any other telescope on the planet. Okay, so a factor of 10 on large scales. So that's what we care about, scattered light on degree scales. These sorts of telephoto lenses offer a sort of magic bullet for doing certain types of astrophysics. So, one is good, 3 is better than 1, and 8 is better than 3, and 10 is better than 8, and 24 is better than 10, And 48 is better than 24. Okay. So, Ori, go back one, please. Because I want to. Yeah. Can you keep advancing? Keep advancing. Because I just want to awe these people with the craziness of this project. Okay. Two more. Okay. One more. There you go. Okay, so there it is. Okay. So that's the dragonfly telephoto array. So it's two independent arrays, each of which has 24 of these $15,000 per lens Canon NEAF lenses. Or actually, not 12,000, so it's steel. And on the back of every lens is a CCD camera with a miniature computer. Okay. A Canon NEAF 400. ISL22. Okay, so that's the dragonfly telephoto array currently looks like. All right. Sorry? F2.8. Okay. So why would this crazy thing work? Okay, why would this work? So for most things in astronomy, you want a large telescope, and you don't want the dragonfly telephoto array. Okay? Because for most things in astronomy, you're trying to do things like resolve point sources. Okay, so if you're trying to do astronomy that operates on the scale of say, you're seeing, okay, then what you want is a telescope that has a figure of merit for how good it is that goes as the aperture squared. Okay, if you're in a regime, say, in space or with adaptive optics, then what you want is a large telescope as well, and it's even better in that case because your figure of merit, how good it is, goes as the aperture to the 4th power. But let's say you're trying to do a particular type of astronomy. You have a particular class of problem where you don't care, okay, about resolution because you're looking at things on a large scale. Then you have a figure of merit for which you don't have aperture entering into the equation at all. Okay, what you have is this. So what enters into your figure of merit is the focal ratio of your telescope. So you want a fast telescope. You don't really want to have a big telescope. You want a fast telescope. Okay, so that's why this works. Okay, these telephoto lenses are pretty fast. They're each, f2.8. So it's a novel concept. Okay, but why why would you want to have multiple ones of these things? What's the benefit in having lots of these things? So Ori, could you go back one? So the idea here is to kind of harness Moore's law. Okay, so the doubling timescale for a telescope aperture is actually really long for the world's biggest telescope. It's of order 30 or 50 years. Okay, so it's really a long time. On the other hand, Moore's law is doubling the performance of a silicon chip roughly every 18 months. So we were sort of inspired. Is there a way we can harness the glass and chips are both made out of silicon? How's about coming up with a way where we can use the performance of the type of glass or the type of silicon that's doubling in performance every 18 months rather than every 30 years? So that was the idea, the sort of inspiration for this. So the effective aperture of a dragonfly-like system, okay, where you combine all of the images as they come in not quite in real time, but you do combine them, is that you can grow the aperture so it's effectively the equivalent of having the square root of the number of lenses times the aperture of one lens. So each lens is about a 5.5-inch lens. Okay, so if you have 48 of these things, okay, then it's effectively a 1-meter aperture. Now the focal ratio, because after all, that's the thing that apparently matters in this particular niche type of problem, goes as the focal ratio of one lens divided by the square root of the number of lenses. So right now, with 48 lenses, Dragonfly is not only a 1-meter refractor, it's a 1-meter f0.39 refractor. Okay, so when we bolted that 48th lens onto Dragonfly, it became the biggest refractor on the planet, except not being f20 like yours, it's f0.39. So, we're thinking seriously about growing Dragonfly to 500 lenses. So if we do, then it's going to be a 3-meter aperture f0.12 refractor. So I told you this was nuts. Right, so what do you do? What do you do with such a thing? Okay, well, I'll describe what you do with such a thing in some detail for most of the rest of this talk. But let me also point out that when you start taking pictures with these incredibly fast setups, you find that there's an enemy, okay? And the enemy is galactic cirrus. So this is what you get, okay, when you look at high galactic latitude, so not at the center of the galaxy, on the plane of the galaxy, we're looking, way off of it, just at a random piece of the sky. So this is just a almost random galaxy. And in 1 hour with 3 lenses, you see that you're completely contaminated with this stuff. These are, clouds of gas and dust falling into the galaxy, or in some cases being expelled from the galaxy, and they're reflecting the starlight from the stars in the galaxy. So that's what galactic cirrus is. This material is basically acting like a mirror, reflecting the starlight. And so you don't really worry about this stuff generally, because generally it's hard to find. But with this setup, it's so easy to find. You have to be really careful in your choice of where you point this thing. You have to basically pre-select on the basis of infrared satellite imagery holes in the sky that aren't brutally contaminated by this galactic cirrus. Okay, so then what do you do with it? Well, let me tell you what we've done with it. So we've launched some explorations of galaxy halos. We've asked a few questions, fundamental questions, like how big are galaxies really? And we've spent a fair bit of time trying to find new classes of galaxies. That's probably the most exciting results so far. And where we're going to go with this, okay, if I have time to describe it, it would be great, okay, is we're going to, I hope, launch an investigation of something called the cosmic web, which I'll explain soon. Okay, so let's start off with the first one. So Johnny at the back, if you can make the room super dark. And so the reason this has to be super dark is because we're going to be looking at low surface brightness stuff. Okay, so there's a truism, okay? If you crack open a textbook, for example, the one that inspired me all those years ago, what you'll read, okay, is that if you have radio eyes, you will see that galaxies are twice as big than if you use your eyes, which are sensitive to light at visible wavelengths. Okay, so, and the reason for that is, of course, what you're seeing here are stars, and what you're seeing here is gas, okay, but a particular type of gas, neutral gas. And you don't form stars out of neutral gas, you form stars out of molecular gas, molecular hydrogen. And so the molecular hydrogen is in the inside, and this neutral, so that's why there's a hole here. And so, the neutral material goes way further out, and so that's why with the radio telescope, galaxies are twice as big, because you can't form stars out here. Okay, so is that true? So this is a Hubble image, okay, of an archetype of a certain type of spiral galaxy called a flocculent spiral. This is NGC 2841, and it's a beautiful Hubble image, and you can see tremendous detail, in this galaxy. But the deepest image of NGC 2841 that I was able to find was actually not obtained with the Hubble. It was obtained by an amateur astronomer. Okay, so this is the point I was making earlier. The amateur astronomer is not trying to resolve fine detail in the center of the galaxy, trying to find stuff out here, and is able to do that with a relatively small telescope. So it's a beautiful image. Okay, so this amateur image of NGC 2841, I'm going to guide your eye with this circle, okay? So that's at the 25th magnitude per square arc second isotope. So this is usually what astronomers refer to when they talk about the size of a galaxy, okay? They talk about the D25 limit, because that's typically how big a galaxy looks on a typical image. So D25. There's a handy reference star to kind of calibrate you, and this is the limit of this thing when seen with a radio telescope. Okay, so for NGC 2841, what I said earlier is true. Okay, the radio eyes see this galaxy as being twice as big. Now, let's look at this dragonfly data and compare. Okay, so first of all, I'm just going to turn it to 7, okay, my comparison. So that's the reference image I just showed you earlier, and I'm not trying to build tension here. Ori, can you advance 1? Thank you. Okay, so that's the dragonfly image for comparison. And so, first of all, you can see it's clearly much bigger, but also it's showing what looks to be either rings or spiral arms beyond the limits of the stars. which should be impossible. Okay, so the reason this thing is a flocculent spiral is it's dynamically stable. And so the spiral arms here have to be generated by a process that isn't the usual process for forming big spiral arms, and yet there they are. Okay, so that's, mystery number one. So let's look at the radio image, and so that's the radio image. So you can see that a lot of the spiral structure in the outer part actually maps very well onto the radio. So already we've got a mystery, okay? Because remember, this shouldn't be able to form stars out there because there's no molecular hydrogen. So what are those stars doing there? Okay, so that's kind of a puzzle, but really we're only looking at this thing, turning it up to 7. So what happens when I turn this up to 11? Okay, so this is when I just really try and stretch the Dragonfly data like crazy. Okay, so here are the limits of the radio data, and you can see stars there. Okay, so at the limits of the radio data, even this little kind of jet-like structure has got stars. Okay, so this thing is basically rewriting the textbook. Okay, this galaxy in stars is as big as it is in gas. So how can that be? How can that be? You shouldn't be able to form stars there. So the answer is nobody knows. Okay, and this is what I like to do. I like to cause trouble for theorists. Okay, but we do need to rewrite the textbook. Okay, so if you open your textbook, you'll see this picture which shows the disk of a galaxy embedded in a dark matter halo, and you'll see that the disk doesn't go very far. Well, what Dragonfly is finding is that the disk actually goes much, much further out into the dark matter halo. In this case, 100 kiloparsecs, or about 25 scale lengths, which is, a typical image only goes out, say, 5 or 6 scale lengths. So we're able to go much, much further. Okay, so Ori, back one, please. Okay, so that was the first thing. How big are galaxies? Well, I can tell you that galaxies, at least some of them, are much bigger than we thought that they were. Okay, but let's look at the next problem, okay, which is, circling back now to that band that I talked about at the very beginning. What lies below that band? What does the universe have in store for us if you look below that band where nobody's been able to look before? So we my colleague Peter Van Dokkum and I were ill-disciplined, okay, because we launched a very carefully planned program of investigation to look at 20 nearby galaxies to undertake the PhD research for 4 graduate students. And we had a cadence for this. It would take 2 years, and the grad students would get this fantastic data, and we'd publish a bunch of papers. But partway through, we were getting this kind of weird feeling again, okay, which is that we did this thing to have fun. And it was proving to be successful, and the more successful it got, the bigger it got, and it started to get less fun. And so we were like, screw it, we're gonna have fun. Okay, so we decided that we were gonna push the pause button for a month on the Dragonfly project, and we were just gonna take a picture of something we thought would be really cool to take a picture of at low surface brightness. So we decided to take a picture of the Coma Cluster. Now the Coma Cluster is probably the most photographed area of the sky. And so we were trying to make a point here, okay, which is that the universe is so unexplored at low surface brightness levels that you can point Dragonfly anywhere and you'd probably find something interesting, okay? And boy, did we get our money's worth out of this observation. Because when we pointed the Dragonfly telephoto array at the Coma Cluster, what immediately popped out to Peter's trained eyeballs, because he noticed this and I didn't, okay, was that there's a large population of enormous low surface brightness galaxies. So these things had been right under our noses, since Edwin Hubble had been photographing the Coma Cluster in the 1930s, right? A whole new class of galaxies. So I like to show this slide for a bunch of reasons, okay? So, we found 57 of them. As a result of our discovery, people have gone back and looked through data and taken more data, and there are now over 800 ultra low surface brightness galaxies, which we now call UDGs, or ultra diffuse galaxies, in the Coma Cluster. And I'd like to show this slide because it shows where these things are located, but also because it makes the point that Dragonfly is good at some things and terrible at other things. Okay, so if you look at CFHT, so this is the Canada-France-Hawaii telescope, arguably, the best telescope for this kind of science. If you look at images from the Canada-France-Hawaii telescope, CFHT typically has seeing of, I think the median seeing is like 0.65 arc seconds. Okay, so it's fantastic. So look at these point sources on the CFHT image and compare them to Dragonfly. They're terrible. Dragonfly is awful. On the other hand, for the diffuse structures, compare Dragonfly to CFHT. There's no comparison. Dragonfly is miles better. So if what you're trying to do, okay, is to look for faint point sources, what you want is a big conventional telescope on a great site. If what you want is to find these big diffuse galaxies, that's where something like Dragonfly can make a contribution. So pick your problem, okay? But using Dragonfly, we discovered ultra-diffuse galaxies that nobody had ever known about before. So what you should envision, okay, is something about the size of a conventional massive galaxy, but with 1/100th to 1/1000th the stars. So that's awesome, but why is it important? Okay, so one reason why it might be important is because these things cannot exist in conventional models for forming galaxies. In conventional models for forming galaxies, you have a certain amount of dark matter, and that dark matter accretes other material, and you get a certain abundance of stars. So there's a close to one-to-one matching for how you get stars in galaxies. And the bigger the galaxy, the more efficient the process. So at the high mass end, you should have essentially, a pure dark matter halos. But that's what we may be saying here. Okay, so we may be saying a large, massive galaxy that's almost totally dark matter. So this set the world on fire if you're a theorist. They're now, so this, our discovery paper for this thing came out at we put it on the internet end of 2014. It actually came out in the AppJ in 2015. And since then, there are 900 papers, roughly, following up on this thing. And so, there are observers who are finding now ultra-diffuse galaxies in all sorts of unusual environments. The theorists are trying to figure out how you can explain away the thing that I just described. How can you get something that's got a lot of dark matter and have hardly any stars? So theorists don't like this. Okay, theorists, whenever you come up with something that is a puzzle for them, their instinctive reaction is that the observers have screwed up. And I actually have respect for that because sometimes they're right. To cut them some slack and to be fair to them, it's actually possible that these might be very big galaxies, but not have way more dark matter. You could imagine ways that you could take, for example, a conventional galaxy and somehow figure out a way to just make it way bigger without giving it more dark matter. So, is that what's going on? The answer is, I don't think so, in all cases. Okay, but in some cases it probably is. So this has now become sort of a fight, okay, between two models for explaining these things. One of them is the failed giants model. So the failed giants model says that this ultra-diffuse galaxy is a ton of dark matter and somehow just failed to make stars. And the other one is the inflated dwarfs model, which is that it's a dwarf galaxy and somehow nature has just made it way bigger without giving it more dark matter. Okay, so it's a bit of a fight between these two. And my opinion is that both are going to be right. And the reason I think that is because I have faith in nature. Okay, we are looking at the low surface brightness universe, which is totally unexplored. Physics says both of these things are possible. My experience says that whenever something's possible, nature figures out a way to do it. Okay, so that's why I think both of these things are going to be happening. So, to just kind of calibrate you as to what kind of galaxies we're looking at. If you plot, again, so in this case it's surface brightness versus size. This is the distribution of all galaxies in the Sloan Digital Sky Survey. That's where the Milky Way disk is. And these are a class of objects known as Virgo dwarfs, because you can For very, very, very nearby galaxies, where you can actually resolve the galaxy into stars, you can probe down to low surface brightness levels. So there are these very nearby, very tiny galaxies that we can probe down to these low surface brightness levels. But for big galaxies up here, what you can see is that the dragonfly objects exist in an area of this parameter space that was just empty before. So it was like, there was a map, here be dragons off on the boundaries, and suddenly we filled it in with, islands and topography. So we've just opened it up. Right, okay, so now here's something you'll find amusing, or at least I find amusing. So we discover these things with telephoto lenses, and we follow them up with the largest telescopes on the planet, and it's hard. Okay, so most of, you should think of Dragonfly as basically a finder telescope these days for Keck and Gemini and the VLT and Hubble. Okay, Dragonfly identifies these things, but you need the bigger telescopes to figure out what they are. Okay, so this is a spectrum obtained with 30 hours of Keck time. So, time on these large telescopes is difficult to get and very expensive. Okay. I actually know the numbers, but I'd probably get shot if I told you. But many tens of thousands of dollars a night, okay, to use a large telescope, and closer to 100,000 than to 10,000. Okay, so these are very expensive telescopes to use. So this is 30 hours with the Keck telescope on one object. Okay, object known as Dragonfly 44, and so that's what it takes. It takes, basically, 5 or 6 nights on Keck to follow up on a discovery made with telephoto lenses. How crazy is that, right? But in any case, if you do that, okay, if you're crazy enough to devote 5 or 6 nights of Keck time to this, you actually can do some amazing things. So this is an absorption line spectrum, and the width of this absorption line tells you about the mass of this thing, because the width depends on how fast the stars are moving, and how fast the stars are moving depends on the gravity, and the gravity depends on the stuff that's there, the dark matter. So using this, we can determine that this is actually a pretty heavy galaxy. Okay, so in this case, it's likely to be a failed giant. Okay, lots of dark matter, very few stars. On the other hand, here's another object that we also followed up with Keck, similar, heroic Keck observations. And in that case, the mass is actually relatively low. So I do think that nature is telling us that, it is smart enough to come up with multiple ways of making these ultra-diffuse galaxies. But there's a better way to do this, okay? So the better way to do this is to use a large telescope, and rather than take pictures, rather than take spectra, take pictures. But it has to be the right large telescope, and it has to have great conditions. So this is what you get, okay, when you take an image of Dragonfly 44 with a Gemini telescope, and hold on to your hats. The seeing here is 0.35 arc seconds. So that's what these large telescopes can deliver without adaptive optics. Okay, so 0.35 arc seconds with the Gemini telescope. What do you think these are? Well, there's the hint. Okay, so what we're seeing here is a population of globular clusters around this object. So globular clusters are, this is actually a relatively recent discovery. Okay, but there's a relationship between the abundance of globular clusters and the mass of a galaxy. So this has been established on the basis of gravitational lensing. Okay, so you can't see dark matter with your eyes, but dark matter does bend light. Okay, so by looking at the way light gets bent around and by galaxies, and then counting the number of globular clusters, you can see that just by counting the number of globs, you can get a handle on the amount of dark matter that thing has, which is actually pretty remarkable. Okay? It means that you can use the finest ground-based telescopes or the Hubble Space Telescope. You can follow up on these things, and you can determine the amount of dark matter they've got. So this is Dragonfly 44. So if you undertake this experiment and you count the number of globular clusters in this thing, which we did, what you find is it's a large number. Okay, so the Milky Way has about 150 globular clusters. The Andromeda Galaxy has about 230, 250. Okay, and so that tells you the relative masses of these things. And so in this case, it has about 100 globular clusters, which immediately rules out that it's a dwarf galaxy that's just been made big. So this is a failed giant galaxy. So this is a easy way, okay, a relatively easy way to determine the masses of these things. And in this case, you can tell that the masses are huge. Okay, so this was nuts. Okay, and it almost made me mad. Okay, that I spend a quarter of a century doing astronomy, with the largest telescopes on the planet, occasionally somebody will care, but generally the only people who care are other astronomers. And you start doing astronomy with telephoto lenses, and then you wind up being the lead article on CNN. You wind up being on the front page of the Washington Post. So it's remarkable how this idea has taken off. And I think it's a reflection of multiple things. Okay, but one thing I think of is that perhaps it shows that it's possible to do something off the wall that tickles people's fancy, and that's how you wind up on the news. And that's one aspect of it. And the other aspect of it is that potentially, at least, it's really important. Okay, so there was a beautiful quote by Freeman Dyson, who last year said that dragonfly was a scientific highlight of the previous year. And in my opinion, no way. Okay, scientific highlight was the discovery of gravitational waves by LIGO. But nevertheless, dragonfly was pretty good. Okay, and what it does do is give you a laboratory for dark matter physics, because you can go with these large telescopes and soon with the James Webb Space Telescope and explore the properties of things like Dragonfly 44, and there's enough light to let you figure out where things are moving, but there's not so much light that it contaminates the underlying dark matter signal. So I think that these ultra-diffuse galaxies are going to be wonderful laboratories for doing dark matter investigations. And so I wanted to basically tease you a little bit. So I'm not sure if I'm going to leave this in the video. I might, okay? But I wanted to tease you with one thing, okay? So the Hubble Space Telescope time application deadline was last night at 8 p.m. And so until 7:59 p.m., I was working on a proposal to follow up on a discovery for a nearby ultra-diffuse galaxy made with Hubble a few months ago. Okay, so we have a program in place to image these with the Hubble Space Telescope. So this is a nearby ultra-diffuse galaxy, and if you zoom in on this thing, what you see is this. So I don't know if this is super obvious from the back. Tell me. Can you see a structure that looks like this? Sort of a reverse S? Well, that's probably a stream. Okay, so certain classes of object, like globular clusters or dwarf galaxies, when you drop them into bigger galaxies, they are destroyed. Okay, so people argue about the number of globular clusters that once existed around the Milky Way. So like I mentioned earlier, there's presently 150, but earlier on in the history of the Milky Way, there were more, okay? And then, but through this operation of dynamics, sometimes you get an unlucky orbit and the thing gets torn apart. So that is what I think is happening here, okay? Is that we've got a globular cluster or a dwarf galaxy dropping into this ultra-diffuse galaxy and it's being torn apart. But all known streams basically look like that. Okay, because things in space move in elliptical orbits. Things in space do not take sharp right angle turns. Okay, so something weird is going on with this object. Okay, so it seems almost as if this object, which looks smooth and round, is a collection of maybe dark matter that shows a ton of substructure. Okay, so if we could look at this thing with dark matter eyes, maybe what we'd see is a dark matter halo there and a dark matter halo there, all dropping into a bigger dark matter halo. In which case you can use the existence of these streams to tell you about how the dark matter in this thing is organized. Without using your dark matter eyes, the dragonfly discovery ultimately will tell you about the physics of the dark matter and how it's distributed. Or we're idiots, and this isn't a stream at all. Okay, so that's what we're doing with the Hubble Space Telescope to try and follow up on these things. That's an example of the sort of thing you can do. Okay, so where would you go next with this? So we're seriously tempted, okay, to just basically take the dragonfly concept and just grow it. I mentioned earlier, we're at 50. I don't know where we can stop. Okay, every time you've got $15,000, you can bolt another lens onto this thing and you can keep growing it. Maybe at some point it becomes silly and you should just stop. And Dragonfly has become sufficiently successful that other people are now cloning it. So for example, the Anglo-Australian Observatory is going to be putting one in the southern hemisphere. And this is beginning to sound ominously like something that's non-fun. And so the thing that made this so much fun was the initial crazy aspect of it. So we're wondering if the next thing we ought to do with this idea is to continue the craziness. Okay, so I'll tell you where I hope that we can go next. And it requires you to remember when I showed you these earlier simulations. Okay, so this is the distribution of dark matter in a simulation. This is 10 megaparsec cubed. So let me remind you, the Andromeda Galaxy is about a little under 1 megaparsec away. Okay, so this is a little over 10 distances to the Andromeda Galaxy. So this is a pretty reasonable volume. It's halfway in terms of size to the Virgo cluster. Okay, so it's a big ice cream scoop out of space. And so if you look at these dark matter halos, these are the round things. What's this stuff in between? Okay, so this is something called the cosmic web. So most of the dark matter is collected into these halos, but lots of it remains in a sort of a diffuse state that looks like a spider web that joins together all of the galaxies. And it acts like a highway, okay, for funneling material that builds up galaxies. So the highway is, or pipes basically flow the gas into the galaxies from which you build up the stars. So if you look at the distribution of stars in this box, it looks kind of boring, right? You've just got a few galaxies, but with your dark matter eyes, you see all of this fantastic structure. So here's a thing, okay? If somebody were clever enough to come up with a technique for letting you image not stars, but gas, okay, what you would see is this. All right, so this is the distribution of gas being funneled along the highway destined to form the galaxies at these nodes. So this gas is visible, it's just freaking hard to see. Okay, so one way of seeing this gas is to build a gigantic new radio telescope. So for example, there's this thing called the square kilometer array that has as one of its main goals detection of the cosmic web in the nearby universe. And that's awesome. I really look forward to the time that the square kilometer array does this. But it's going to be like a decade out, and it's like a $2 billion project. Okay? So is there a way that you could find this gas without waiting a decade and spending $2 billion? So, Ori, can you advance? So I think maybe the answer is yes. Okay? So some of the gas, cools off and it gives off emission lines. So most of those emission lines are going to be ultraviolet. Okay, so most of the energy from that gas is going to be invisible from Earth because the main emission line is Lyman alpha, which is often the UV. But 1 in 20, roughly, of the ultraviolet photons in the ultraviolet emission lines is going to emerge in hydrogen alpha, which you, being a bunch of astronomers, know you can just buy a filter. Okay, and with a hydrogen alpha filter, you can take pictures of glowing gas. So the problem is this stuff is just really incredibly faint. So the surface brightnesses on these plots, which are dragonfly-sized fields, so dragonfly has a field that's roughly 2 degrees on a side. It's 2 degrees by 3 degrees roughly. If you could take a picture of this gas, this is what you'd see. Okay, you'd see the cosmic web. But this stuff is incredibly faint, and the emission is incredibly narrow. So can we, using a dragonfly-like setup, image this stuff? And the answer is I think we can if we play a trick, okay? And the trick is not putting this filter in the cameras or in the lenses, instead putting them in front of the lenses. Because again, as you amateur astronomers know, the performance of these depends on a bunch of factors. One of them is, for example, the speed of your optical system. And so these filters like optical systems that are very slow, not very fast. But if you put one of these lenses in front of Dragonfly, then the speed of the optical setup is infinity. You know, it's incredibly slow before it hits the lens, and then it becomes very fast. So that's the trick. The problem is we need 5.5-inch hydrogen alpha filters, and they would cost about $10,000 each. Okay, so I don't know what to tell you. For me, that's kind of a great deal. So if we can get 48 of these filters and put them on the Dragonfly array, I think we could start probing the cosmic web next year for $500,000 rather than in 10 years for $2 billion. So this is a simulation done by one of my students. So what she did was take a hydrodynamical simulation of the cosmic web and put these little boxes on it to try and see whether or not she could detect hydrogen alpha from the cosmic web in a reasonable amount of time with the Dragonfly array that I've just described with the hydrogen alpha filters. And the result is kinda, okay? So with a 48 lens Dragonfly in this case 10 hours, you can get a signal to noise of between 2 and 3 for the brighter pockets of this thing. And where this gets interesting is with a 480 lens Dragonfly in a 100-hour integration, you can start getting signal to noise of 3 in the stuff that really delineates the cosmic web. So I think you can do this. Okay, so I think you can do this now. Well, for $500,000, then you can do this next year. Okay, so the net result is that this, before last year, was the world's largest telescope, refracting telescope. Yerkes 48, you might recognize this person. And this is half of the world's largest refracting telescope today. And that's Charlie Connery from Harvard, who couldn't make the trip. Okay, and so I think we're at 48 now. Where I hope we are in a few years is at 480, and it's been kind of a wild ride, and I don't see an end to it yet. And so I think I'll stop there. Thank you very much. So they told me to leave time for questions, so if there are questions. Yeah.
If you talk about the detectors that you have on the back of this, where is Dragonfly located?
Yeah, so I'll read I'll speak the question out again. So the question is, what detectors are on the back of Dragonfly and where is Dragonfly located? Okay, so Dragonfly has these SBIG STT8300 cameras. And so it's this, the Kodak KAF 8300 detector, which is, reasonable, but not the world's greatest detector. So we're certainly envisioning upgrading that. And Dragonfly is located in New Mexico. Okay, so it's at the New Mexico Skies Observatory, and I can't say enough good things about those guys. They've done an outstanding job of operating it. So it's basically the graduate students write a little script in the afternoon, they set it going, and then Dragonfly takes all its data during the night, and then we just download it the next day. Sure, another question.
How critical is the mechanical alignment of all those OTAs?
Okay, so the question is how critical is the mechanical alignment of all those OTAs? In our case, not very critical. Our exposure times are only 10 minutes, and in 10 minutes, nothing seems to flex very much. I would say, over-engineered it. If you look at I guess it's shown here. It's a structure that's held in place by all of these aluminum tubes, and there is some flexure in this setup, but in 10 minutes, it's basically ignorable. If we start doing much longer, hour-long integrations for this cosmic web project, then I'm a little more worried. But so far it seems fine. Yeah, back there. Yeah.
At the beginning of your presentation, you mentioned that visible normal matter was only 3% of the total. Because if you had $100 million to build a really huge one of these, would you start seeing so much more matter that affects that?
Yeah, I guess the question is, if we had $100 million, would we be able to take pictures of dark matter? Is that?
Yeah.
Yeah, what you should be able to do with, upgraded Dragonfly is see fainter and fainter structures. So the dark matter halos have some stars, we think, although we found examples of some that have barely any stars. So with a bigger Dragonfly, we would be able to find even more of those surface brightness things. And then with the narrowband filter, we would be able to find the gas that would be there even if the stars aren't. So in some ways, the gas is safer than the stars, right? Because you have to have funny conditions to form stars, but for gas, you just need gravity to suck the gas in. And so that would let you, detect something irrespective of almost any other assumptions. Yeah. So another question here.
Yeah, I was reading where we discovered that the halo around the Andromeda galaxy extends about halfway to the Milky Way. Were you involved in that?
No. Okay. So the question is about the extended Andromeda halo. Yeah. So the Andromeda galaxy is an unusual galaxy. So so I was not involved in that study, but what I was involved with is an investigation of how the halo in the Andromeda galaxy compares with that of other galaxies. And it turns out that the Andromeda galaxy halo is unusually big, and an unusual amount of stuff has been going on. So what's funny about this is that the Andromeda galaxy has been a reference, since the 1920s. So because we were using this unusually big, unusually active halo as a reference, our ideas for what typical galaxy halos look like is wrong. So most galaxies are actually more boring than the Andromeda galaxy.
Also, the failed giants, could it be that that's still a forming galaxy that's formed from dark matter in an area where there wasn't a lot of stars and gas and dust, and as it moves, it can accrete more stars and gas and dust and become more like a regular galaxy?
Yeah. So the question is, could a failed giant galaxy evolve into a more typical type of galaxy? And so the answer there seems to be yes. Okay. So people are actively working on that. So is it a stage where you're looking at galaxies at different points in their life cycle, and ultimately, are these failed galaxies, failed giants, going to accrete enough stars that they look normal? So some theorists will say yes, but then other theorists will say it's impossible to have a failed giant in the first place. So like I said, I like to make the theorists uncomfortable. That's a good thing. I should go back there. Yeah, back there.
Obviously, these are commercially available Canon lenses designed to be electronically focused by a Canon camera. You're not doing that. So how did you do it to get those electronically controlled, independently focused, every one of those, keep them focused with temperature drift? How did you do that?
Okay, so this is a nerd level question, which I'm actually very happy to answer. So there's a company, called Berger Engineering, that manufactures a Canon EF focus controller that you can stick onto the back of your lens, and it listens to commands on the serial port that will move the focus point on these lenses in and out. So it's about $1,000, but on a $12,000 lens, that's fine, right? So we use those, and the focusing is done by software written by me. And it's actually very easy. I don't understand why people have angst about focusing. Focusing is easy. So you take a picture, and then you run, the software source extractor, which is, professional. It was written in France for use by professionals, but I know lots of amateurs use it. And so you use source extractor. You measure the mean full width half maxes of your image. Then you move your focus a little bit, and then you measure the mean full width half max. And then you do that to define a parabola of full width half max versus focus position, and then you just go with the minimum. So it's trivial. We can focus one lens in about a minute and a half. And because of the way Dragonfly is designed, everything is totally parallel. So I can focus 1,000 lenses in the same amount of time it takes me to focus one. and then we monitor the images in real time, and if the focus has drifted, then we know the temperatures. We apply an active correction to tweak the focus, and then if it's still not working, then Dragonfly is smart enough to know I need to focus, and so then it takes a minute or so and refocuses. It's really easy. So the key is massive parallelism, right? You get one camera that operates automatically, or one lens that operates automatically, then it doesn't matter how many lenses you've got. Okay, another question. Well, hold on, I should go in the back because I haven't done the back. Okay, at the back there.
Yeah, would you expect the thing H alpha mission you mentioned at the end of the web of H alpha, would that be overwhelmed by the galactic cirrus you mentioned?
Oh yeah, so that is a worry. Okay, so the question is, would I expect the cosmic web to be overwhelmed by the galactic cirrus, which is also distributed over these large scales? So the galactic cirrus won't be emitting in H alpha, but it will be doing is it's acting like a mirror, reflecting off of everything that's emitting H alpha in our galaxy. So I'm a little worried about that, but I'm not that worried. And the reason is because since the universe is expanding, the H alpha from the galaxies we'll be looking at will be shifted relative to the H alpha that's being mirrored by the galactic cirrus. So I think provided you're clever and you don't look at things that are too close, you'll be able to just, by using the appropriate narrowband filter. So it's chosen to not be centered on H alpha in the galaxy. It's H alpha multiplied by some redshift. You'll be fine. Or 1 plus some redshift. Okay, other questions?
So is the population in these ultra diffuse galaxies the same ratio as big galaxies, or are they newer stars, older stars?
Yeah, so welcome to my world. So the question is, what are the stars in these ultra diffuse galaxies like? So this is what we're currently working on with Keck and with Hubble. So the answer to your question is, I don't know, but if I get my HST time, I'll be able to tell you. So this is actually incredibly hard, okay, because they're so diffuse, very difficult to follow up from ground-based telescopes. And it's so new, we haven't had time to basically process through all of this stuff with Hubble. So the first Hubble observations of ultra-diffuse galaxies are just coming in now. So what I showed you, the kind of thing I might have to censor, okay, that's only like 2 months old. So and it doesn't have enough signal to know to answer your question. So stand by. Okay, I'm sure they're going to kick me out of here. 2 more questions, or am I done? One more. Okay, I can get 1 more question. So what happened? I haven't done back there. So let's go back there.
Your diagram had cubes on the left there. You talked about flow of gas. What is the current understanding of that mechanics and physics of that?
Oh, the physics of the gas in the cube. Yeah. Okay. So I think they're going to shoot me unless I leave. So I'm just going to use your imagination. You know the cube with the gas on the far right? So the question is, what is the physics of that? So the physics of that is something called the warm-hot intergalactic medium. So it turns out that most of the baryons, most of the regular material in this room, the stuff I'm standing on, the hydrogen and the helium, is not in stars. Okay, it's in the phase shown out in that diagram, the warm-hot intergalactic medium. So that's where most stuff is. So it's hot, its temperature is between 10,000 and 1,000,000 degrees, and it's incredibly diffuse. So very, it's kind of like cirrus clouds. So that's why it's been so hard to find. Okay, it's out there, and if you add it all up, its abundance is greater than that of all the stars in the universe. But since it's moving so fast because it's so hot and it's so diffuse, nobody's been able to directly see it. So if we were able to directly image the cosmic web by looking at the warm-hot intergalactic medium, we would be, for the first time, be able to image most of the baryons in the universe and the largest collapsed structure in the universe with freaking telephoto lenses. So how crazy is that project? Okay, I better go. Thank you very much. Thank you very much.
We can take a picture of it too.
Look, Mommy, we take a picture of the moon. Look, Dad, there's the moon.
Take a closer look.
Awesome.
We can take a picture of it too.
Look, Mommy, we take a picture of the moon.
Ladies and gentlemen, please welcome Mr. Joe Rayo.
Sorry, Joe was here a little earlier, but welcome back, folks, to NEAF. Our next speaker is a very dynamic person. We're very fortunate to have him there. I have to say we have a great audience, a great crowd here today. From Orbital ATK, we have the Vice President and General Manager for Operations. We've been involved in several programs at Orbital ATK, the Cygnus Resupply and the Antares program. He's been awarded the Exceptional Public Service Medal from NASA. A local person from Rutgers University now working at Orbital ATK. Please give a warm welcome to NEAF 2017, Mr. Frank DeMoro.
Good afternoon. How's everybody doing today? Good. Excellent. Love to see the big crowd. So I had about 5 minutes in the exhibit hall this morning before I came to get prepared for my talk, and I cannot wait to go back. I can't promise my wife I won't be bringing home a new telescope. Pretty impressive there. That video you just saw was actually really reminded me of my first introduction to astronomy. When I was, so I grew up 21 miles from here in Maywood, New Jersey, in Bergen County. I am a child of New Jersey public schools, and as Vinny mentioned, I'm a proud graduate of Rutgers University. Received my degree in mechanical and aerospace engineering. And I have been in the space business ever since I graduated in 1980-something. That's not important. But my first introduction to astronomy was back in 7th grade. Mrs. Williams, our science teacher, Pirates reviews. And as that video showed, the first real celestial body I observed with was the moon. And anybody who has done anything in astronomy can attest that the moon is an absolutely fantastic celestial body to observe with any sort of magnification device, binoculars, whatever. And so I always tell people who are just starting to get into astronomy, that's the first thing they should look at. And from there, that following Christmas, I got a Sears 3-inch Newtonian reflector telescope made of cardboard and plastic. And in that same house where I grew up in Maywood, I observed for the first time, after figuring out how to use it and reading all the astronomy books, Jupiter. And that was magnificent, but what was even more magnificent was the night I could, on a very clear night, which was a little odd for that part of Bergen County because of the light pollution, but I was able to actually see the tiniest dots of light in the moons of Jupiter, and that was it. I eventually graduated, so to speak, to a 4.5-inch Newtonian reflector telescope, which is what I have now, but I'm going to be looking later what I might be able to take home. So I'm going to talk today about the Cygnus program and the commercial resupply services program that we do at Orbital ATK. We are one of 2 American companies right now that are bringing cargo to the International Space Station for NASA. There will be a 3rd participant. Sierra Nevada joined us when they became a participant as part of the follow-on CRS-2 contract. CRS is Commercial Resupply Services. SpaceX is the other company that delivers cargo like Orbital ATK does. I'm going to talk a little bit about the development of Cygnus and about the Antares rocket, and also about the launch pad from Wallops Island, and just give you a little bit of sense of what it was like being part of that. For the past year, I've been the general manager of the Advanced Programs Division within our Space Systems Group, but for 6 years prior to that, I managed this program, the Cargo Resupply Program, and the Cygnus Satellite Program. So it's a real source of pride for me to be part of human exploration, human spaceflight, and things like that. So the first thing I'm going to do is talk through a little bit about the company. Let's see.
You got to yell for it.
Okay, if we can, there we go. If we go to the next slide, you can see that Orbital Sciences Corporation was an entity prior to 2 years ago that merged with Alliant Tech Systems, ATK, 2 companies that have been in the aerospace business for many years. So we formed Orbital ATK. We are about 12,000 employees around the country. I think we're in 17 states right now. And it is a company devoted to aerospace and defense businesses. So what you can see behind me here is a bit of a description of what we do. So we have 3 main business areas. We have the Flight Systems Group, which does launch vehicles, and I'll show you a little bit more about that. We have a Defense Group, which primarily supports the Department of Defense, and then we have my group, the Space Systems Group. So we have been building satellites as part of Orbital ATK and all the predecessor companies for many years now. You can see over 165 delivered spacecraft of various sizes. We have 95 additional ones in production across the country. My group, the Advanced Programs Division, is where we house our human spaceflight group, the Cygnus vehicle, but we also do space logistics, where we do life extension of geosynchronous spacecraft, which is part of our roadmap to eventually putting robotics in space for refueling, satellite repair, satellite observation, and eventually being able to transfer spacecraft around Earth orbit using sort of like a space tug. So this is just a summary of some of our customers. You can see on the upper left there, NASA, one of our biggest customers. Of course, they're the customer for the Commercial Resupply Services Program. But we have customers around the world. We have universities, we have governments, we have private companies around the world. We do all sorts of types of spacecraft. And you can see here, this is the Flight Systems Group, and some of the products they have. One of the more notable ones right now is we are building the solid rocket motors that are going to be part of the Space Launch System, SLS. That is done at our facility in Utah, and those solid rocket motors are actually derived from the motors we built for the space shuttle many years ago. If you look in the upper left, you can see the rocket taking off there. That's the Pegasus rocket. That's an air-launched rocket that was dropped first from a B-52, and then eventually we modified it to drop to from our own L-1011. It was the first completely commercially developed rocket. Have launched and continue to launch many spacecraft for NASA. It is a small launch vehicle, but it's perfect for small Earth-observing spacecraft, as well as other spacecraft that observe other galaxies in the solar system. The medium-class launch vehicles you see next to the right is really the Antares rocket, which we developed initially to become a medium lift vehicle, which eventually became the launch vehicle for Cygnus and for the CRS program. We are actually starting to embark in even bigger launch vehicles. We just announced it last week at the National Space Symposium in Colorado Springs, our development of our next generation launcher, which is a launch vehicle family, which is starting to grow in size. And we also build some composite structures for both the military but also commercial use. In our space systems group, this is the best group. I'm not really biased there, but that's just a fact. So we build all sorts of spacecraft. So in the upper left, you can see commercial spacecraft. So anyone who gets DirecTV or Dish Network, anyone who has tape cable television, most of those satellite signals go over satellite, and we have built many commercial communication spacecraft for customers around the world as well as in the United States. And I was part of that group for several years before I went into the Cygnus program, and that's the kind of spacecraft that it's out in geosynchronous orbit, and it's life limited by fuel primarily. Typically, the technology doesn't get old, and the hardware lasts a lot longer than it's designed for, but it runs out of fuel because it has to be station kept extremely precisely. So there's another vehicle we're starting to build on the bottom left, which is the mission extension vehicle. And it's the first phase of our space logistics and satellite servicing roadmap, where we're going to fly those spacecraft out into the geo belt. And the customers that are out there that have perfectly working satellites that are about out of fuel, where they would normally have to push them out into the graveyard orbit and launch a whole new spacecraft, we can rendezvous with that spacecraft, dock with the back of the spacecraft, and become sort of a jetpack and keep that spacecraft alive. So now that operator can continue to use that spacecraft and not have to get rid of it and launch a new one. So that's called the mission extension vehicle, and as I mentioned, that's part of a roadmap for all sorts of satellite servicing programs that we plan to embark on. We have built a lot of Earth observing spacecraft, space observing spacecraft, like the Gallup spacecraft. Landsat 9 is a program we're building right now, follow on to other Landsat spacecraft. We built the Orbcomm constellation for low data rate communications that is still in use today, where companies like Caterpillar can put a transmitter receiver on their equipment, which is extremely expensive all around the world, and they can track where that equipment is at any time, day or night, and find out how it's operating. They can collect all sorts of telemetry. Over to the far right on the upper slide, that's the GSAP spacecraft. That is a satellite observing spacecraft we build for the government. We just launched a couple more not that long ago, and that's been it's a small geo spacecraft, but very successful. You can see the picture there of the Hubble Space Telescope. We obviously didn't build the Hubble Space Telescope. What we have done, though, over the years is played a major role in the servicing of the Hubble Space Telescope. Both the legacy orbital company and the legacy ATK company did all sorts of logistics work. We built the tools, many of the tools that we use to swap out the electronics and the optics as part of the Hubble repair missions. And so we're really proud to have been part of that, which the Hubble Space Telescope, anyone would realize, is just a tremendous observatory. We're all excited about James Webb getting launched next year, but I think we'll all have a special place in our hearts for the Hubble mission. On the bottom right, we launch a lot of balloon missions now for NASA. We have a team out in New Zealand waiting for the winds to die down to launch another balloon as soon as they can for a high altitude observation. And then you can see over here, We build a lot of component solar arrays, tank structures for spacecraft and otherwise. The pride of the fleet is this vehicle up here. That's the Cygnus cargo resupply vehicle, and what we'll spend most of our time talking about today. So a little bit about commercial resupply services. So as good scientists and engineers, we'll break down the problem. So International Space Station, pretty big. You can see it's slightly bigger than a football field when you factor in the solar arrays and thermal radiators and things like that. This was especially important now this year with the Super Bowl being in Houston. Everyone wanted to talk about this International Space Station in relation to the size of a football field, and there you go. So even though weight doesn't matter too much, but it is 1 million pounds of mass that has to get moved around. It's in a 400-kilometer-ish orbit, which means there's a reasonable amount of drag from the atmosphere, so it needs to be reboosted. And so if you think about the problem of how to keep a space station flying, I won't get into how it was built. That was quite a feat in and of itself. But if you think of the problem of how you need to keep it flying and how you need to support its use for what it's meant to be, which is a national laboratory, and to conduct all sorts of scientific experimentation, you figure out, okay, what do we need to do to keep this thing flying? There are over 100 systems and payload racks on the International Space Station. It has about 1 acre of solar arrays, which are still operating extremely well. The batteries on the space station were just swapped out as part of the Jackson mission. They launched their HTV resupply mission. They did a battery swap out, so it's nice and healthy. But you also have to think of it in terms of obviously the humans on board. So the internals of the space station are roughly the same as about the size and volume of a 5-bedroom house. And you've got 6 people living there, living and working and doing what they do. And so we need to get them food, we need to get them clothing, we need to get them water. Even though they do recycle things on the station for water, they do need to supplement the water. They need supplies like laptops and printers and printer paper, which is quite very heavy to put in the cargo module, but they need that. They need medical supplies just in case. And they need the scientific experiments to be able to get out of the International Space Station when it's intended to. And so that's where we come in. So then the job is put to us and other companies to figure out how we're going to get those supplies up there. The number one priority for any vehicle going to the International Space Station is safety. It is intolerable for any vehicle to cause damage to the space station or even worse, and so that's the number one. Number 2 is mission success. You absolutely need to get there. They need the food, they need the supplies. They obviously keep enough stores on board in case something happens, and I'm going to talk about that in a little bit. But safety and then mission success. Everything after that is really up to us to figure out how it's going to get there. So what did this mean? So NASA embarked on going about cargo resupply in a different way than they may have in the past. In the past, they might have done everything on their own, built a spacecraft. They would own the spacecraft, that type of thing, and have sort of a larger approach to things, the way NASA would normally do things. Well, they changed their ways on this approach. They wanted it to be commercial, and they wanted it to be service-oriented. And what that means is that NASA does not own the Cygnus spacecraft. Orbital ATK does. They don't own the Dragon spacecraft. SpaceX does. What they do is they pay us to perform a service and bring that cargo up, and we'll get paid based on how well we perform that service. And what that also meant is a different way of doing things in which NASA was investing in companies, not just paying the companies. If you look at the pie chart, if you look on the left there, we have 3 components of how we're going to get the cargo to the space station. You've got Antares, the rocket. You've got to launch it from somewhere, Wallops Island, and then you need to have the spacecraft to bring the cargo up, and that's a Cygnus spacecraft. If you look at the pie chart on the right, you can see where the investment came from. Orbital ATK invested more than half the money than the government did. And we knew that going in. That was a commercial venture we wanted to be involved in, and so we invested that much money You can see NASA invested that much money. And Mars, which stands for the Mid-Atlantic Regional Spaceport, which is part of the Virginia Spaceflight Authority, Commercial Spaceflight Authority. Everybody put in a certain amount of money to create this system. So this is what we would call a public-private partnership, and in a way that supports government use. So a little bit of background how they furthered that. In 2006, NASA put out a competition to get companies to win the privilege of investing in this system. And we didn't win first time around. SpaceX won, and a company called Rocket Plane Kistler won. But Rocket Plane Kistler had some troubles along the way, and so eventually NASA realized they might not make it. And so they canceled the contract, recompeted that second contract, and we won that contract. And so in February 2008, we embarked on the development of the Cygnus spacecraft. I should point out the Antares launch vehicle was already in Orbital ATK's plans as a medium-class launch vehicle. So Antares had started. Cygnus did not. Also interestingly, is only 10 months after we started the development of Cygnus, we also won the operational contract for Commercial Resupply Services, CRS contract. And so we initially won 8 missions. We're now up to 11 missions on the contract. And so that's how Orbital ATK got into the human spaceflight business and cargo resupply. Just a couple of pictures to show you the Wallops Flight Facility launch pad. The larger picture here, you can see the water tower. I'm told that's the tallest water tower east of the Mississippi. I'll believe it. You can see this was actually a test article of Antares before we actually started launching the rocket on the actual pad. There's the flame trench that the first stage fires. All the flames come out and go towards the ocean. And then over here, you've got the liquid fuel farm. So Antares, which I'll show you in a minute, is a liquid first stage rocket and a solid upper stage. So we had to build the infrastructure to be able to load liquid oxygen and kerosene into the rocket. We also reused some existing NASA facilities. H100 is where we process the spacecraft and load the cargo. V55 is where we fuel the spacecraft with the hydrazine and oxidizer. And then the horizontal integration facility is where the Antares vehicle is integrated and tested, and where Cygnus is eventually mated. And then it will roll out, when it's all done, out these doors, come down this road, up the concrete pad horizontally, and then it will be transported to the vertical position for launch. The Antares launch vehicle itself, as I mentioned, it is a hybrid liquid and solid rocket vehicle. The first stage is liquid. Then once the first stage is depleted, then it will separate, and then we actually light off the solid upper stage up here. So here you've got liquid oxygen tank. You've got the RP1, which is really kerosene. It stands for Rocket Propellant 1. Those are loaded into the vehicle the day of launch, a few hours before launch. And when the rocket takes off, it puts off about, in its current configuration, about 900,000 pounds of thrust. When it's further optimized for CRS-2, then it'll put off over 1 million pounds of thrust. So it's a pretty powerful rocket. You can see the payload up here inside the fairing, Cygnus spacecraft, of course, and then a solid motor here, which is actually built by our sister division out in Utah, the Castor 30 XL. This rocket, the Antares rocket, can put a fully loaded Cygnus spacecraft into an orbit about 190 kilometers in altitude. And that's not only by the rocket capability, but that's by design, and we'll talk about that in a minute. We've had several variants of the Antares rocket. The biggest change of note that I should mention are the engines. We originally started this program with engines that were referred to as AJ-26 engines, which were actually older Russian engines. Originally they were NK-33s. And as some of you might know, we had a launch failure in October of 2014. And we lost the mission. And so as part of the recovery plan, we swapped out the engines for an RD-181 engine from Energomash in Russia. So that's the rocket we fly right now. The combination of those new Russian engines and a bigger solid motor gave Antares the lift capability of the bigger Cygnus vehicle, and we'll talk about that as well. So we've got a rocket, we've got a launch pad, we've designed the spacecraft, we've filled it with cargo, whatever NASA wants us to put in there. Now we've got to get it to the International Space Station. So we launch, we get dropped off about 190, 200 kilometers, depending on the launch vehicle. We like that altitude of the initial orbit because we have to, at that point, begin the process of phasing ourselves to not only raise the altitude to the 400 kilometers where the space station is, but we have to get to that point at the same point in space. And so if we're at 200 kilometers when the space station's at 400 kilometers, we catch up very quickly, or relatively quickly. If we actually launched into a much higher orbit, if we launched into a 350 kilometer orbit, and we weren't very close to the space station, it would take us a long time to catch up. While we have scientific payloads and time-sensitive payloads on the spacecraft, we don't want to take that much time. So we launch into a lower orbit, we catch up more quickly, and over time we continue to raise the orbit. It typically takes us anywhere from a day and a half to 3 days to close that gap, not only on an angular basis, but also from an altitude basis. We get about 1,000 kilometers below the space station, so now it's right below us. We're 1,000 meters below the space station. And now we start making our way up. That's called the R bar, R for radius, towards the radius of the Earth. And we start making our way up the R bar slowly and very safely. We have a suite of sensors on board the spacecraft which detect where they are in relation to the spacecraft at all time, using a combination of laser scanners, which work with reflectors on the space station. We have another sensor which actually knows the shape of the space station, and it measures how big it is, and we know how close we are based on that. And then we use the GPS system. We actually do relative GPS. We compare the GPS solution that we get on the spacecraft with the GPS solution that the ISS has, and we know about how far we are away. So we use those three things to make our way slowly up towards the space station. We get to about 250 meters below, and we stop. Then we assess how's the spacecraft's health, how's the ISS health, is everybody happy? We'll continue to move from that point to 30 meters below and stop again. And once everybody's happy, we make our final approach to the space station, where we get to about 10 meters below, about 30 feet. The robotic arm comes out, the crew on board will grapple us in the back of the spacecraft and eventually move us and connect us to the space station. We are up there for any period of time. It can range from a couple of weeks to a few months. This next mission we're about to fly, we expect to be on the station about 90 days. When we're done, the arm will grapple us, pull us away from the space station, let us go, and we'll fly away. And we will either directly re-enter over the Pacific Ocean, or we'll go off and do some more scientific experiments, and I'll talk about that in a minute. So that's essentially how Cygnus gets from the rocket to the space station and eventually ends the mission. So the pictures here, I'll start on the right. So we designed Cygnus just because that's the way we do things, to be compatible with multiple launch vehicles. But we never had intended to not fly on Antares, but after Antares failed, we had to get flying again. And the flexibility of the spacecraft being able to fly on multiple launch vehicles meant we could quickly integrate ourselves with an Atlas V rocket from the United Launch Alliance and keep the cargo flowing while the Antares team figured out what went wrong and how to fix it. So we actually have launched twice so far on Atlas. Then we launched on Antares. This next mission will launch on Atlas again. And that was an agreement we worked out with NASA to get them a little bit more cargo. Atlas V does have a higher lift capability than Antares, and NASA needed the cargo. So that's why you see we have two launch vehicles there, because we can actually fly on either one. But over to the right, this is the Cygnus. It has two main parts. It has the cargo module. And this is back to, okay, how do we solve the problem? Let's break the spacecraft down a little bit. So we need a place to put the cargo. That's the cargo module. We buy that from a company called Thales Alenia Space in Italy. Why? Because they have built most of the modules that are on the space station. They know space. They know International Space Station interfaces, and so that was the lowest risk, best approach we could pick for NASA. Then we have the service module. That's what we build at Orbital ATK in our facility in Dulles, Virginia, which integrates components from all around the country and, quite frankly, all around the world. The solar arrays you see here, these circular solar arrays that unfurl like a fan, those are built by our facility in Goleta, California. This structure, the service module structure, is built by our facility in San Diego, California, and the tanks that you can't see that are inside that hold the propellant are built by our facility in Commerce, California. A lot of the sensors are built, we fly what's called a LiDAR, a laser range system from Germany. We also fly one from Canada. We fly a star tracker from Sourdon in France. We have GPS antennas from the United States. Orbital ATK builds a lot of the avionics ourselves. So within that service module, even though we have all the cargoes in here, we needed something to do the flying. We needed something to generate the power, to store the power when we don't have energy on the solar arrays. The propulsion systems, the computing systems that take all those sensor data, figuring out where you are in space, and telling the propulsion system which thrusters to fire and for how long to guide the spacecraft exactly where we want it to go. And that's all done on the spacecraft without any human intervention. And it has to be that way because when you're close to the spacecraft, close to the space station, the only people we want talking directly to the spacecraft to command it are the astronauts. Why? Because if they see something wrong, they need the ability to hit a button and have us fly away. But we don't want to be we're not in the control center with a joystick flying Cygnus. It's doing it all on its own. Around the spacecraft, we have 32 7-pound thrusters that do the attitude control of the spacecraft. We also have one additional big thruster, which is hard to see here, a very high thrust thruster that we use to raise the orbit because it's more efficient. But when we want smaller fine control, we use the 32 thrusters around the spacecraft. It has a lot of redundancy, meaning that we can accommodate all sorts of failures in the system and still have both an operational, but most importantly, a safe spacecraft. So we have 4 computers on the spacecraft, all operating independently. They're all taking the data from the sensors, crunching the numbers, and this computer says, I want thrusters 5, 7, and 9 to thrust for 1 second. Well, it compares that solution to all the other 4 computers, and they should all agree. They're all getting the same data. The spacecraft hasn't changed. And what we do that for is so that if one computer says, I want to fire thruster 11 for 6 seconds, the other guys vote them out. Sort of like Survivor on a spacecraft. But we have multiple strings on the spacecraft so that if we have multiple failures, we can still get away from the space station safely. So that's the space vehicle. We can carry about up to 3,500, or maybe even a little bit more, kilograms of cargo in that cargo module. It's fully human rated, which means it has the safety systems embedded in it so that it can be around people in space and be safe. Just a couple of more things about it. So we actually have flown 2 different versions of Cygnus. The standard version, which is a smaller version on the left, and then the enhanced version. This is a rendering that you saw a picture before of the actual spacecraft. We originally planned this evolution of the cargo module, but what we hadn't originally planned was the evolution of some other systems on the spacecraft, where after we flew it the first couple of times, we realized there was some efficiencies we could take in the system. And so you can see the solar arrays are different. We changed out some sensors on the service module. We also figured out a better way of packing the cargo. So the original plan is that this would hold about 2,000 kilograms, and the bigger module would hold about 2,700 kilograms. But after working with NASA and the Italians who built the cargo module, we figured out how to more efficiently pack it. And so we got a 30% or so increase in packing efficiency. And now we can fly 3,500 kilograms. On the next contract, we're actually increasing that a little bit more, where we can pack almost 3,800 kilograms. So we're slowly making improvements and doing that because that's our job, to make the system as efficient and effective as possible. The solar arrays generate about 3.5 kilowatts of power. That's plenty for the Cygnus spacecraft. We carry about 900, or maybe a little bit more, 950 kilograms of fuel. So what that enables us to do is do all the orbit raising. It enables us to rendezvous with the space station, and if something were to go wrong, we could actually fly away, and then come back. We have enough fuel to do that multiple times, just in case something happens. Why would we fly away? Maybe we had a failure, as I just described, and we lost 2 strings of our system, and we're not safe, and we need to reintegrate those systems into the spacecraft. Maybe we had a late sensor failure. Maybe the crew, which is watching Cygnus approach the space station, isn't comfortable with where it is. Maybe it's outside the little window box that they're looking at, and so they want to send it away. Well, we don't want just one shot at it. We want multiple shots, and so we have enough fuel to be able to do that. Just a little bit about the cargo module. You can see the volume. So the bigger module is about 26 cubic meters, relatively large when you go stand inside it, as I've had the privilege to do. It is big, and we're actually using that for hopefully the future of human exploration. But when you put all the things in it to lock down the cargo, and we have a fan to circulate air inside the module. When it's on the space station, we can actually carry powered payloads. So we do run power to that module. We have biological experiments on this next mission going up, so we have to keep those powered so they stay cool and at the right temperatures. And as I mentioned, this comes from Italy, and we actually, the cargo module and the spacecraft service module never see each other until we actually get to the launch site. And that's when we make them together, and you'll see that in just a little bit. So I do have some pictures to share. This is Cygnus made it to Antares. This was our recent mission in October of 2005. We do it horizontally. Atlas does it vertically. Doesn't matter. We can do it either way. And you can see some of the folks there. This is right before the fairing was installed over the spacecraft and before we got rolled out to the launch pad. It was a beautiful night launch. The OA-5 was our return to flight mission on Antares after the failure in 2014. This was their return to flight mission. The engines performed flawlessly. We actually got better performance than we expected, and the solid motor, which was its first flight, also performed extremely well, and the mission went very well. I've got a little movie to show you in a minute. But nighttime launch out of the Wallops Flight Facility in Virginia is absolutely stunning. That's not the only thing we launch out of there. We also launched some other smaller solid rockets. Both go to orbit, but also suborbital rockets for NASA. This is a picture of OA-5 as it's rendezvousing with the space station. So I mentioned it takes about a day and a half to 3 days. It depends on where the space station is when we launch. I think this took about 2.5 days. We always rendezvous with the space station in the wee hours of the morning in Virginia, which is where we're based. Because that's when the astronauts are up. They go on UTC or Greenwich Mean Time. So we're there in the wee hours of the morning. But there's nothing better than to be in the control center and watch your spacecraft. First, you start to see the lights, and then you start to see the sun glint off the solar rays and off the cargo module, and then you can actually see the spacecraft. Now, I've had the privilege of launching many spacecraft in my career. The ability to see the spacecraft again after it launched is very, very special. You never see that. You've always gone off the rocket, and you know they're there through the telemetry you get. But here you can actually see the spacecraft. And I can promise you, in every case, it's looked just like when we launched it. Nobody messed with it once it got away. So we get, you can see it coming up, and everybody's getting excited, but we have a full team of engineers on console at our Mission Control Center, also at our Dulles facility, and we're monitoring everything. All the telemetry, temperatures, attitude control, are there any failures? If they are, what are we going to do about it? At the same time, we're sending all the exact same data to NASA, and they're looking at all the data. And so we have this check and balance of Orbital ATK team looking at it, NASA's looking at it, and that's what enables them to give us the go or no-go, should that be the case, once we get close to the space station. So it's very exciting. You can see in the lower picture, the robotic arm ready to capture us. We have cameras on the spacecraft, so we can see what's going on. These pictures are taken, they're called rocket cam. One's from what we call the far field, and then the lower right you can see as we're approaching the space stations, we're coming up from below. We don't get these pictures real time. We're actually recording all of that. We use it afterwards for situational awareness. Should there be a problem, we want the video, but so far we've just used them for a lot of data gathering and actually a lot of fun. It's just very cool. Here's just a few more pictures as we're grappled. So you can see in the upper left, the spacecraft is grappled at the back of the vehicle. On the upper right, probably my favorite picture ever of Cygnus, given the darkness of space behind it and the solar cells and the orange of the material and the solar rays. We're grappled, and then on the bottom right center, you can see where we're attached to the space station. It's called being berthed, but you can see the Soyuz vehicles over to the right. At any one time, they've had many vehicles attached to the space station. It was a lot of fun. I believe it was OA4. We had Cygnus, we had a Dragon from SpaceX, we had multiple Soyuz, we had a Progress, and so it was a busy time. Interestingly, traffic management, which is what NASA calls the process of managing which vehicles come and go at what point, is actually quite complicated. There are stay-out zones on the calendar for when a Soyuz is coming up or going down, or a Cygnus is going up or coming down. And I'm part of that process, or I have been, because it's actually quite complicated. And it all is based on not only the vehicles coming and going, but when they need the cargo and how much cargo they need, and things like that. So it's actually fun to take part in that. And one last, maybe this is my favorite picture. I don't know. Maybe my second favorite picture. I put this in here because has anyone ever heard of the website Gizmodo? Gizmodo named Cygnus the cutest of the cargo vehicles. This is a source of great pride in orbital ATK. But we also think it's very well deserved. I mean, look at that. So anyway. And then with Cygnus upon departure, so we get let go, we fly away, and then we start to do some cool things. So I'm going to show you, we have monitored the reentry. We have a destructive reentry. We do not return cargo to the Earth like SpaceX does. What that does is enable us to bring up a lot more pressurized cargo. So that's our job. NASA gave us that job. They gave different jobs to SpaceX. What do we carry up there? A lot of scientific experiments. There was a vaccine experiment. This is Rick Mastracchio, astronaut. He was on our Orb-1 mission, grappled us. He's doing an experiment there. Over here, there's this sphere slosh experiment. They put liquid in them and they shoot them around the space station. Well, maybe that's a little strong, but they fly around the space station in zero gravity and they test the effects of slosh on propulsion and things like that. And then one of our proud moments here are the ants. We flew ants on our Orb-1 mission. The Orb-1 mission was supposed to fly in December of 2013. There was a problem on the space station. They delayed us to January. Well, we had already loaded the ants on the vehicle. So we had to roll the spacecraft back to the horizontal integration facility, take the ants off, fly them, this is no joke, fly them to Colorado. They put more food in. They flew them back to Washington. We put them back in the vehicle, and they were the happiest ants that ever flew in space. Interestingly, they needed some ants on the ground to help with the controls, and they looked around Wallops. Again, this is true, and they found ants of the same species, and so they gathered up some ants and they put them in a jar, and they became the ground control ants. So the ants are stars of our history of delivering cargo. We're really proud of that. Sapphire is an experiment that we have been flying. This will be the third time we fly it on this next mission. This is by NASA Glenn. So imagine you're on a trip to Mars, and a fire breaks out in the spacecraft. Well, you can't just abandon the spacecraft like you could do in the space station. Knowing how fire propagates and how flame propagates and how combustion works in microgravity is extremely important. So NASA Glenn devised the Sapphire experiment. We load it as cargo, but it stays in the cargo module after everything else is taken away and all the trash is put in. And then we fly away, and then we actually fire off Sapphire. And there's a fire in the cargo module. And we know it's because the smoke alarms are going off and the temperatures are going up, and it's very cool. It's controlled, but it's very smoky and all sorts of other good stuff. So they burn the stuff, the material, whatever they're testing, and they take all sorts of measurements, and then we downlink the data, and then they take that to figure out how fire is going to propagate in microgravity. And so we've flown 2 of them, and in each case they've learned enough from each experiment to make the next experiment even better. So we're proud to be part of that. We're flying it for a 3rd time on our mission, which is going to launch in the next couple of weeks. We also deploy little CubeSats right off of the Cygnus spacecraft. For the first few missions, we delivered it to the space station, and they would deploy them. Well, now, for the past couple of missions, we've actually launched CubeSats right off of Cygnus. These are satellites about this big, and maybe 3 inches square, and they're of various sizes. They perform various tasks. And you'll see in the movie that I'm going to show in a minute, the satellites flying out of their deployer. You can see the picture on the lower right. That's done for NASA via a company called NanoRex. So I'm going to talk over this video quickly. This is the service module at our facility in Dulles, getting prepped for shipment to Wallops. We ship it by truck. This is showing the on-ground deployment test of one of our UltraFlex solar arrays. We have to have special equipment to do that on the ground since there's a lot of gravity. The gravity makes that deployment very, very difficult. Here's a cargo module arriving at the launch site from Italy that gets shipped over by boat. Eventually it's loaded with cargo and then mated to the service module, which is happening right here, to create the Cygnus vehicle. And there's a lot of bolts and there's some propulsion lines that we have to hook up, and then it's put into a shipping container and it's trucked from the H100 building on Wallops Island, on the mainland, over to Wallops Island itself, over to V55, where we'll actually fuel the spacecraft with its hydrazine and its oxidizer. Here you can see some cargo getting loaded. We do cargo loading in 3 phases. The initial load is about 75% of it. The late load, we call it, is about 20%, and then the final load is about 5%. Here we're in the horizontal integration facility. All the cargo has been loaded. The spacecraft has been mated to the rocket, and now the fairing is put over the spacecraft. And here we're rolling out from the HIF, as we call it, horizontal integration facility, a mile down the road, up the ramp. And the rocket eventually gets transitioned to vertical, getting ready for launch. You can see the water tower in the background, which is part of the deluge system that keeps the pad cool and also lessens the noise. That's the Mission Operations Center in Houston, where they monitor Cygnus. And you'll see here in a second the Antares vehicle take off. It says OA5 mission summary. We actually put a daylight launch in here so you could see the rocket take off. It was from a previous mission, but it's about the same. Looks the same. Let's see. Okay, so the engines ignite and the rocket takes off. Does a little waggle there on purpose to get it away from the transporter erector launcher, which is the thing that it rolls out to the pad on. And you can see on this mission we had cameras on the rocket to be able to show where it's going. Eventually, here in a second, you will see the first stage fly away, and the second stage will ignite, and that stage will take it to its proper orbit, where the spacecraft will be separated and then go on its way. And that's the fairing separation, so the protective covering flies away. The second stage motor ignition. And this will be done in a second, and eventually the spacecraft will separate, and you'll actually see some video of these UltraFlex arrays deploying, because they sort of come out in a fan, like there you go. And that is from the rocket, another rocket cam on the spacecraft. We put those on specifically to monitor this deployment in case there was a problem. We haven't had a problem so far, but it's the pictures are cool. I will tell you, this is sped up video. It actually takes quite a long time, and when you've got your manager breathing down your neck waiting to know the solar array is deployed, it feels like it's forever. So this is a view of what the astronauts see. So if Cygnus were to go outside of that square box, the astronauts could press one button and we would fly away and we would come back. And so here you can see, this is a view from the arm onto the grapple fixture. So they grapple us and you can see them moving us here, and they berth us to the space station, and we become part of the space station. They open a hatch and they'll start taking the cargo out. Now, after all the cargo's out, they start filling it with trash. Why? Because if you lived in a 5-bedroom house with 6 people and nobody took out the garbage, it would get pretty bad. So part of the service we provide is taking away that disposal cargo, and it's very important to NASA. This is some video of the Sapphire experiment burning. You can see the material is on fire, and so that it's taking pictures. Here you can see this NanoRex deployer. There's a CubeSat flying out. Trust me, it's not that close to the solar array. I know everybody's heart stops. And then this, I think OA4, we worked with NASA AIM. We had a chase plane follow the reentry of Cygnus. That is the actual vehicle reentering the atmosphere. I will tell you, in complete honesty, that is the most bittersweet moment of the mission. You have this amazingly fine spacecraft who's done its duty, and there's a great sense of pride for that. But it's burning up in the atmosphere, and so it's something it's quite a moment for the team. We do celebrate the success. It's just it's very special. So just a little bit of statistics, because we all like numbers. We've taken up to the space station so far 13,500 or so kilograms, almost 30,000 pounds of cargo. We're going to fly another 3,400 kilograms on the next mission. So we're doing our part to get that cargo up there. The other data on there is how much cargo we've taken away. It's not as much as we brought. So at some point that math is going to have to get worked out. But because whatever goes up is going to have to come down. And then we've got what our missions are coming up. So we've got OA7, which is just about on the launch pad on April 18th. We expect to launch. Got about 3,400 kilograms. And then this is a notional plan of when NASA will launch these missions. They'll determine when they want them. We'll be ready. But you can see the rest of our missions are on Antares at various times, and we continue to increase how much cargo we're flying on Antares. And then on top of this, we've got 6 missions on our CRS-2 contract to further support the space station through 2024 and hopefully beyond. So I just want to talk briefly, and then I have a video on where Orbital ATK wants to go from here. We are extremely proud, as I mentioned before, to be part of the Human Spaceflight Program and being able to support astronauts and the scientific research they're doing in space. But we want to do more. And we want to start supporting NASA on their trek towards Mars. And the first step towards Mars, which is cislunar space. We have worked a program called Next Step Phase 1, which is complete, which is conceptual designs of how you would create a habitat in cislunar space. We are awaiting the turn on of Next Step Phase 2, which takes you from conceptual design to ground demonstrations, and hopefully eventually Next Step Phase 3, where there'll be flight demonstrations of that. We think Cygnus, given its history, given who's built it, given how well it's worked, is a perfect building block to be the building block for cislunar habitat out at the moon and then eventually to Mars. So we've put together a plan which we think over the next less than a decade will have us with Cygnus Space Vehicle and other vehicles like Orion and other participants out into cislunar space doing scientific research and then eventually onto Mars. So let me just show you that here. Highlighting the fact that today we're supporting human exploration by delivering cargo to the International Space Station, and some of this video are some of the things you've seen before. Cislunar habitat that we think can be based off of the work we've done with Cygnus so far. The idea here is we would launch that off of an SLS. Of course, Orbital ATK is part of the SLS program with the solid motors. But you would launch this habitat out with this heavy lift rocket out towards the moon. And what it will eventually become is a place for the Orion, the astronauts on the Orion capsule to rendezvous and have a place to live and stay and do scientific research for a longer period of time than if you just go out in Orion itself. idea being that once their work is done, they will go back in their Orion capsule. Those astronauts will come home, and then that module will stay out there. Eventually, it'll become a building block of a bigger vehicle, a bigger habitat that's out there that not only are for the astronauts to stay and live, but also do additional scientific research. Places where we can add nodes to it, so you can then attach different devices, whether it's a lunar lander or a scientific research module or things like that. So everything here is lined up with the current plans for exploration with Orion and the work that Lockheed Martin is doing on Orion, the SLS work, of course, that NASA's doing. You can see here where we've now rendezvoused and met up with that initial cislunar habitat, added another module, and so now the crew can do even more work out there. And out in the 2024 timeframe, we just keep adding modules so that as the crews are making their way out to that cislunar space on a regular basis, as we start to really gear up on what we plan to be eventual trip to Mars, you'll end up with this space station around cislunar orbit. And then as we get, a little bit of a decade or so, it's building, you can see a Mars lander potentially attached to it. That's just, of course, a notional concept. The idea is that it gives you the flexibility to do things out beyond low Earth orbit that we're just thinking about now. And this is really what's important for all of us to be involved in human spaceflight. I have been involved in this now for the past 7 or 8 years, and it has been a highlight of my career. It's really up to us to get out there and push NASA, push the government to get moving, to pick the destination and get out there as quickly and as safely as we can. And then eventually the idea is you can build this station up and using all sorts of different new technologies, eventually push that station towards Mars. So I really appreciate your attention. I really love being here. I can't wait to walk more about the exhibit. And thank you very much for your attention. We have a few minutes if there are any questions.
Yeah, you were talking about the space tug, and obviously it's NASA's choice, but how would you characterize the capability of that and then really be something that's going to help us with?
So the question is on the space tug and how I classify the capability. So a couple of things about the space tug itself. I think there are certain new technologies that are in the process of being developed that are important. One of those is extremely efficient propulsion systems like solar electric propulsion. There are smaller scale versions of that we actually fly on our geospacecraft, and other folks do as well. We flew it on the Dawn mission to the asteroid. What we're really looking forward to those are 10 kilowatt systems. We're looking now more towards 50 and 100 kilowatt systems to give the not only the fuel efficiency of high power solar electric propulsion, but also the thrust that you need to push big objects around. And I think we need to start where we're taking something from low Earth orbit up to the geo belt, and then going further, like they were planning on doing with the asteroid rendezvous and retrieval mission, where high power solar electric propulsion was a major part of that. That technology is key for NASA. I think it's key for those of us in the industry that want to play a part of that. I think its capability is yet to be harnessed. So I think we've got a lot of work to do to figure out how big a system can we reasonably fly, how expensive is it, how efficient is it, and how would we couple that with other technologies. So I think the space tug is on a lot of people's roadmaps. It's certainly on ours, and I know from working with NASA on the asteroid mission, it's something that's one of their higher priority technologies. Any other questions?
Outside of the U.S., are there other government commercial ventures such as yours and SpaceX, etc.?
Yeah, so SpaceX is commercial, Sierra Nevada's commercial. They'll be doing cargo resupply in the next contract. Japan does their own cargo resupply with their vehicles. That's more government run. Proton is run out of Russia. The Europeans used to have what was called the automated transfer vehicle. They don't fly that anymore. So in terms of delivering cargo to the ISS, there's, let's just say, 3 commercial companies. They're all U.S. based, and then we've got other governments to do that. In terms of the support for beyond low Earth orbit, I think that's where we're going to also need some more international collaboration, given the cost, and we're starting to see more and more of that as we go. So we've got commercial companies like Jeff Bezos from Amazon has expressed interest. Bigelow has an inflatable module on the space station right now. So the commercial approach that we've used and that SpaceX has used is starting to come more and more in favor. And so I think we'll see more and more of that as we get moving over time. Yes, sir.
Yeah, how many CubeSats can you build up in 6 months?
Okay, so in the deployer that you saw on the spacecraft, we can launch 12 3U size CubeSats. So far, we've only launched 4, but we have the ability to launch 12. There are bigger deployers we could fly. That was a 2x3. We can do a 3x3. But we also carry up all sorts of CubeSats inside the cargo module to get launched out of the space station. I think this mission coming up, we have 30 some odd CubeSats there.
And is there any, problems in regards to problems with the junk?
Yeah, space debris? Yeah. So, interestingly, if you launch a CubeSat from the 400-kilometer space station orbit, the orbit decays relatively rapidly, and it re-enters in several months' time. On the last mission, though, the CubeSat folks really want to go higher because they want a lot more life. We actually flew off the space station. We went up to 500 kilometers, so 100 kilometers above the space station, and deployed that CubeSat and deployed them from there. So they can be in orbit for a couple of years now. But to do that, they had to work through the approvals of NASA, because eventually that CubeSat orbit, it's in the same inclination. So the CubeSat orbit's going to cross the space station orbit. And so they just want to know what's up there, how they can track it. The good news is that over time, because the orbits are separated in altitude, there's a slight precession. So you get to a point where the risk of a collision is extremely small. But they had to do a lot of work to be able to get there.
Are you exploring reusability?
We are not. Certainly not on the rocket side. We know that's a big thing in the news now. SpaceX has done amazing things with reusability. Blue Origin is all about reusable rockets. ULA is talking about that. United Launch Alliance. Where the economics of it, I think, are still to be worked out. Whether or not we eventually put something reusable for like a cargo delivery system, that's up in the air. But right now, we don't have any reusability. So, yeah, I think eventually, because if you don't want to tug around tanks and tanks of hydrazine, you need to move towards the higher efficiency system like solar electric propulsion. Eventually, we think Cygnus can become a cargo vehicle, not only a habitat module, but a cargo vehicle for those systems. And for those systems, for those types of vehicles, we would employ something of a much higher efficiency. And typically, the approach has been a xenon solar electric propulsion system. Yes, sir.
When using the Russian engines, do you have any concerns about continued ability to access those in the political environment?
Well, that's a great question. The question is on the ability to continue to use Russian engines in the current political environment. So far, I think it's fair to say that Russia and American cooperation in the space station has been really untouched by the current political environment. There's still a lot of trading that goes on in terms of we can send them their supplies on our vehicles, and they can bring up supplies for us on their vehicles. So that cooperation is real. I think we buy those engines on a commercial basis as opposed to government to government. Is there a risk that the government of Russia could step in and say no more engines? The obvious answer is that the risk is there. We think it's relatively low, though. We think both Russia and the United States are so invested in getting humans into space that area of cooperation will continue, and that the risk is very low. Well, I think I am out of time. I thank you very much for your attention and for having me here, and it's great to see you. Take care.
Look, Dad, there's the moon.
Let's take a closer look.
Awesome!
We can take a picture of it too.
Look, Mommy, we took a picture of the moon.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
Look, Dad, there's the moon.
Take a closer look.
Awesome!
We can take a picture of it too.
Look, Mommy, we took a picture of the moon.
One small step for man, one giant leap for mankind.
Look, Dad, there's the moon.
Let's take a closer look.
Awesome!
We can take a picture of it too. We can take a picture of it too.
Look, Mommy, we took a picture of the moon.
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, welcome everybody. Welcome again. You folks having a good time in today? Keith? It's good. We have a really great program. We continue today and this afternoon. Our next speakers come to us from the PBS series Stargazers Popularizing Astronomy. These two astronomers, James works at the Kiki Silva Planetarium in Florida, and Dean at the Cincinnati Observatory. Please give a warm and loud welcome to James Albury and Dean Regis. Welcome to NEAF, guys.
Well, good evening, or good afternoon. Good afternoon. Thank you very much for having us here today. My name is Dean Regis. This is James Albury, and we are the co-hosts of the TV show Stargazers. Let's see, out of curiosity, how many of you guys watch us regularly? Uh-oh. All right.
We're in trouble.
I know. All right, we're going to have to do some explaining. That's right. Well, anyway, well, the show that we're on a PBS show called Stargazers. This is broadcast all around the country, and we give 1 minute and 5 minute segments about what's up in the sky. And this is our great graphics behind us. As you can tell, we fly through space on hoverboards. Very exciting stuff. James, we'll let you introduce yourself a little bit and your background with this.
Okay, well, as again, my name is James Albury. I work at the Kika Silva Pla Planetarium. And when I first started working there, the last name Pla was the first 3 letters of the planetarium. I said, was that a typo? But to see the Pla family, they donated money to have the planetarium completed. So it is interesting the planetarium has such an interesting name that rolls trippingly off the tongue. But nevertheless, I started working in the field of astronomy and in planetariums when I was 14 years old down in Miami at the Miami Space Transit Planetarium, because apparently they didn't have child labor laws back in the 80s. But anyway, while I was working there, I had the opportunity of working with Jack Horkheimer, who was the creator and original host for the Star Hustler program. And we're going to talk a little bit about the history of the show as we go. But I really enjoyed not only working in that environment, but also sharing my love of astronomy with all the people who visit. So I said, when I grow up, I think I'm going to go ahead and work in a planetarium. So when I went to the University of Florida, I studied astronomy, and when I graduated, I said, well, there are no astronomy jobs readily available, so I'll go into computer science. So I did that for a while. Then eventually I met my wife, who I was helping with her electronic thesis at the time. And we eventually got married, and then when we were moving from the Jacksonville area back to Gainesville, she said, Gainesville has a planetarium now. And didn't you work in a planetarium when you were in high school and early part of college? I said, yeah, but I don't know. Well, she said, go ahead and look at the job description. So I looked at the job description and said, I can do that. I've done that. I can do that. Oh, well, let me go ahead and apply. And I applied. They liked me, and now I've been the director there for almost 8 years now. I've produced several planetarium shows, and now I get to co-host the show that I used to watch when I was a little kid. Now my son watches me on the show. So it's kind of trippy now that you realize that a lot of things come full circle as they do.
And when in there was your bodybuilding career?
Oh, that was I was competing in bodybuilding right when I met my wife, which was interesting. I met her 2 weeks before I competed in the Gainesville bodybuilding competition. I won the competition. I invited her to the competition and I ended up winning. So I was like, well, that's good fortune.
Yeah, before I met James, when we were about to be named co-host, before I met him, my colleague was like, have you Googled James Albury? And I did, and the first picture was him like, I mean, this is like, do it.
Well, I don't want to mess up.
Yeah, you don't want to break the suit, but I mean, it's if you want to have fun, Google James Albury bodybuilding. You'll be, it's impressive. It's impressive. Sure. And so this is your planetarium, and a lot of people wonder when you say you're at Santa Fe College, you're not in Santa Fe, New Mexico.
Right, yeah, we often get that because there's a river near Alachua County in Florida. It's called the Santa Fe River. So when Santa Fe College Santa Fe Community College was started 50 years ago, they call it Santa Fe Community College, but there's also a Santa Fe Community College in New Mexico. So that produced a problem when we had our planetarium, because I occasionally, to this day, get phone calls from people trying to make reservations for the Santa Fe College Planetarium, Santa Fe Community College Planetarium, and they're calling from New Mexico or places nearby and say, well, that's a 2,000-mile commute. That's a long way to go. Yeah, that's why, unfortunately, when John Pla and his wife Amy Hard donated money to the planetarium, we have the other name, Kika Silva Pla, rather than the Santa Fe College Planetarium. So, yeah.
Well, and my name is Dean Rigas. I'm the astronomer at the Cincinnati Observatory, and I've been there since 2000. Just last year, I wrote a book called Facts from Space. It has about 850 facts about everything in outer space, stars, planets, all sorts of stuff. It's a good starter, a good reader that you can pick up anywhere. Some of our local radio personalities said, this is the perfect toilet book. This is perfect. You're sitting on the toilet. You know, I don't go with that. Anyway, we'll have, James and I will be out at the side, and I'll have these for sale. I'll be happy to sign some of these, and James has some postcards to sign with his headshot, so you can get, not the bodybuilding one. So that's us. Anyway, and then I also work at the Cincinnati Observatory. This is a historic observatory in Cincinnati, Ohio. We have 2 telescopes. Our new telescope is a 16-inch Alvin Clark and Sons from 1904. That's our new one. The old one is our pride and joy, one of the oldest telescopes in the world. Made in 1843 in Munich, Germany, saw first light 1845. So it's going to have its 172nd birthday on Friday, so a week next Friday. So definitely love to have you guys come and visit us either in Gainesville or in Cincinnati. So the show, how the show got started, well, this was something that goes back a long way to when Jack Horkheimer started it. And so Jack Horkheimer, there he is. Jack Horkheimer was the one who started the show. It was originally called Star Hustler. And so maybe you recognize that name. Now, why would you have to change the name from Star Hustler to something? Anybody? I don't know. That's another thing to Google. Other than James Bodybuilding, look up. Anyway,
one of the challenges, would I may tell the story?
Yeah, go ahead.
One of the challenges as the Star Hustler started back in 1976, and eventually the show went national in the mid-'80s. So when the internet came along, often teachers would like to show the episodes to the students. So they would do a search for Star Hustler, but when you search Hustler on Google, you don't get, well, you did, it wasn't as family friendly anymore. So
you got something. You got something, that's true.
So when Jack was talking to the producers of the show, he said, well, we need to change the name. And one of the producers, Ed Wagland, said, with Jack's advancing age, we should change the name from Star Hustler to Star Geezer. He said, no, Geezer's, even though he likes it, Gazer would be better. So Stargazer, or Jack Horkheimer Stargazer is the name that eventually went to. And then the manifestation of it today, we have Stargazers, plural, because there's 2 of us. And there were originally 3 of us. Right. Marlene Hidalgo, one of the science teachers from Miami, when in October 2011 was announced that we would revamp the show a little bit and have 3 hosts. She was our 3rd host, but actually she moved to this area.
That's right.
She was because she was so far away, she wasn't able to do the show anymore with us. But
Well,
Yeah,
so
but-
my memory of seeing the first time I saw Jack on TV was, I was really little, and I was watching it, and it was always on at the last thing that PBS did. So it was right before the station called it night. So why I was up at 12 at night, I don't know. But I was watching, I was like, boy, this guy's a little out there. He has the same, can you do the voice? Greetings, stargazers. There we go. And
I have the music on my cell phone that was on the show. We'll talk about that.
And he was always wearing this the jacket, the members only jacket, and so he's this kind of casual guy. And the other thing that, he's got a lot of claims to fame. Jack Foley Horkheimer is his full name, and he was mostly into acting and theater initially, and then found astronomy as kind of his love. And he was just this great popularizer. He really got people's attention. And so, oops, I didn't do that. Okay. So James met him several times at least, right? Because he was your boss, essentially.
He was my boss. And one of the interesting things, you notice the picture of Jack there, he's wearing his famous toupee. But at work, he never wore the toupee, and we're saying, well, why is he wearing the toupee? Is he vain about his, disappearing hairline? And it turns out that back in those days, were initially, when they started doing the show Star Hustler and then Stargazers, they had a practical set where you had planets and a moonbeam that Jack would walk in on. However, with the advent of technology, the advance of technology, they were able to do green screen technology. The problem is that chroma key, the technology they used for green screen, was not as sophisticated as is today. And in trying to key out everything that was not green, the reflection off the top of his head was disappearing. Or at least it was making the top of his head disappear. So rather than him wearing a hat, they said, oh, well, maybe you can wear a toupee. So I told my dad this story, and he said, well, goodness, you're completely bald. Do you want to wear mom's wig or something like that? He said, no, they've taken care of it. Although when we put makeup on, I also had to put makeup on the top of my head so that I don't glisten too much. And I said, this looks like Martian dust. Maybe I can get a face painter to paint Mars on the back of my head, the Tharsis Ridge, or maybe the Valles Marineris or something like that.
Yeah, that's what they said. Because that was one of the first questions I asked when I went in. They said, "Well, why? What was he wearing the toupee for?" I said, "Oh, well, yeah, because his head just disappeared. It was very disturbing to see just eyes and a cavity where his head was. Stars coming out of it. Not really the best thing." So Jack passed away in 2010, summer 2010, and so we were. James and I were both watching, and James is living in Gainesville, and I was in Cincinnati, and we were wondering, what are they going to do with the show? Are they going to continue it after all these years? And so the first person we saw right after Jack was a guy named Chris Trigg, who worked for was it the Science Center there? He worked for the Science Center, and it was kind of just like called into service. Said, okay, we need somebody to fill in.
And you're not hideous looking.
That's right. And they brought Chris in, and he did a really good job. I thought he was pretty sharp. And so then I said, well, okay, I guess they're going to continue the show. And somebody asked me, so why don't you see what they're doing? Are they going to have new hosts, or what's going to happen? And so I called up the station. I said, what do you guys, are you taking any tryouts? And they said, actually, Chris doesn't want to do it. How about you come down right now? I was like, oh, well, I felt kind of privileged. They didn't know who I was, but there I was somebody. So it worked out. So I went down for my first episode, and I got to sit on the rings of Saturn just like Jack and swing my legs and all this stuff and get burnt by Antares and Deneb and all sorts of stuff, and you flip around all over the place. So, by the way, how do you think that we sit on the rings? Anybody? What do you think?
CGI.
Not CGI. Come on, we're talking like 70s technology here.
The green screen technology we were talking about earlier.
Exactly. It's green screen, and it is a green chair.
Yeah.
So we're sitting on a green chair. It's high tech stuff. So that was my first time. And when I did this the first month, we used to film 1 month of shows at a time. And I thought, man, I really bombed. I felt like I had like deer in the headlights. I was like, all these lights. You're reading from a teleprompter, all this stuff. And I went after the first taping. I was like, well, I guess that was it. I'll go home to Cincinnati, and that was it. And they said, well, we'll give you a C+. But how about you come back next month? And I said, oh, sure. So I got the call back and did another month. And then they tried a few other hosts as well. We had Ed Romano did, I think, 1 month. He had the 1 month stint that Ed did.
In this area also.
Yeah, that's right. And then they called in this guy.
Oh dear.
Look at that young guy there. Look at that clean shaven face.
Hair.
He comes in the first day with a tie on. I was like, oh my goodness, who is this guy? And tell about your first time.
So I didn't, I was thinking maybe, do I need to wear a members only jacket like Jack did? And I said, no, well, I'll just dress the way I do at work. So I wore a tie because my wife was.
You wear a tie at work?
Yeah.
Oh my gosh, I don't even know you. Anyway, I'm sorry.
Anyway, with the when you're on national television, your wife says you're not going to be on television embarrassing the family, and Mom calls me up, says the same thing. It's like, okay, I'll wear a tie. So when I get there, the producers say, wow, you're kind of overdressed. Like, next time you can dress like this.
I think I wore jeans on mine, actually.
Yeah.
So that's how, anyway.
Yeah. So in the first episode, we did. I went down during the spring break at Santa Fe College, which was helpful because I had the whole week off. So I went down there, and we taped the episodes for the month of April. And one of my favorite episodes is we were talking about the Summer Triangle and so forth. And at that time, they did the special effects at the same time we were recording. So it took a lot longer to do that because that's what Jack insisted on. He wanted to see what the final product would look like as they were recording it, which made it a lot harder to do. But we did it, so they were actually able to have me spin in on the rings and land, and I would react as they were flying me in. So if you go back in YouTube and look at my original episode from April of 2011, you'll see when they spin me in on the rings, I actually react when I land, which is kind of fun.
Yeah, you were good at that.
Oh, thank you. Yeah, we don't do it
It's
anymore.
like you were flipping through space.
Yeah. And yeah, you'll have to tell the story about the people who called you asking whether we were okay.
Oh yeah. So that's the thing is that I asked the film crews, like, so tell me some good Jack stories, and the one that the cameraman Keith told me was that there were people that really believed we were in space. They really thought we went to space just to film this 1 minute show and to say hi. And so Jack Horkheimer got a fan that came up to him at one of the conferences like this. And it was this kind of older lady, and she comes up to him and she said, oh my gosh, I'm so glad to meet you, Mr. Horkheimer. Every time I see you, I'm just afraid that you're going to be lost in space. They're throwing you around up there. I'm just so glad that you're okay. And he's like, yes, thank you. I'm on Earth all the time, but I don't know if the graphics can fool people, but I guess maybe they can. I don't know. So then we also tried out another co-host, Marlene Hidalgo. She was a science teacher in Miami, Florida, and so for a little while there was 3 of us. So we were the stargazers, James, myself, and Marlene. And and she was with us for about a year or two, something like that. And so it was a lot of fun, just kind of playing off each other and flying through space and all sorts of things. And then she moved up to, I think, the New Jersey area, somewhere like that, a couple of years ago. And but this is kind of what the typical scene is. This is the green screen that we film in front of. It's kind of like what weather people do. And
it's a very big green screen.
And so this must be. I'm pretending to be Orion. And James is not impressed. But anyway, that's... and so then they just fill in the magic of television behind, and you could have anything you want. You could be on Mars, you could be all sorts of places.
We can't wear anything green.
That's true, yeah. You can't wear anything green, or else you disappear completely into the background. So here's the 3 of us, and this is kind of the full setup there. It's filmed in WPBT2 studios in North Miami, Florida. So James drives down from North Florida, and I fly down from Cincinnati. And so now we film 2 months of shows at a time. So we write the scripts for 2 months ahead of time, and luckily, astronomy is so predictable, we don't have any surprises.
Except for comets.
I know. Don't we need a comet, everybody? We need a comet.
Yeah,
this
we're
is ridiculous. It's been 20 years. We need a comet.
I'll write my comments.
And then we can have another trip to Florida. And so there's James in his usual hamming it up pose. One thing that I've learned about him is that he, well, let me think. Nerd is probably too weak of a word. He is incredibly nerdy. I mean, like, not only is your ringtone the Jack Horkheimer theme, like, whenever we're driving, he always has something spacey playing. Like, he's learning all the time about space stuff. And so, if you guys meet us afterwards outside, I do warn you, if you ask him a question, you will get the whole answer. That's for sure. So get ready for that. He also is quite the dancer. Whenever we need to relax and ease the tension, he's always doing so. What do you call that one?
What, this one or
whatever you.
Well, whenever we talk about conjunctions, I start dancing.
He has the conjunction.
I really like conjunctions.
And we had one fan write in and said, what's wrong with James? He's got ants in his pants. Does he have to pee or what's going on? So you might have to work on the dance a little. I don't know. It looks like you have to pee. But anyway. So one of the last things that Marlene did with us is that in 2011, she and I went out to Reno, Nevada, and we did a show out there for the eclipse. They had a lunar eclipse that was visible out there, and so we joined with the Reno public television and did a show out there. And so that was really fun. We're really excited about the other eclipse that's coming up, though. And so what we're going to talk about next is we want to really, the main part of Stargazers is to get the public interested. We know we're not like trying to teach, PhD astrophysics, that's for sure. We're trying to inspire people. We're trying to get people maybe their first looks through telescopes. And so we want to get a few things to get you guys going. And just to give you a little bit of an example of kind of what the shows are like, we've got a couple clips here. This is going to kind of highlight some of the unbelievably realistic graphics that we have. And so let's see, could you guys start this one for us? Start this video, please.
The bright nose of Canis Major, the big dog of Orion. And it's always kind of low in the southern sky from my latitude, but let's see the difference from down in Miami.
When Dean comes from Miami to film Stargazers, he's traveling down the curve of the Earth. So when he heads south, he gets to see stars that were blocked by his southern horizon in Cincinnati. For every 1 degree of latitude Dean goes south, he'll get to see 1 extra degree of the southern sky.
All right, that had to be the worst acting job of walking ever. I mean, they're like, oh yeah, that was good enough. I was like, that's terrible. That's terrible. Anyway, that's how I get to Florida, as I walk down giant Earth. Anyway, the next one is, this is the secret to James' hair.
The secret to my haircut.
Start this one, please.
The sun's output is the same all year round, but the difference in our seasons is how much of that energy we soak up. It has nothing to do with how close or far we are from the sun. We're closest to the sun every year in January and farthest from the sun in July. So the distance isn't the difference. Hey James, you staying cool?
The sun is blasting off my hair.
Oh, you're doing great, you're doing great. Now, let's see how our tilt affects the view from down on Earth. Sorry about your hair.
It's okay, it'll grow back.
And it hasn't. And it never did. Oh well. All right. And the next one, so we try to play off each other a little bit, and okay, so I'm kind of nerdy. I don't know.
A little.
Who's the nerdier one?
What's the orbital eccentricity of Mars?
See, there we go. That's the answer to that question. So this is, I don't know if you all have, some of you are from astronomy clubs and have gone to conferences where you have a constellation shootout, where you sit in a planetarium and try to shoot out, try to name all the constellations and stars. Well, that's what we do. So if we could start this clip, this is our episode about that.
Now we're facing south at 10:30 p.m. and we can see Orion high in the sky.
Below him is the rabbit constellation called Lepus.
Above Orion's right shoulder is Taurus the Bull.
And to the right of Lepus is the constellation Eridanus. Okay, James, since you picked Orion, I challenge you to a star lightning round.
Oh, goody.
Okay, we're zoomed in on Orion and we're going to name stars. Go.
Rigel,
Bellatrix,
Misa,
Alnitak,
Alnoran,
Mizaka,
Safe,
Betelgeuse.
Good play, Mr. Regas.
We could be here all night.
I mean, it's kind of weird that we do a show where we talk about like obscure star names, and like they still want us to do those. I mean, like, so we're like trying to sneak in education here wherever we can.
Yeah.
And so James is really good at constellations.
Yeah. So we started doing the couple of episodes, the one on Bootes, the herdsman, that airs either next week or sometime soon. We talk about the individual stars in those constellations. Because I'm the director of the planetarium in Gainesville, as it were, and I'm also the president-elect for our region's planetarium association. So we have, at our conference, we have a constellation shootout where all of us gather in the planetarium, and they set the projector to the latitude of the host planetarium, and they just slowly cruise the stars by. And John Bell, who is the director of the planetarium at Indian River State College, he's my role model. He can tell you the name of a star that's so obscure, it's like, I didn't know that star had a name. So I wanted to be like him. So fortunately, at one of the conferences, they had the same planetarium projector that I have at my planetarium, a Godo Chronos. So having the Sakai easily recognizable, because it goes down to about 6th magnitude, the magnitudes of those stars on the Godo, I won that competition. And then the next time I competed, I won again, because thanks to doing stargazers, I've learned all of my obscure star names, like Rastaban, which is one of my favorite names, and Grafus and Jashuba. So yeah, now I just judge the competition. I don't compete in it anymore. But that's
You're too much of a ringer, right?
Yeah. So now, thanks to stargazers and working in a planetarium all the time, and we'll talk more about all the different shows that we do.
Yeah. And our final clip is, okay, now this was an episode that I really lobbied for, that this is one that I wanted to, I guess maybe in another life I wanted to be a stand-up comic. So I asked, could we do a show just about moon jokes? Yep. So get ready for some bad jokes. If you could cue that one, please.
The long-awaited moon joke episode. Hey there, stargazers. I'm Dean Regas, astronomer from the Cincinnati Observatory.
And I'm James Albury, director of the Kika Silva Planetarium in Gainesville, Florida. We're here to help you find your way around the sky.
And this week to share some space jokes, specifically about the moon, since you'll be able to see it after dark each night this week.
Dean's been wanting to do this forever, so just humor him.
We have some gems, like what holds up the moon?
What?
Moon beams, of course. I got a million of them.
Well, more like 5 or 6 of them. And as we wax on about the moon and show you what's up in the sky, we know that your interest will not wane.
Let's show you.
So, how does the moon cut his hair?
I know, eclipse it.
But that makes me think about eclipses. And although we had 4 total lunar eclipses in the last 2 years, we won't be having another one until January 31st, 2018.
I hate waiting that long for an eclipse, so luckily there will be a solar eclipse before then. Mark your calendars for August 21st, 2017. That's when the new moon will slide in front of the sun and block part of it out.
This eclipse will be easy to see across the entire lower 48 states. And if you happen to be in the right place at the right time, on a narrow path between Oregon and South Carolina, you can see a total solar eclipse. That's when the new moon blocks out the entire sun.
Wow, so that's just a little sampling of some of the shows that we do to get you guys excited about this. And I think what we really want to cover a lot about is, you know, how we can all be part of this, how we can all be part of spreading the word about astronomy and science. And this is one that James shared with me. I loved it.
Yeah, because I found out in my travels that not everybody likes science. So this is, I love finding memes on the internet. So to describe this one, first, okay, we're not the center of the universe. 2, once you believe in science, you feel that, okay, well, we can't prove God. And then third, there are no unicorns. So, yeah.
But science is one thing, but astronomy.
Yeah, astronomy, people love astronomy because at every level you can participate in astronomy. You can participate in it at one end where you're doing research and graduate work, and other end you can actually be an amateur astronomer and just look up at the night sky and keep track of things that are happening every day in the night sky. So I often ask people if you could describe astronomy in one word, what word would you use? And some of the words that came up we're advancing much. Okay. Beautiful, mysterious, impressive, Cool was the one that you submitted.
Oh, I did cool?
Yeah,
Okay.
and inspiring and big, because everything in space is big. And sometimes those distances and sizes are really tough to comprehend. But when you put it in a smaller scale, say for example, if you put the entire solar system in a coffee cup with the orbits of the planets included, our galaxy would be the size of North America on that scale.
And
So-
if you think of anything that you see in the news, it really struck me is that all astronomy stories are always positive. There's like no negative astronomy stories. It's like there's always something new that's discovered. They discover a galaxy, or they discover a planet orbiting around another star, and I don't know what it is. There's no like downside. It's like that we have this. We have this conduit to the media, where the media loves these stories. They love sharing it with the public, and
it's inspiring. It gives hope.
I think so.
Because I was inspired by Star Trek, and I used to watch Star Trek all the time. Oh, that'd be really cool to travel to different planets and visit. And then the space program. I grew up I was born in the late '60s, so I was alive when we were sending people to the moon and so forth. So I remember seeing Saturn V launches as a kid, and that has something. It sparks an interest in people, and I'm hoping that once we get the Orion program and we start planning missions to the moon again and to Mars, it'll inspire a new generation. So that's one of the things that's a passion for me, is to, with our planetarium and then the observatory and the show Stargazers, that we can inspire young people to think about traveling in space, because we develop a lot of other technologies as spin-offs from space exploration. So, opportunities. So, with the challenges of getting people interested in astronomy, there are always opportunities in engaging them. And as many of you as amateur astronomers know, back up. Okay. So one, you can visit a planetarium, and most of the people I've talked to, their first time visiting a planetarium was as a child on a school field trip. And you'd be surprised, quite a few people never get an opportunity to go back to a planetarium until they're an adult and they have kids and they take them to a planetarium. How many of you have been to the Hayden Planetarium in this area? Okay. How many have been to a planetarium other than the Hayden? Okay. Yeah. I've always wanted to do a planetarium tour and make a t-shirt of all the planetariums I visited.
That would be cool.
Yeah.
Like a concert tour, except
Yeah.
for planetariums.
Yeah.
Oh, that's pretty cool.
Yeah. So, okay, we can
All right.
advance to the next one. Now, often movies can inspire you to go into space. So recently we had 3 movies that would inspire people to be astronauts. So Gravity, probably not, because if you saw Gravity, they really should have called that traffic. But Interstellar and The Martian, both were movies that talked about what would it be like several years from now. Because my son, who's 6 years old now, he will be the same age as Mark Watney was in the movie, or he is the same age. Well, by that time, he'll be that age. He'll be in his 30s. And Interstellar talks about how we could potentially go to another star system using the physics that we understand today. So, and then the gravity thing, well. But it was a cool movie, the special effects.
Yeah, either shrapnel or inertia. I think that was the other thing it should have been called. But
Yeah,
anyway,
and putting stuff in the same orbit, very close to each other. That is not.
So yeah, I think we do. I don't know if you guys do this, but when we see movies, sometimes the science distracts us. You know, the kind of science, and luckily for all of these, I can kind of turn off that part of my brain and say, "Oh, that would never have happened." Oh my gosh, yeah, right. If they would have tied down the rocket better, it would have blown over.
Yeah.
Anyway, so we got these movies, and then we also got those movies that. Oh, Pluto Nash. That was the other one I was gonna. Oh yeah, anybody see Pluto Nash? It was on like Star 64 the other week, and it was bad. It was pretty bad.
Yeah, some movies might make you not want to go into space. But, I wonder, will that play? I don't know if I don't think. Okay, well, I had a video of this, but videos and images from NASA can really inspire. One of the ones that recently I saw and I shared it on my Facebook page was the image of a close-up image that Cassini took of the hexagon at the North Pole of Saturn. And that hexagon is actually produced by a phenomenon called Rossby waves, which is a jet stream pattern that happens on planets. But particularly on Saturn, the planet itself rotates so much faster in the atmosphere that it causes eddies that make little pinch-off points that form a hexagon. And in this picture, they showed a little storm, a little cyclonic storm in the hexagon. And that storm was bigger than the entire state of Texas. Go tell Texas that. Texas to the crowd. So, there we go. Okay, so Hubble pictures and pictures from Cassini, as I mentioned before, can also inspire. Because that picture of Saturn from the nighttime side, of course, we've never seen that before, and we can't see it from Earth. But when we send robot probes out there, we can catch images and vistas of the planets that we could only imagine before. And the Hubble images, I'm really excited about the James L. Webb Telescope eventually being deployed.
Yeah, we only have a few more months of the Cassini mission also. I mean, it's been there since 2004, but it's going to end September of this year when they're finally going to crash it into the planet. So we only have a few more months to get these amazing pictures of Saturn, because we're not going to have anything around orbiting Saturn for a long time. There's nothing on the books. So that was my favorite mission, is the Cassini mission. And yeah, I'm glad you mentioned the hexagon part of it too.
Okay, so one of the other opportunities we have is the best thing we can do to interest young people, or anyone for that matter, in astronomy, is to show them something interesting. And when I was about 18 years old, that was when Halley's Comet came by. And how many of you saw Halley's Comet? Yeah, so it was hyped up because it's kind of humanity's comet. It comes by every 76 years or so. So my great aunt, she saw it in 1910 when she was 10 years old. She got a chance to see it again in 1985. And of course, my mom, who had never seen it, she was like really excited. I was like, oh, when is it going to get here? When is it going to get here? So because we live in Miami, there are a lot of street lights, so we drove down to Homestead, where it was a little bit darker. And I had the telescope set up, aimed at Halley's Comet. And she looked through the telescope, and she said, and I quote, "That's it?" Because she sees all these pictures, and she expects this big flaming thing in the sky. I said, well, Mom, it's really just a ball of rock and the ice is melting, and it creates a little atmosphere, and the solar wind blows the tail back, and it's on the opposite side of the solar system, unfortunately, so it was very dim. So, to salvage the moment, I said, well, Saturn is up. And coincidentally, Saturn is in the same spot in the sky as it was 30 years ago, because it takes 30 years for Saturn to go around again. Because Scorpius and Sagittarius are right there. So I aimed it at Saturn, and she looked through the telescope and said, oh my gosh, you can see the rings. I said, well, yeah, Mom, it's a telescope. But then I realized, no, don't say that, because Mom will slap you. But yeah, so a lot of people don't realize that when you look at that dot, bright, because most people don't realize you can see the planets as bright dots in the sky, and when you aim a telescope, you can actually resolve the rings or the moons of Saturn, or depending on the size of the telescope, you can see the great red spot. So, is that on the next slide or no? Okay. So the things that when you have an opportunity to share an astronomical event with folks, because sometimes we'll do sidewalk astronomy, and we'll talk later on about a couple of events that I've done at our planetarium with our local schools. And when little kids, when they look at Venus through the telescope, we did that about a month or so ago, the kids would look at Venus and its crest and say, oh, look, it's the moon. It's like, no, because the moon wasn't up, unfortunately, otherwise I would have shown them the moon. But when they see Venus looking like the crescent moon, you don't want to dampen their enthusiasm and say, well, that's not the moon, that's actually a planet. But you say, well, Venus, the way it is right now, it looks a lot like the moon. And so, but at least they're associating it with something that they're familiar with.
And so this is the trap that maybe you've fallen into if you're an astronomy educator or in an astronomy club, is that there's events that get hyped in the media, like a comet or a meteor shower, and then you go out there with the public, and the public is disappointed. They're like, oh, well, that was it. I heard there's going to be 100 meteors per hour, and there's like, and I saw 2.
Or the converse of that is what we used to call the Horkheimer effect. And the Horkheimer effect is like Murphy's Law for astronomy. It's basically the probability of cloud cover is directly proportional to the awesomeness of the event you're trying to show people. Yeah. So, and we jokingly named it, Jack named it after himself, because like we would publicize things. So, for example, the transit of Venus that happened back in 2012, we're hyping it. In Florida, we were able to see it just before sunset, but if you've ever been to Florida, weather in Florida in June, it's really nice and sunny in the morning, and then you get thunderstorms in the afternoon. So we had 300 people at the planetarium, and just as the transit was about to happen, we had storm clouds build up, and it started pouring down rain. So we all went inside the planetarium, and fortunately for the internet, we had video feeds from SLU and a couple other observation points. It seems like Arizona has the best weather. Arizona and New Mexico, they're all, which is why they put observatories there. But they had an image of the transit. So when I got home later on that evening, my son was 2 years old at the time. I was telling him, hey, that's Venus transiting the sun. And of course, he didn't really know what was going on. But he'll be, I don't know, he might live to see the next one.
No?
Yeah.
100 years from today.
117,
100 years from now.
100, yeah, maybe.
So yeah, you want to, that's the trap, is you want to publicize your events, but you want to make sure you have something good to actually show them. So,
The big one.
you got something. The big one! Now, I mean, comets. Who knows what's going to happen with the comet? Meteor showers, who knows what's going to happen with meteor showers? This is something you know is going to happen, and it's going to wow your crowd. This is going to be huge. I can't underestimate this. I can't underemphasize this. This is going to be so big. The media is going to be all over this. And so what we want to encourage you to do is to use this moment to your advantage. Because if you're an astronomy club or if you're just an astronomy enthusiast, the media is going to need your help. Because they, how do I put this delicately? They need your help. They just need your help. And to explain something to them that they can understand. Oh boy, I'm digging it deeper. Anyway, the way that you can put it to them to help them understand things that they can communicate then to their audience. This is really important. And because this is going to be so huge, this is going to be all around for that whole week and probably even a month ahead of time. Because this hasn't happened in the United States in 38 years, at least in the mainland U.S. And it's going to be visible from coast to coast. And everybody in the U.S. will at least get to see a partial eclipse. So it's a story for the entire country. Now, I've been looking forward to this for a long time. This is a slide from one of my early PowerPoints when I first started the observatory. And I showed this to kids. I said, oh, there's going to be a total eclipse. Like pretend this is the year 2001. And I said, there's going to be a solar eclipse in a short period of time. 2017, 2024, and 2045. 2045. And that was a good joke. But now, it's almost here. I can't wait. This is something we've been looking forward to for a long time. So we have to really share this with as many people as possible.
I'm already promoting the 2045 eclipse because that one goes through not only where I was born, Denver, Colorado, but centerlines also the entire state of Florida. And it goes over where my mom was born, Nassau, in the Bahamas. And the moon is going to be a perigee on that eclipse. So it's going to have between a 5 and a 7 minute totality, which is one of the best solar eclipses in the 21st century. And it's 2 weeks before my 78th birthday.
That's right.
Yay.
And so James and I are planning to be in our retirement homes there together to watch it from South Florida. What do you say?
Yes, that works.
All right.
We'll probably still be doing stargazers.
Maybe we'll be. Then we'll definitely call it stargazers. That's for sure. So here's what I recommend is that if you're in a club or even if you want to promote your organization, definitely approach the media. Make the first contact. Introduce yourself. Say, we got this event coming up. If you have any questions about it, I'm the guy to talk to. Let us know. We'd be happy to help because there's going to be some, have to figure out when the timing is, how much it's going to be blocked from where you live, all that kind of stuff. And so just make an introduction would be very good. And I highly recommend talking to the weather people. They are the scientists of the news. And so you really need to make your friends with the weather people. Oh, is Joe Rao out there? Sorry, Joe.
Yeah.
He's a weatherman and an astronomer.
So not only can you sacrifice a goat to get the eclipse to end, maybe you can do something about making clouds disappear.
That's right. Yeah. But whether the meteorologists really love astronomy, I've never met a meteorologist who doesn't like talking astronomy. And so if you can get in good with them and that they know who you are and you can make contact with them, that's a really good way to do it. Now offer them your expertise, and then offer them a program. Get the news to come out and do a program, or just have them invite them over to show through the telescope, or bring a telescope to the studio. Even better. That's a great way to do it.
Or collaborate with your local planetarium to see if you can partner with.
Oh shoot, no. What's that? Yeah, there it is.
So, because when I started working at the planetarium in Gainesville, I started working there in October of 2009, and just shortly after that was the Leonid meteor shower, and I got a phone call from our local television station saying, hey, we want to come out and do an interview about the meteor shower. And I thought, oh wow, I'm now the Jack Horkheimer for Gainesville. Because when I was younger and I went to summer camp, there was an opportunity where and this was before I started working at the planetarium, I saw Channel 4 visit the planetarium in Miami, and Jack was there doing an interview in the lobby. I thought, wow, that's really cool. He gets to go on TV and talk about stuff. And then when I went home later on that night, I actually saw what they recorded. So anyway, when the media contacted me, I realized, okay, that I need to be ready to talk either on television or on the radio when it comes to astronomical events. So you can be the Jack Horkheimer of your particular region or your neighborhood.
Oh yeah, I mean every city really needs this. I mean, because this isn't something that the professors and universities do like to do, I guess.
And some people don't communicate as well as...
Right, and that's what the TV folks told us. So, oh, well, we used to always call the University of Cincinnati, but now we can talk to you. And so they really need it. That's the thing. They're looking for it. And this event is going to be perfect for that. And so then you can also try to spread the word through teachers. In Cincinnati, at least, August 21st is going to be a school day. It's a Monday, and a lot of people are back in school, and we're at the range where it's only 90% blocked in Cincinnati. So we're trying to educate the teachers that, oh man, they're stuck there. The poor kids, and the teachers have to be stuck there, and so we want to educate them on how to see the sun safely.
And one of the things that our Planetarium Association is doing is we're ordering a lot of eclipse glasses, and we're going to distribute them in our respective communities to the schools so that the teachers at certain schools have the glasses, because the kids will be getting out of school for us just the maximum part of the eclipse. So you can do that in your communities. And the nice thing about the eclipse glasses, you can put branding on it that advertises your astronomy club or your observatory or planetarium.
Yeah, and I think getting the word out early is good, because I don't know if you've ever heard of this tragic story that I heard from the 90s when there was a annular eclipse, almost a total eclipse around Ohio, is that the principals basically canceled recess. So they said, we don't want you going out there and getting blind. So instead, recess is canceled. And so nobody saw the eclipse in almost the whole state of Ohio. I mean, it was tragic to hear this. Or you could educate the teachers to look at safely and wow the kids.
Yeah.
Or, so that's what we want to try to get in front of this and try to get the word out a little bit more. And the key thing is that you probably will want to wow them ahead of time. You'll want to wow them by bringing scopes to them and showing them views of the sun, safe views of the sun, put a solar filter on things, or just host star parties at night for them too, and show them really interesting stuff like the moon in a telescope or Saturn in a telescope or something like that. So you could outfit your historic observatory with a solar filter, look at the sun, take telescopes out to places and observe the sun there. This is with a H-alpha filter on a scope that we took to a school. And then getting telescopes in the hands of people is always good, because that's what it feels like. So many people have not ever looked through a telescope, and when you show them that, you introduce them for the first time, it's just the feeling you get back is just incredible. So these are some telescopes that we awarded. These are Galileo scopes, and these kids were so excited. They're looking at the moon, and then they're showing it to everybody else that passes by. And so a lot of you are probably in astronomy clubs, and you have a lot of people that you can work with, and have a lot of people who get out there and mobilize to do this. And this moment of the eclipse could be a way to either boost your own numbers in your club, or start a whole new era, really, of having new members in your astronomy club, because this is going to be such a widespread thing.
Mm-hmm.
Then you can also travel to places, because, well, I'm not going to stay in Cincinnati for a 90% eclipse. And
yeah, I'm going to try to see totality myself.
Getting mobile and getting out there and joining some other star parties is good. Annular eclipse that happened in 2012, I went out to Reno, Nevada, and had a really cool sight to see. This was the star party there where they had a few thousand people that were set up. And it was sunny. Well, most of the time. And so you could get to these star parties and get out there, and so I definitely encourage you to not settle for 90% eclipse. I'd say get out there and see as much as you can. And then you can also do some star parties in advance to this, like this one. What was this one?
Yeah, this one we did a star party as part of. First one was Night of Stars over at Duval Early Learning Academy in Gainesville, and we did one the following week, and this was in February over at Irby Elementary, where my son happens to go to school, and that's my son. Interesting thing about your children and when they see you do things, they want to do the same thing. So, and we even cut our hair the same way, oddly enough. But and cloning works. But yeah. So, but yeah, it's funny. He knew all his planets by the time he was like 2 years old, and I said, "Wow, it's a good thing I don't work at a liquor store." So the telescope we had, our planetarium has been blessed with donors who will donate telescopes to us. So one of our students, he donated his Celestron Next Star to us because he said, I live out in the country, but I never really had time to set it up and operate it properly. So he donated it to us. So it's a lot more portable than our 12-inch Nicassagrain to take with us. So we carry that, and that's the one that the students look through. And so I first lined it up with Venus while it was daytime. Because a lot of people don't realize that you can see some of the planets in the daytime. I showed a couple of our professors Venus just in the sky, because as Venus was coming around as a crescent, we got to see it. So having the kids look through the telescope. And how many of you actually have done star parties yourselves? Okay. Have you ever noticed that when kids, particularly younger ones who are, I guess, younger than 6 years old, when they get up to the telescope, they immediately want to touch the eyepiece? It's like, no, I just aligned it.
Oh yeah, I think Corona. Yeah.
We should write a top 10 list, top 10 things that often happen at star parties. So. All right, so.
Have you heard the trick to stopping that?
Oh, what is it?
I've seen this in action, is you get a walker. Like, a nursing home walker, and you put it right in front of the telescope, and so when the kids go up to lean in, they put their hands on the walker, and then no moving telescope. Except for then they're like, what's that? And then it's gone. But yeah.
Yeah, because like with my ladder, you see how the kid...
Oh yeah, see, the ladder does it too. Perfect. So in I also, we're going to be talking about this eclipse as being such a giant thing, but let's not forget some of the other wow moments. And I've kind of come back to Saturn again, because I know probably a lot of you have seen Saturn over and over and over again. What I always think of is the first time I saw Saturn at a telescope. When I first got this really cheap telescope and I pointed at Saturn and I found it myself, and I was just like, I still remember that so well. That was this moment in my life. And so we're going to have Saturn up during the summertime, right before the eclipse. And so I really highly encourage using that to show people, because Saturn is going to be at its most tilted for its cycle, and it wows the crowds every time. Guaranteed.
Jupiter was my first planetary experience. I purchased a telescope when I was I purchased my own telescope when I was 18, but I got one as a gift when I was 13, so the first planet I want to look at is Jupiter, because in Sky and Telescope, not only do they show you the positions of the moons every night. So I looked through my telescope on the particular night, and the moons were right there, and the next night I would say the moons had shifted. And that made a huge impression on me, that you could see the moons of another planet through just the modest telescope.
Yeah, and I think Saturn is one of those things, and Jupiter also is just that. I wrote an article for Sky and Telescope about Saturn and kind of my relationship with it, and it's I've been doing this for almost 20 years, and it's sometimes you forget about what it was that inspired you in the first place, and Saturn was definitely that thing for me. And just to take the time, it seems like, oh, well, we're going to look at Saturn again, but for somebody that's never seen through a telescope, I'm still shocked at how few people have actually looked through a telescope before. And they come to the observatory for the first time and look through a scope and see this. It's something not to be glossed over, that's for sure. And then another way that I found that's really good to engage folks is using their technology. Is you get the telescope, you point it at the moon, and I don't know, have you gotten this? What do people want to do? Take a picture. There you go. You got it right there. They want to take a picture with the cell phone. And of course, this is always frustrating to the people in line. They're like, "Oh, another picture through the telescope."
And I can barely. And they try, and it's not easy to do unless you have a mount for it, like they did in the Celestron commercial.
And this was just one that somebody held up to our telescope. Of course, it was through the observatory telescope, 11-inch refractor with a 2-inch eyepiece. But still letting people have a picture that they can take home with them is really powerful, because they're gonna keep it. They're gonna tweet about it. They're gonna. What else do they do?
Personalizes the moment.
Snapchat.
Yeah.
What's the other one?
With Twitter.
Instagram.
They'll tweet it, or Instagram.
I don't know what it is at all.
So, but yeah, I Instagrammed the first photo that I took through our telescope, and I was like, wow, because my cell phone, it's not easy to line it up properly. But when you do, and you can actually capture it, it's quite an amazing thing.
Yeah, and I think just that's where kind of things are going, is that more and more people that come to the observatory, they want a picture, and it's a great marketing tool for your group too. You get that out there, you get people talking about it. It's really pretty cool. So I'm not sure. Speaking of Arizona, this is Arizona. I went out to Sedona to see a few things. I saw the transit of Venus and a partial eclipse out there, and I would say definitely get hooked up with other clubs. It kind of boggles my mind whenever I travel somewhere and I want to meet other astronomers, or I want to hook up with other clubs. It is so easy. If you know where you're going, just send an email to an astronomy club, and they are the most friendly, welcoming folks. It was this guy in Sedona he was the president of the astronomers of the Verde Valley, and he invited me to his house to view the transit. I mean, he doesn't know who I am, and he just invited me. They're like, "Oh, he's another astronomer. Come on over." And we came to his house. Now, of course, he was a little into it. He had a separate structure with 4 permanently mounted telescopes mounted in a slide-off roof, and camera equipment and stuff like that. And his wife let him.
That photography is one of the 2 hobbies that can get quite pricey.
Yeah. So if you are going to travel for the eclipse, definitely hook up with some other astronomy clubs, because I found universally, there's no exceptions, all of them have been so great and welcoming. It's like we're kind of a brotherhood. Yeah. It's like the astronomers.
Either that or misery loves company.
Oh, I mean, that's what it is. That's right. And so it's always great to have them doing that. And there's James. So what's your where are you going to go for the eclipse?
Well, our astronomy, the Southeastern Planetarium Association, we booked a block of hotel rooms for ourselves in Kentucky. So we're going to try to all meet there for that eclipse, and it's in a resort that's in the center line for the eclipse. And my colleague who I work with, she said she's okay with manning the planetarium that day while I go. And it's the first day of classes, so one of our astronomy professors begged the department chair, "Can I please go?" And we'll start class the next day. It's weird. I almost want to ask the college president if we could push the first day of class to the 22nd, not the 21st. But
yeah, I already put in my notice that I'm not going to be there that day. That's going to be a problem. Is that I don't know if anybody's going to be at the observatory on the eclipse day. We might be closed.
That's one of the challenges of solar eclipses, because those of us who are in the know about it, we want to actually see it ourselves. But if you don't live in a city that's on center line, so it's do I want to be, because you really want to be there to educate people, but you also want to see it yourself. So, yeah. Okay, so let's see.
Well, so
we have 7 minutes, 20 seconds left.
Oh my gosh!
I know.
I think they started the clock late.
No.
No, they didn't. Oh, okay, good. Well, anyway, we definitely want to encourage you guys to use this moment. Use this to really inspire a lot of folks. Build your club and make some connections to the media that's going to last after the eclipse. Because there's always going to be more stories. We're always going to have more things that are going to be in the news. And if they know who you are and where you are, they will definitely get in touch with you. And so I want to leave you guys with our parting shots. Here's Jack and the crew. Well, a lot of the crew's still there with the show, actually. And they're there doing their keep looking up symbol. And I found this one here. Here's the Jack's one. And there he is. Keep looking up. There it is. Yeah. So thank you guys very much for having us today.
So I think we may have time for any questions, if anyone has any.
Yeah, we have some questions.
Yes. Okay, so your question was that you heard how the speed of light? Yeah, the speed of light. So what is the speed of dark? Oh, dark energy and dark.
I think it's still something we don't. Dark energy and dark matter is still something not completely understood. Yes, so they can calculate the speed of how galaxies are spreading out. The question is with what kind of accuracy are we recording this? That's the thing. But the evidence is suggesting that these galaxies are receding away from us very fast. At least the farther galaxies are, the faster it seems like they are getting away from us. But there seems to be some other force that's involved that's accelerating this more than it should by just the mass alone. But that's one of the things we're a long way from understanding that one completely.
Yes, sir.
Here's two parts. Where can I find a list of stations that carry your programs? Because I don't know if any of the PBS stations actually carry it.
Yeah. Okay. So the question was, where can we find a list of shows that carry our program? And what was your second question?
Oh, the second part of it is, are you guys concerned about the potential demise of the CPB, Corporation for Public Broadcasting?
Yeah. Are we concerned about the demise of the
potential
demise of the CPB, the Center for Public Broadcasting? So,
well, the first question I can answer is there is no database to say which stations run our show. I tried to put that together, but the deal is it's a free show. They beam it out on a satellite, and they pick it up. Whoever wants to pick it up picks it up, and it's totally free of charge. I've got a list of about 100 that I know of that they use it, but there's still a lot of them that we're not sure if they do or not. So if your local station doesn't air for stargazers, they really do respond to it. You can give them a call, write them a letter, and say, it's free, and then their eyes will be like, oh, in that case, there we go. But right now, the best place is to find it on the internet. So our website is stargazersonline.org, and it has pretty much all the episodes on it.
And then in regards to the Corporation for Public Broadcasting, for Stargazers, we are primarily funded by donors, the Admirers and the Bachelors and so forth, and a few of the other folks. So every year we solicit donations from those folks. And people also donate themselves individually online.
In terms of venues for carrying the program.
Oh, venues for carrying the program.
Well, yeah, so the Stargazers doesn't necessarily have to be PBS. Like even CBS, ABC, anybody can pick it up if they wanted to. But yeah, it's we're a little concerned about that. But there's other outlets.
Yeah, we're also on the internet, so a lot of people see us on the internet if they can't catch us on there. But of course, the television station that produces us is a PBS station. So it looks like we're about to wrap up. So we want to thank you all so much for traveling the millions of miles, or thousands of miles. Hundreds of miles.
And we'll be happy to meet you guys outside. We'll be out at one of the tables just down the steps. And I'll have my book available for sale. James will have some postcards to sign. And we also have some limited edition Keep Looking Up pins if you come and meet us afterwards. But we'll be out there for a little bit. But thank you guys so much.
And keep
looking up. Thank you.
Thank you very much.
Take a closer look. We can take a picture of it too.
Look, Mommy, we took a picture of the moon.
We choose to go to the moon in this bikini and do the other thing, not because they are easy, but because they are hard.
Picture.
but because they are hard.
Take a closer look. We can take a picture of it too.
Take a closer look. We can take a picture of it too.
Look, Mommy, we took a picture of the moon.
What's up?
No, I didn't know because I was working here on boats.
We choose to go to the moon with this machine and do the other thing, not because they are easy, but because they are hard.
Alright. You did?
Take a closer look. We can take a picture of it too.
Ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, welcome back. Welcome back. Oh my God, what a crowd. You guys are great. Welcome back. Are you guys having a good time here today? Yeah. Are we providing you good information and good talks here? Yeah. Well, you're not going to be disappointed in this next talk. So, our next speaker, and we're very, very proud to have him here with us today. He was the Discovery and New Frontier Program Managers. He was the Deputy Administrator for Sciences at NASA headquarters, the SLS Program Manager, and presently he's the Center Director at Marshall Space Flight Center. Please give a loud and give it up for Todd May.
Thank you. I was told to stay on the blue carpet. Hey, so I'm really excited to be up here. This is my first time up here to this event, and it's kind of a payback to Ken Kramer, who's on the board here, and he's been coming to a lot of our events over the years. He said, you really got to get up here. Guys like John Grunsfeld and Bill Gerstenmaier and Jim Green have done the talk, and it turns out I've worked for most of those guys, and a couple of them have worked for me, so it's great to be part of this. The other thing I really like about this is raise your hand if you know where you're going to be on August 21st, 2017. Yeah, I'm going to be in Calvert City, Kentucky, so I get it. So anyway, thank you for having me here today. I'm going to talk a little bit about exploration and tie some things together, I hope, and as well as give you an update on the Space Launch System. Marshall Space Flight Center has a long history in exploration, both of humans and the type that you like. We were heavily involved in the early development of the Hubble Space Telescope and the Chandra Telescope, and we still operate with the SAO and harbor the Hubble Telescope today, as well as the development of the Saturn V and all of the propulsion elements for the Space Shuttle, and now the development of the Space Launch System. So I grew up in a small town on the coast. No, I didn't grow up on the ship, but I would go down to the coastline a lot when I was a kid and look out at the horizon, that thin line that separated the ocean from the sky, and always wondered what was beyond it. And some things kind of clicked for me later on in my career. If you go back, what I loved about the advertisements you were seeing is they showed the astronomy, and then they showed the JFK speech, where we say we choose to go to the moon. But if you really look at that speech, there's a lot more in there. One of the things he says is that space is the new ocean, and we intend to sail it. And that's when I understood that exploration and discovery is really universal. Whether you're an astronomer and you're exploring with your eyes, or you're a scientist and you're exploring with your mind, or we send robots in the planetary world to other bodies, celestial bodies, and we explore robotically, or we explore with human feet like we have on the moon. But also through history, exploration is also kind of universal. If you've ever seen old maps, they have usually up in the corner that little dragon with the humps coming out of the water, kind of like Loch Ness. And it would say in Latin, in the really old ones, Huc sunt dracones, which is here be dragons. And if you watch The Right Stuff, the intro there, they say, in kind of this dramatic voice, he says, there was a demon, they said, that lived in the sky. He lived behind a barrier. They call it the sound barrier. And if you ever went beyond it, you would die. And I think that's kind of universal, right? Whether it's the ocean, or whether it's the sky, or whether it's space, there's also a little bit of danger when we send humans out into that unknown. And so, of course, these are the Nina Pinta and Santa Maria. My grandmother actually gave me these models when I was a kid of these ships. And so I always understood that idea that space really is the new ocean. And like probably many of you, and that father and that son in the advertisement, my dad actually used to take me out to see lunar eclipses near the Gulf Shores where I grew up as a kid. So enough about that. I'll talk a little bit about Mars first. Of course, I came from the National Space Symposium this week, where they had all the center directors lined up, and the final question by David Livingston, who was our moderator, was, what are you doing to get us to Mars? And of course, Bob Caban at Kennedy says, well, we're building the launch complex that's going to launch the rockets. And I said, we're going to launch the rockets And it gets to Mike Watkins, who's the director of JPL, and he kind of said, well, we're already on Mars. So yes, we have definitely gotten to Mars robotically. At one point in my career, I actually had the chance to sit console when we landed Phoenix. I sat right behind the project manager, Barry Goldstein, and it was a very visceral moment to actually vicariously explore. And when the first pictures started coming up, I was in the room with the scientists, and I felt like an explorer. But you know, Mars is hard. And some of you may have seen this graphic before. What it is working from the outside. If you see the various colors there, those are the colors of the lines are the various countries that have attempted to get there. And at the end of those lines heading towards the center is either a green check or a red X. And the red X unfortunately means mission failure. And as you move in, the circles there, you go from a flyby to an orbiter to a lander to a rover. And what you'll find if you look at it closely is that the United States has had a pretty good record. Many other countries have not, and more than 50% of the missions to Mars have failed. It's a tough prospect. The moon was hard, but Mars is even harder. And so I'm going to talk a little more about that as we go forward. The other thing I'll point out on this slide is this quote here, reach new heights and reveal the unknown for the benefit of all humankind. That's actually NASA's mission statement. And there's about 17,000 people that work for the agency all over the country, and we get up every day, and this is what we get to do. This is our mission. And it's really fun to be part of the agency, and particularly fun to be part of the agency at this particular time. Because at this particular time, we are establishing commercial ability to launch humans into deep space. We are building the most powerful rocket we have ever built. The James Webb Space Telescope is going to launch next year. We are celebrating more than 15 years of permanent human presence in space, and we are working on going deeper than we've ever been. So, as I said, Mars is hard, and I think Bill Gerstenmaier has spoken here before, and he's probably talked to you a bit about this. But if you really think about where we are today from a human perspective, we're in what's called low Earth orbit, and we're pretty much Earth dependent. If something fails on orbit, we build another unit and we send it up. And we can have astronauts down in hours if we needed to, if there were an emergency. If you want to get out to Mars, you're talking about a multi-year mission. And when you do that, you're going to be Earth independent. And you really have to rethink how you do reliability, maintainability, and logistics. If something goes wrong on the way, you're not going to send another unit up. You're on your own. And that really has caused us to think differently about what we're going to do when we go. For example, you may want the ability to make 3D parts of just about anything you need and have on a stick all the drawings of the entire spacecraft. You may want to deconstruct the racks so that you can get to just about any part you need to. You may want to make everything as common as possible so you can borrow from one area and put it over in another area. Those are the kind of things you've got to think differently about. You've also got to think about things like performance, especially when it comes to things that we're real interested in at Marshall, like regenerative life support systems. Whether you have regenerative water or oxygen, those are two things that we humans, it's one of the reasons that the rockets have to be really large. We're pretty needy. And today on the International Space Station, our performance is about 40% to 70% recyclable. We want to get that up into the 70 to 90% range. And our reliability is on the order of 6 months, 6.5 months. We need to get that up to about 2.5 years. And so we really need the next generation of life support systems as well. So Mr. Gerstenmaier recently, last week, actually rolled out a plan to the NASA Advisory Council of what we would do in what we call the proving zone. That's out in cislunar space. You're days away there, but you can still have a supply chain if things go wrong. And his plan is basically a successive series of missions where we are able to stay longer and longer out there in deep space. And there'll be more coming out on that in the coming weeks and months, but that is what we have presented to the NASA Advisory Council in terms of how we move forward. So I talked about the fact that we humans are pretty needy, and if you're going to go out to Mars, you're going to need a big rocket. I would tell you about 4 or 5 years ago, a lot of folks were thinking, why don't we just use a whole lot of small rockets? And I think we kind of consistently said, no, things are going to get larger, especially when people get involved. And if you really look at just about industry, any industry from time immemorial, whether it's rail or whether it's planes or whether it's cargo ships, the trend they've gotten bigger, not smaller. Particularly if you have a complex architecture, the reliability actually goes up in your mission if you have a smaller number of things in bigger chunks. So this is your current fleet, if you will, of the new ocean-going vehicles. The ones on the far left are actually operational today, and you probably recognize a number of them, or maybe have seen a launch of these. This is in the largest capability we have today is about 24 metric tons. As you move over into the middle, these are actually in development today, and you see a couple of new entrants in this world as well. One really popular one these days is the Falcon 9 Heavy, and then you see a series of SLS vehicles beginning with the Block 1. The Block 1 capability is 70 metric tons to initial mass to low Earth orbit. And then once you add the upper stage, that takes you to 118, and once you add the advanced boosters, 130 metric tons. Our plan is to get to the Block 1B, the 118 metric tons, by the second launch, and we're currently developing the Block 1. And then out to the far right, you see some notional vehicles that have been presented that go even bigger than that into the future. So a little bit about the Space Launch System. This is the most powerful rocket ever built, and it is out of design and in build today, and I'll talk a little more about it. It can lift a payload up to 130 metric tons once you add the upper stage and the boosters. Because of that, I mentioned that it reduces the risk of missions, particularly long missions, and it also reduces the timeline. It also can be game-changing in terms of science and technology, and I'll show you some illustrations of that here in a second. And it moves us forward into an innovation economy. The rocket today is being built around the country, over 1,100 contractors in 43 states. 800 of those are small businesses. So if you look at kind of the payload capability here on the far left there, you see kind of the largest 5-meter fairing we have today, and there's a person down there, a little white shadow shows you the size of what a human is there. But when you start with the first construction of the 8.4 meter fairing there in the second. That's a conceptual view of what like a Europa mission would look like. And the really neat thing about the Europa mission for us, we see a big advantage is that if you take any existing vehicle today and try to launch it, you can't go direct. You've got to spiral out. It takes about 7 years to get there. With an SLS, you can get there in 2.5 years. And I actually worked the New Frontiers program and the New Horizons launch with Alan Stern, and it launched over 10 years ago. And we got together for the flyby 9 years later. And let me tell you, you get older. We both had gray hair this time when we saw each other. And a number of our colleagues who started out with us in that mission are no longer with us. And it really can make the difference in a mission when you're just getting started, or whether you're going to be there to see the science on the back end. And then you see kind of in the middle there, that's the initial configuration with the Orion. But you can actually put another payload up under that once you add the upper stage. And that can be anywhere from 6 to 10 metric tons. And so you can have a secondary payload even when you're launching an Orion. And as you move to the right, something you may be interested in, really large telescopes. And I'll zoom in on that capability here in a second. And then to the far right, once you put the 10-meter fairing on, now you're in the Mars class, and you can actually take those really large things you need to be able to get to Mars itself. And this is just kind of an illustration of what we're talking about. And this was done working with Dr. John Grunsfeld and some of our friends over at Goddard. But you can see on the far left of this picture, that's the Hubble mirror today. And then the second one there is the James Webb telescope. And I know we're all really excited about that. But as you move over to the right, you can see an architecture that's enabled by the SLS that takes it even another level. And you guys can do the calculations in terms of what kind of science that could enable for astronomy. With respect to mission capture, I mentioned a little bit about the ability to open up the outer planets, but this is kind of an illustrative. We use a term called C3, which is essentially the energy it takes to get somewhere. And if you see that orange solid section down in the bottom, that's all current. That scopes all current launch vehicles today. So that far left grouping of launch vehicles that I showed you on the previous chart. And then as you move up the screen there, the green is the initial 70 metric ton capability, the blue is the Block 1B, and then once you add the advanced boosters, the red is all the way up to the Block 2 capability. And then as you move across the right to the chart, you can see the various celestial bodies you're trying to get to there. And so you see, for example, out to Europa, for the Block 1B, you can get up into the 17 metric tons. So we currently are working on the Clipper mission, which is an orbiter, but if you want to land, it actually takes a pretty heavy payload. I think they're currently estimating the lander to be 16.9 metric tons, and you can see that Block 2 is about the only thing that can enable that size lander. So I'll just tell you a little bit about SLS. It's actually, as I said, being manufactured as we speak today. The engines for the first 4 flights are actually already down at Stennis and built. These are flight engines that flew on the shuttle. We have a new state-of-the-art flight controller, and that first flight unit has actually been put on the test stand, and we fired it here a few weeks ago. And so those things are doing great. The ICPS, or the Interim Cryogenic Propulsion Stage, which is our interim upper stage, is illustrated here in the bottom right. The flight unit is actually at Kennedy already. We've done all our qualification testing. We actually stretched the tank, and then we built the flight unit, and it was delivered a couple weeks ago. The boosters themselves have completed qualification, and we're in the midst of coring all the flight segments. I believe we had a gentleman here from ATK. He probably talked a little bit about that a little while ago. And then the core stage, which is our large new development, that's a 27.5-foot stage. It's down at, it's designed by Boeing in Huntsville. It's being, the big pieces are all being built in Michoud outside of New Orleans. All your major pieces of that core stage now have completed the welding process, and we're in the process of outfitting those things. We put the TPS on the tanks, and we put all the plumbing and the electronics in those sections. And so the qualification stages, where we actually build up a version of these things to structurally qualify them, will be shipped up to Huntsville. All those test stands now are complete, including one test stand for the hydrogen tank that's over 21 stories tall. It's almost the height of a football field. The barge that we used to push the core stage around, we actually took the old shuttle external tank barge, we cut it in half and stretched it 65 feet, and it's now longer than a football field. And that's just for the core stage. You see it represented by the Pegasus barge here. The machine on the left is the vertical assembly center. That is basically our most interesting piece of manufacturing equipment. The old external tank on the space shuttle took about 30 different stations to be able to make the external tank, and a lot of that welding was done in the horizontal. We now do all of that work with only 5 major stations, and we use what's called self-reacting friction stir welding. This machine right here is over 200 feet tall, and it's accurate within 10,000ths of an inch, 2/10,000ths of an inch. And the way we do it is we put the pieces in the machine, and then we have 2 weld heads that just go around with an operator sitting in a chair. We lift it up, and then we put another one in and do the same thing. And then when we're done, we pull the whole thing out, and we have an entire tank. It won't fit vertically in the building, so we actually have to build the 2 halves horizontally and then put them together. And then once we put them together, we take it out the back and put it on that Pegasus barge. The first flight when we build, we'll go to Stennis Space Center, and we'll take that entire core stage and put it up on top of the B-2 stand. And when we do that, it will be, I believe, the 2nd tallest structure in the state of Mississippi. I think if it were in New York, we wouldn't stand a chance. See, I'll also mention that the avionics are all those avionics boxes now are through qualification, and we have a facility in Huntsville where we call it the sill. We take all of those pieces and we put them around in a mechanical structure that simulates the full diameter of the core stage, and we put the full length wiring to make sure we have all the right line loss and things like that. And so we've done that with development units, we've done those with qualification units, and now we're populating with flight units, and we're on our last version of the software now. We're actually testing with the flight version that also has a subunit that is to do the test at Stennis. And so we're moving closer to launch. We've been working really hard. All these pieces are being put together, and we're looking forward to shipping the rest of this down to Kennedy and kind of turning it over to them, and then they stack it up and get it ready to launch. So a couple other things to consider here is that, as I said, Mars is really hard in a couple of different ways. From a technological perspective, there are a lot of different technologies that we're going to continue to push as we move into the future. One of the problems that we haven't completely solved is in-space transportation to Mars. And so there's a lot of different trade studies out there in terms of what we might do. The current thinking is we're going to work on solar electric propulsion and kind of scale that up. But one of my personal favorites is nuclear thermal propulsion, and so I'm pretty bullish on that. We've been working on that at Marshall Space Flight Center for a long time now, and we think it's very efficient and reliable, and it's really good for pushing the crew out to Mars. On the left, one of the other things we have to work on is making things less expensive and really changing the industry thinking in terms of how you make things. What you're looking at there is a 3D printed turbo pump that we have actually built and tested. We built it in a very short period of time. We put it on the test stand. We spun that turbo at 86,000 RPM. That's actually 3 times faster than the Space Shuttle main engines. And we put 20,000 pounds of thrust out the back end. A lot of folks are hearing about additive manufacturing, and you know pretty much anybody can purchase one for their desktop, but there's not a lot of folks out there that are doing it with high nickel alloys and doing it with the kind of tolerances it takes for turbo machinery and things like that. So we develop these things, we push it out there, we have different vendors around the country that build the parts, and that kind of moves the industry forward. And then we work on things like the standards. What's it going to take to be able to certify these things to actually be used in rocket engines that push humans around? We also are interested in composites. We believe that as you move into the future, composite tanking and things like that are going to actually make the rocket lighter because of a thing that if you're a fan of this kind of stuff, my favorite astronaut talk is Don Pettit talking about the tyranny of the rocket equation. It's really hard to get anything up into space because of that stupid equation. And if the Earth was a little bit heavier, we wouldn't even be able to get off the planet. And so we end up having to be very efficient and push the limits of the materials and the processes and things like that. Composites are better than metals, but we have to push those into the future. This is actually one of 3 machines in the United States that can do very large laydown of plies. You can actually customize your thickness as you go across the parts and do it out of autoclave and do large structures in very complex shapes. And so we believe this is also going to be kind of industry changing. We also think that this is where the commercial airplane industry is going in the future as well. So we don't just do rockets at Marshall. As I said, we've got a long history in science, and so we recently competed in a small Explorer class mission. Marty Weiskopf, who's actually the project scientist on Chandra, was part of this team. And it was announced over the Christmas break that we won the XB mission with our partners Ball out in Colorado. This will study some of the most energetic phenomenon in the universe. And again, you guys know more about this than I do, but like supermassive black holes and magnetars and things like that using X-ray polarimetry. There's a technology in here that we are kind of best in class at using. It's infinite grazing optics and things like that. So we're really excited about this. We're just getting started. We've assembled the team, and in a couple of years we're going to get this one up and flying and start really getting some really interesting science out of that as well. So I know we're at a community college here. I don't know how many students are in the room, but I will tell you from a NASA perspective, We've got a lot of folks that will be retiring in the next few years, and we're looking for you. We believe that there's a large untapped resource out there in this country, especially in minorities and females. They don't tend to choose engineering and STEM as much as the more traditional folks out there, and so we are looking to hire, and so you see here that we're really interested in getting you into NASA. We think that folks like me are getting old, and I'm going to be beer in hand, toes in sand here pretty soon, and we need that next generation to come in. So I think with that, I'll tell you that you can't spell Marshall without Mars, and it's funny, it took me a few years to even notice that. So with that, I think I'll just take any questions you might have. Thank you for having me today. Yes, sir.
How is the federal hiring freeze and the coming budget discussions affecting?
Yeah, so the question was, how is the hiring freeze and the coming budget discussions affecting us? The hiring freeze is having an effect. We definitely have needs. There is a caveat in the hiring freeze. In certain areas for critical skills, you can appeal to the administrator. And at Marshall, just like the other centers, we've actually done that. And almost all of our appeals have been accepted, and we're moving forward on those for the things that are critical. I will tell you that this is not the first hiring freeze we've had in the federal government. I think it's the fourth. And I'm hearing that it may be lifted in the near future. So I don't think it'll have a long-term effect. If it was long-term, we might start thinking about how we do things differently. Most of the centers do have a support contractor workforce that can augment. The only problem with this particular one is it says you can't hire support contractors with the intent to actually replace the civil servant job. And so you might end up having to think differently about certain things you do. But I'm not hearing any panic or any real serious concern unless it goes long term. With respect to the budget, I don't know if you've been paying attention, but I'll just say in general, the NASA budget is always in a tough spot because we are not military and we are not entitlements. We are part of the discretionary part of the country's budget, which means we are in a pool of folks that are really what's left over after the big things are taken care of. We're kind of the tail of the dog. The good news is, out of all those agencies, NASA was actually least impacted. We had about a 0.8% reduction in our budget. Other agencies we saw in the 20s and 30% reduction. And so even 5 years ago, when I was first putting together the SLS program, we told the teams flat is the new up and down is the new flat. And so we're kind of prepared for that. But I would also say that the way this works is it's a multi-part process, right? So the administration proposes a budget, and then it goes over to the other end of Pennsylvania Avenue, and then Congress disposes of that budget through ultimately an appropriations that the administration signs. The good news for NASA is that we think we have strong bipartisan and bicameral support for almost all of our programs. I just saw this week where 144 congressmen and about a third of the Senate signed support letters just in this last week or so. So I feel pretty good about it in the long haul. It's a good question. Yes, sir.
We have equipment that can make it to Mars. How about the human factor? Has that kept pace with the physical challenges of deep space exploration?
That's a good question. So the question was, we have equipment that can handle it, right? So the robots can handle deep space, and we designed them specifically to be able to do that. What about the human body? The human body is affected by deep space. The body changes when you go up into space. We have, of course, had permanent human presence on the International Space Station from a zero gravity perspective for over 15 years now. And we have done a lot of study of that. Some of the studies have shown us there are things to be concerned about. Other things have actually taught us how to counter some of the effects. So, for example, when we call it countermeasures. So, for example, your exercise regimens and things like that actually can counter bone loss. One of the ones that we're concerned about is optical generation we're seeing in some of the astronauts over time. The big one when you want to go to Mars is radiation. That's one that's a bit of a concern to us. So you have to have some way of protecting yourself from that radiation. There's some pretty basic kind of things. So, for example, water is a pretty good protector of radiation, so you can put all your water bags around you, or polyethylene. I mentioned additive manufacturing. One of the interesting and strange partnerships we have is with the Army Research and Development Center and Caterpillar. They actually have been developing the ability to take a robotic 3D printer and take sand in the desert and actually make 3D printed Quonset hut type things. We would like to see something like that on the moon or Mars when we put humans there, because that regolith is a natural radiation protector when you get there. And so it's one of those technologies that I think will push the limits of what we know. That risk is there, but it's not something that I think we should shy away from ever going into deep space.
Thank you.
Good question. Yes, sir.
Yes, we are talking about the exploration to Mars. What role is taking the private sector in?
Good. So the exploration of Mars, and what is the role in private sector? So the private sector, truly private sector, can do just about anything they want if they can get an FAA license to launch, right? So that's a, yes sir, to follow?
My question is because as far as I know, there is a company in Costa Rica who is working with Astra. I don't know if you are familiar with that.
At Astra, yeah.
With a plasma rocket, we reduce...
Vasimir.
Yes, Vasimir, we reduce the time to go to Mars from 6 to 8 months to
It
45
could.
days.
That's right. So the statement was Vasimir in Costa Rica is working on a type of propulsion that could theoretically reduce the time to get to Mars down to 32 days. Now, one thing you have to note about that is that in order to actually make that work theoretically, you have to have a very powerful source of power, like a 12 megawatt nuclear power source. And 12 megawatts is a lot of power for a nuclear power source in space. So we are interested in nuclear reactors for space. I'm interested in nuclear thermal propulsion, especially. But so the question was also about private sector.
Yes,
right?
And also, as far as I know, the NASA set with the Astra working to send a small scale rocket to space. I don't know if it's sending already and they are testing. Do you know something about that?
Yeah, I don't know about a flight rocket to space. I do know that we have funded some work. I know that the previous administrator actually flew with the gentleman that's working on that, as well as a senator from Florida, and they are both very bullish on that as well. So that's an interesting technology. Anytime a technology comes along and changes the way you think about things, it's something that could change our future. By the way, that's also one reason you don't want to get too defined in how you're going to do things, because the world changes and you may want to have on-ramp and off-ramp. So that one's one we're going to continue to watch. We think it's a very interesting thing. The scaling that up and getting long-term runs are going to be important to prove out that technology. That's a good question. Yes, sir.
When do you personally think that humans are going to get on Mars?
Did you say when? Yeah, so first of all, best shirt in the audience. It's the NASA meatball, but it says nerd. I've got one that says TRKY, and I actually thought it meant Trekkie, and I wore it to Comic-Con a few years ago, and somebody told me, no, that it's actually the company name, which is Turkey. And so I was walking around with a NASA Turkey shirt. So the question was, when do we think humans will get to Mars? Our current plans get us into the Mars vicinity in the 2030s. A lot of these problems still have to be solved. The private sector may have enough money to be able to do it on their own, and we'd love to see that too. So far, most of the money is still government money, and as I mentioned, go back to question 2, we still have to compete for our budget with a lot of other things that are important to a lot of people. The good news about NASA money is that just about every dollar you put into NASA, in my opinion, And I think some data shows you get a return on investment. You actually get a positive return in terms of innovation, in terms of scientific knowledge, and in terms of getting guys like you interested in STEM. And that's what's going to push us forward is the STEM field and innovation in the future. Yes, sir, up here in the white hair.
Yeah.
With your hand still up, sorry. It's hard to see from here with the lights.
Can you comment on rocket reusability with regards to Marshall? I noticed a lot of the commercial companies are really starting to talk that up and do it.
That's good. So the question is about rocket reusability, and you said within Marshall. So a couple things. You might not know this, but actually Marshall is supporting most of those companies out there. The way that works, we have, since our creation, the ability to have what we call Space Act agreements. And we have them with just about every new space company. And because we have an engineering directorate that has 1,300 folks that are very specialized in things like this, they tend to come to us, particularly when they have problems. And so we're pretty well versed in what's going on out there. With respect to reusability, a couple things. I've got my own opinion about it. And I think you have to pass some gates. First, you have to be able to do it, right? You have to be able to launch something, bring it back down, and launch it again. Secondly, you have to be able to prepare it to launch again at a price that is low with respect to building another unit. Third is, for that to be a business case, that price has to be sufficiently low to have a return on investment, which means you probably need to do it, the more times you can do it, the more that makes sense, and the actual amount of money it takes to refurb it. Fourth, you need to be able to do it, either sell them at a much cheaper price when you fly them again, or keep your reliability high enough so that your insurance costs don't get so high, or your reliability goes so low that you can't be used. And then I don't know if I have a fifth. So a couple of companies out there. Another thing I will remind you is that Space Shuttle was mostly reusable. The only thing we actually threw away was the external tank. And a lot of folks considered that to be a very expensive prospect. One of the things about the shuttle is it was originally designed to fly between 30 and 60 times a year, and we never achieved those rates. One of the reasons was it was a lot more expensive to refurbish that and get it ready to fly again than we originally thought. On the SLS, if you noticed in the architecture, we're actually using essentially the same booster design that we used on the shuttle. We just added an extra segment. But believe it or not, I made the decision not to refurbish the boosters, right? We could bring them back and refurbish them because the cost of refurbishing those boosters is about $75 million a year to maintain the infrastructure it takes to go out and get them, to clean them out, strip them down to bare metal, and use them again. Plus, we had about 16 sets of boosters already in our stores. So what it comes down to is, if you're not launching very often, so people might go, why isn't the big rocket reusable? It comes down to how often do you fly, and how much does it cost to fly again? So what we're seeing in the new space area is, and this was kind of cool because I just flew in from Denver where Blue Origin's had their New Shepard, actually the flight unit there. And it's a pretty interesting thing to look at. So it's gone up above the Kármán line 4 times now. And they've said that it's hundreds of thousands of dollars to refurbish that and fly again. That's a really interesting thing, and that may be something you put some humans on top of that thing. You maybe beef up the propulsion a little bit to be able to handle that, and you may have a business case there. And then, of course, now we've seen SpaceX now has put an orbital satellite in orbit and then brought one back down and landed a stage again. So I think time will tell if that's actually going to be a good business proposition in the long run, and if the cost will stay on, we'll keep the reliability down. I think we're kind of in this 2 and 3 now on that technology, and I think it could be game-changing in terms of the satellite market. I think you'll know that it's game-changing when the prices come down low enough to where we compete against the other things that are out there, the other countries that are doing in that market, and they start coming to us and using us more and more. So that'll be your first indicator, right, that it's actually a moneymaker. but it's a good question. Yes, sir.
Yes, in 2001, at the Paris Air Show, there was a panel on the future of space exploration. And the European Space Agency had a plan to orbit an IP node around Mars around 2008 or 9 in order to have the rovers just send the signal to low Mars orbit and then have the node send the signal back to Earth. Has anything happened with that, or is there still plans to orbit an IP node around Mars?
I don't know. So the question was, in 2001, ESA at the Paris Air Show showed a plan for IP nodes around Mars and relaying.
So that the rovers wouldn't have to send a signal all the way back to Earth.
So the rovers wouldn't have to send a signal all the way back to Earth. No, I don't know. I really don't. I wasn't following back then, and I don't really know that program. So I don't. I know we're working on some interesting laser comm is a really interesting way of getting things back to Earth in high bandwidth and with a lot less infrastructure to be able to do that. But I don't really know. Yes, sir.
Talked about the lunar stage. You know, the getting out of the Earth, and talk about the moon being part of the progress to Mars. Can you talk a little bit more about that?
Yeah, so the initial idea is that you have you first really establish the ability to put humans back into deep space in some form in the cislunar space with an Orion module and perhaps a logistics module and an airlock and maybe some docking ports. The idea there too is that you also expand the opportunities for international partnerships there, so that the architecture or commercial ventures could also partner as well. But it also becomes a place where when you get ready to make your deep space transport, you can dock up to that and get prepared to make the journey from cislunar space out to the moon and back. So the current thinking is that deep space transport is actually a back and forth type capability cislunar space, and then you come from cislunar space back to the Earth. More to come on that. Yes, sir.
Are you planning to send up water, food, voice, and take it to Mars?
So the question was, are you planning to put water and food and oxygen before you go to Mars? I don't know all the details, but I know if I was going to land on the surface, I'd probably want to know that the things that are there and ready to support. I actually had the opportunity to have breakfast with Buzz Aldrin in Italy about 3 years ago, and I asked him this question, and he said, "Well, I'd actually like the bacon frying on the surface." And by the way, we talked a little bit about commercial space. I think obviously one of the things, just like on the space station, is we're going to need a logistics supply chain once humans get out there. And so as a minimum, we see that as an opportunity for deep space commercial services as well. Yes, ma'am. Okay, so the question was that in the early chart on exploration, that historically exploration has been compartmentalized country by country, and the question is that something we might could see overcome? I don't know. I'm not a policy person, but I will tell you that one of the things Dr. Ochoa, who runs Johnson Space Center and is in charge of all the astronauts, said this week at the Space Symposium was that as astronauts have gone to the International Space Station and cosmonauts as well, and astronauts from a lot of different countries, when you stay up there for very long, it starts to change how you think about yourself in the world. You actually start thinking of yourself as a citizen of the world. And if you just think about it, you're looking out that window every day, and every 90 minutes you're going around the Earth, and you're not seeing the borders and things like that. You're seeing a blue planet. And so I really I think if you were to ask just about any astronaut who has gone to space and stayed there for a long time, they would tell you that they think that vision is a great vision. The other thing I'll tell you about the International Space Station is, as tough as relations are right now, kind of around the world, that thing is continuing to operate with no issues. And by that I mean Americans still go to Kazakhstan and Russians and Canadians, and they launch in Kazakhstan up to the station and come back down in the interior of Russia. And so it's a really interesting model with respect to international collaboration. And it can continue to be such as we push out into deep space. I do believe as we move into deep space, we'll see those collaborations. And so in some ways you could say, I mean, that is the frontier right now for humans, and so we are exploring together today internationally. And I want to say that Ellen said, don't quote me on this, but something like 75 countries have been involved in the International Space Station, either through sending up people or payloads and scientific experiments. One of the things we do at Marshall is we actually operate all the scientific experiments 24/7, 365, and we've got about 25 flags out in front. Right there on Redstone Arsenal in Huntsville, Alabama, you have flags of all these nations. That's a good question. Yes, sir.
About interstellar travel, there was a lot of talk about the Russian oligarchs paying some money, investing into microprobe that's going on.
Yeah, small probe that you shoot a laser at, right, to accelerate it out into interstellar.
On that regarding NASA at all?
I don't know. I know that Pete Gordon, formerly of NASA, was involved in it, so I don't know that there's a current NASA involvement officially, but there are certainly people, from retirees from NASA that I know are involved. It's a pretty neat mission. It'll be interesting. It raises some interesting questions, right? Especially if you've seen the movie Interstellar. I actually watched Arrival on the plane coming in. I really enjoyed that. I'm sure you guys have seen all those movies. Yes, sir.
You had that graphic early on that showed the various, there were 3 phases of developing those vehicles. Is there a more definitive timeline on when some of those that are under development now will come online?
No, and it's really hard. I got a good feel for the 4 you saw to the left of the middle. That's the SOS development and how that'll come along. Some of the others, it's notional, and in the private industry, you can really say a lot of things. You can say, I'm going to do something for $1.99 next week, and so and then you get a tracker behind you. So I don't want to say because I can't.
What about the ones that are going to be coming online? Are we looking at those?
That's hard to say. So I'll just pick one. Falcon 9 Heavy. We've been anticipating that one for a long time, right? And so I don't know when we're actually going to see them, and that's not up to us. That's really up to the private company to decide when and how those kind of things come along. And then other areas, we like I said, we have a lot of folks that are helping in that world, and so we know challenges and things like that as well. That's all I can tell you is they're in development and they're moving forward. Yes, ma'am.
Hi. In your presentation, you mentioned how you're looking for the next generation to come to Marshall and to NASA to help with space
Absolutely.
exploration. What would you say to those children and young adults who are in our audience today, as well as to teachers and educators who can inspire them and encourage them? What type of skills and knowledge do they need to become the next staff?
So to the folks that might want to come work for NASA, you kids out there, first to inspire you, I will tell you that it was really inspiring to me to sit at a table with 5 other center directors this week and hear everything that we all have going on. And the kind of wrap-up comment that we all said was, we are so excited to be part of the agency at this time. And I rattled off a few things that are just about to happen. But as we move into this next phase, it is really exciting to see how we're going to be pushing the frontier, both robotically, through the photons we're seeing through bigger telescopes, and from human presence out into deep space. In terms of skills, I would say any type of engineer. I'm a materials engineer by trade, and so materials and processes are really important. Any material, anything that has mass and occupied space is a material. Anything you do to it is a process, and you are pushing the limits of both of those when you're pushing out into deep space. Computer engineering. We have over 3,800 people that do avionics and software and things like that, and that's going to continue to be important. I think I heard at one time the Mars lander mission had over 1 million lines of code. If you are an aerospace engineer, especially doing things like just to get a big rocket up off the ground, but if you're going to try to land it again too, that's really interesting. If you're going to be coming in from deep space, there's some interesting problems associated with that as well. Mathematicians, big data, that's a really interesting one these days. My son is actually in business analytics, and he does that. Now the big thing is to take different types of data sets and lay them over each other and watch for patterns to emerge. Even doing predictive analytics is really interesting. Those are just a few, and if you're a scientist, an astronomer, right, when we get James Webb up there, we're probably going to need a whole new generation of those folks. If you are a life sciences person, we talked about the effects on the human body of being in deep space. That's going to continue to be a discussion. Even the ethics of things like that. If you're in policy and law, this question about who does deep space belong to, and are we going to have international fights over territory and things like that. So just about any field. I mean, we have accountants. We have people that count the money, right? And we have lawyers because there's a lot of legal issues associated with some of the things we do. So just about anything, but particularly STEM fields. That's the one where we really worry about, are there enough kids staying in STEM? That's why we do the robotics challenges. At Marshall, the last 3 weeks in a row, and I'm actually missing it today so I can be here, we had the Regional Robotics Challenge, we had the Human Exploration Rover Challenge, used to be called the Great Moon Buggy Race, and then this week we do Student Launch Initiative, and they're launching rockets up to trying to hit exactly a mile. And that's part of trying to keep those kids really interested in STEM. So, great question. Yes, sir.
Can you give us an update, a little more information on the Webb telescope? What vehicle it'll launch on? When next year?
Okay. So it's not my world anymore. I worked in that world back when it was going to launch in 2013. It's going to launch on an Ariane out of Peru, South America. I think it's still on track for 2018. I think it either is about to go or has already arrived at Johnson Space Center to do some vacuum testing. The only thing that we're kind of close to in Huntsville, all the mirrors came through Huntsville actually to our XRCF, and then a small company, a small business in Huntsville actually built all the thermal blankets that go under the bottom, and they've delivered all those units to Northrop Grumman for folding and integrating. But last I heard, it's on track and it's looking good for a launch next year. Yes, sir.
Your slide says the journey to Mars. How about the journey from Mars? And how much vehicles are we going to need? Even though we tested it last week, we had humans there trying to get them back.
Right.
If that's the case, can we start testing those now?
That's a good question. So the question was, how about the journey from Mars instead of just to Mars? And can we start testing those rockets now? So the Mars mission, the Mars Sample Return mission is kind of the next thing to do robotically. There's an ascent vehicle that needs to get that sample up off the surface, and our folks are working with folks at JPL and headquarters on a hybrid type of propulsion to bring that up off. And yes, you can do that robotically before you ever send the humans, for sure. It's a little further down the road. I'd love to have that problem right now in front of me. We still got to get the lander, and we got to get the transport and things like that. It's a multifaceted problem. Yes, sir, over here.
Could you comment on the process of landing, what the latest thinking is?
I don't know. The only thing I can tell you about that is when I was working with JPL in some of the Curiosity in Phoenix, and when I was deputy head of science, I remember them telling me that the Mars Curiosity rover was kind of close to the limit of our current technology of what you could land on the surface, that you really got to bring on a new type of technology. For example, SpaceX is working on with the supersonic retro jets to be able to land in their Red Dragon concept. That could be a possible solution there, as well as aero braking and things like that. And so those are some technologies I think that we're going to have to develop. Mars is hard. It's a hard problem because the moon doesn't have an atmosphere. You're basically just slowing down to a docking there. But when you have all this atmosphere and weather and things like that, to me that's really going to be the most tricky part. And on the moon we were only there days, but when you go down to the surface on Mars with all that weather and everything, it's going to be a challenge. To go in 6 months later and walk over to a vehicle, get in, and trust that everything's going to light up and do what it's supposed to do. Yes, sir.
Could you talk a little bit more about the nuclear propulsion systems that you had mentioned?
What would you like to know?
I mean, when they might be tested, will they be tested?
Yeah, currently at Marshall we have a thing called N-Trees. It's basically a thermal simulator. And what we're trying to do is to see how the hydrogen reacts when you run it through those temperatures. What I would like to see is a program over a couple of years to kind of even the playing field with some of the other things that we've been looking at. I'd like to see maybe a zero energy reactor built with some state-of-the-art technology. And I can't say a whole lot about that yet, but we've been looking at some things. And then I would like to get a simulated reactor test with the tankage and everything down, say at Stennis at some point in the next 3 or 4 years. And so we have some ideas around that and how to advance it. It's like anything else, it's going to be one of those things that you have to go up to headquarters and justify it, and it's got to compete against the other things we're doing. But it's one that I'm very interested in myself. I also think low enriched uranium and maybe a manufacturing technique around that might be a good thing. I hear a phone. I hope it's not mine. Yes, sir.
Is asteroid impact avoidance at all part of fun on your radar in the Marshall Space Flight Center?
Asteroid impact, so is that on my radar? I would love for that to be on my radar. I'd love to build an SOS to go, solve that problem. I don't know that where ARM is going to end up in the future, which was kind of an asteroid capture mission. I'm not working on that problem every day. I will say, in general, there's the community that looks at space debris and things like that is I'm seeing a lot more interest in that in the last couple of years, for sure. Yes, sir.
What about the concept of a space elevator? That's something that's
The question was a concept of a space elevator. We don't have a lot of people actually working on that one right now. I did see a week or two ago somebody announced it was a UAE announced another country talked about maybe doing a space elevator, suspending it from something in space. I think working it back from the other way. Yes, sir.
Could you talk a little bit more about the space debris around Earth and how we plan to clean it up?
I'm not an expert in it. I've only heard a few different types of concepts, and there are several different ones. One involved for large objects actually coming up and using the celestial dynamics to actually be in an orbit to be able to actually come around under it as it went around in the orbit, and then you have like a net type thing, so that by the time you come back around the other orbit, you've gone around the object and you net it up, and then you use a propulsion station to bring it down. Another one that I've heard about just this week was very large structures at the equator that are maybe the size of a football field with something like a Whipple shield, because almost all the LEO stuff, everything, unless you're going at the equator, comes through the equator. And so you put a series of these things around the equator itself.
Different nations finally come to an agreement on how they're going to keep polluting space connections.
That's above my pay grade. So you talk about private space. There's a lot of folks that make money cleaning up stuff that other people do, right? So, there may be a market there. And I'm only partially kidding, right? I mean, some of that, is strategic, and there are assets you don't want to be harmed, but there's a lot of telecom companies up there that don't want their assets harmed either.
It must be difficult just to launch and make it cool.
Yeah.
It must really be.
It actually is. There's a model that JSC uses called ORDIM, and I think they're using ORDIM 3 right now. And believe it or not, one of the big contributors when we do a human launch on SLS is the predictions of debris impacts on the backside of the ICPS due to the debris in low Earth orbit. So we actually have to take that into consideration when we design our trajectories. That's a good question. Yes, sir.
So given that SpaceX is the only other entity talking about going to Mars, taking humans to Mars, what do you think of their plan? Elon Musk announced it a few months ago.
The MCT plan down in Guadalajara, I think. It's ambitious, I would say that, and it'll take a lot of people to solve a lot of problems to make that work. Anytime, my chief engineer says anytime you try to light more than 10 things to get off the ground, it just, it's not something he would recommend. So I think that challenge is going to be a difficult one. You'd have to have graceful failure of things if you have a whole bunch of engines launching. And I could just tell you, scaling up to 27.5 feet across is one set of challenges. You go up to the type of diameters you were talking about there's a whole different set of challenges as well. But the idea, I think, is really good, and I think it keeps a lot of us focused and dreaming about the future and what it could be, and if nothing else, that's a great thing for all of us. Way up there, and I've got like 2 minutes, I think. This guy with his hand up there in the corner.
So you mentioned using composites for reduction of weight. I was wondering if you could speak to potential benefits, other potential benefits and challenges for that material class in dealing with the environment of space and what it has to do to get up into space.
Okay, so the question is around composites and other potential challenges and opportunities. I'll just say for the boosters, if we stay with solid boosters, we think going to composite casings you can actually increase the internal pressure you use and lower the mass of the booster itself. And so one of the concepts for advanced boosters uses composites. The challenge with composites is damage tolerance, and also if you know whether you've damaged it enough. One of the things we did early in the program when we were really looking at the future boosters, we actually spent some money on a program called A Better. We built a composite tank, and we took it to burst failure, and it burst at 3,600 plus PSI, which is more than double the operating pressure that we would like to see. The other is we took about a 1-inch spherical ball bearing thing, and we put it on a pendulum and swung it in and banged it into the tank before we did that test, and to see if it would reduce the burst pressure, and it still went up to 3,600. So, but damage tolerance is the thing you have to worry about. I think I'm out of time. I got 36 seconds, so I appreciate your time.
I don't think so. Try knocking, maybe one of those guys will win. Otherwise, you're jumping around.
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, welcome everybody back. Wow, we have a really great audience here. Have a seat there. Well, welcome. Are you having a good show here today? Really good? My shout out to you now on this one. Thank you very much. So our next speaker, you're going to be absolutely thrilled with our next speaker. She comes from the Massachusetts Institute of Technology, a professor. She's a planetary scientist. She has been dubbed by NASA Quest as the Indiana Jones in exoplanet searching. She has received numerous accolades and awards. It is absolutely my pleasure, and I am so thrilled to have this presenter here today. Please give a loud and warm welcome to Dr. Sarah Seeger.
Hi, everybody. Well, my first question for you is how many of you have been to a truly dark sky? Great, that's what I was expecting. Actually, I was expecting 100%. Well, I'm here to tell you about exoplanets. And the next time you go out and look up at the night sky, that'll probably be tonight, you can wonder about the stars out there and whether or not there are planets around each of those stars. To get started, to help you understand what is an exoplanet and how many there are, I have this animation called Eyes on Exoplanets. Actually, it's a software you can download, so you can go home later and Google Eyes on Exoplanets and download it. And just excuse me, because this animation clip that was made from the software, it goes really fast, so I have to talk super fast to get through it. So it starts out with this illustration of our galaxy, but quickly zooms in to a real map of our sky. All those highlighted stars, yellow and red, are actually stars with known exoplanets. And in fact, the software also has a spacecraft that orbit our sun and satellites, and you can actually go anywhere on Earth. And here it takes us to the west coast of North America in the spring night sky. And if you click on it, you can actually see the stars outside at your night that have known exoplanets. Put the constellations out, zoom around. Actually, it takes us to a very special patch of the sky. Does anyone know what that patch is? It's actually a special place where a space telescope, Kepler Space Telescope, stared at one patch of the sky for about 4 years and found so many planets. Now, if you know the name of a favorite planet, you can type it in. And this one is Kepler 186. So the software takes us to the star, and look, there are 5 planets around that star, and these orbits are to scale. It also, you can click on this menu and find the so-called Goldilocks or habitable zone, a region around the star where a planet as heated by the star would be not too hot, not too cold, but just right for life. Here it goes a little too far, and if you can read the fine print, it says, hypothetical visualization of planets. So we can't see other planets around other stars like that. But I wanted you to be able to see this night sky software and just appreciate just how many stars out there have planets. Now, one thing is that most of these stars, you need your binocular to see the star at all. And of course, with your naked eye or most of your telescopes, you wouldn't be able to know that there's a planet there. So one thing about these planets, we don't know too much about them. So just for this introductory part of my talk, I'm going to, can I just get some help clicking this forward? It's a little sticky. I actually am going to tell you a little bit about some of the exoplanets. It doesn't want to get out of the animation. There you go. So remember that planet Kepler 186f. So NASA made some travel posters to help us think about exoplanets because we can't yet go there. This one says Kepler 186f, where the grass is always redder on the other side. Experience the gravity of HG 40307G, a super-Earth. This is imagining an exoplanet, this particular one, that is more massive than Earth, that has a more higher surface gravity. So if we could go to that planet, we would have a lot of trouble walking around. Relax on Kepler 16b, the land of two suns, where your shadow always has company. And it's one of a number of different planets known that has two suns. The planet orbits two suns. Oh, they're gas giants. I'm absolutely sure there are also terrestrial planets out there orbiting two suns. We just haven't been able to find them yet. And so what I always like to say about this particular system science fiction got some things right. So for our exoplanets, I have now just a little bit of a more quantitative, although somewhat out of date graph to show you. And this is showing you a large number of the known exoplanets. Each dot represents a different planet, showing you its size as a function of its orbital period. And this is what we call on a logarithmic scale. It covers a vast amount of area. You can see a line showing you where see if I can, Earth would be at 1 Earth radius. And we have a Neptune size, Jupiter, etc. And these are orbital period in days. So Earth would be about here. In this dark part of the diagram, it's fair to say that our telescopes, no matter how sophisticated, can't reach to that part of the diagram yet. The other thing I want you to see is that just how many planets there are. And they actually come in all masses and sizes and orbits. It's just phenomenal that, in fact, we have not found a solar system copy yet. Our solar system turns out to be very hard to find with any planet finding technique. Can you see where this diagram is most dense, where there are the most planets? The most common type of planet? It's not a very scientific approach, but nonetheless, you can see where it's all dark there. That's because all the planets are overlaying each other. The most common type of planet we know of so far are planets about 2 to 3 times the size of Earth. They're smaller than Neptune, but larger than Earth. And believe it or not, we don't know how these formed, or why there are so many of them, and there are no solar system counterparts. So when I see this diagram, I like to think, in exoplanets, anything is possible. So just to conclude this introductory part of my talk, what is an exoplanet? A planet that orbits a star other than our sun. We know of thousands of exoplanets. We don't know a lot about most of them, their masses and orbits. We know about multiple planet systems. And we know just how bizarre these other worlds might be. So to make progress, that's what my talk is about today, is to tell you a bit about what's going on and where we're getting. And so I'm going to divide my talk into 2 parts, a 2-step approach to finding a habitable world. The first one is with existing telescopes or those under construction. You've already heard more than once about the James Webb Space Telescope, for example. And in the future, I'll be talking about new space-based facilities. And while you're wondering what I might mean, you can browse the props we've brought up, and I'll get to that in the second part of my talk. So to start with, here is just an Apollo image of Earth and our sun, not to scale. But I wanted you to know that actually for educational and popular astronomy purposes, we're very lucky. Our Earth is approximately, just approximately, 100 times smaller than the sun. It's 100,000 times, actually it's 100,000 times less massive than the sun, and about, unfortunately, 10,000 billion times fainter than the sun. So if you were going to set out to find another Earth, which technique would you use? One that involves a planet size? You're talking about 100 times smaller, or 10,000 times in area. Mass, which involves about 100,000 times smaller. or 10 billion. Because you know, our Earth isn't necessarily so hard to find. The problem is it's right beside a big, massive, bright sun. So anyone want to guess? 100, 100,000, 10 million. Well, the way we find most planets today is by size, because that's the easiest way we have. And here's a little animation to show you. You see the little planet going in front of the star? It's supposed to be the size of Earth going in front of a star the size of our sun. But what we're doing as astronomers is we're looking at that bottom graph. We're looking at untold numbers of stars, thousands, hundreds of thousands, probably a million stars, looking for a little tiny drop in brightness. I want you to imagine that you're out there with your telescope, or actually would be out there robotically, taking an image of the sky every few seconds or every few minutes, over and over and over again. And that's what the Kepler Space Telescope did. That's what a lot of astronomers in the professional community are doing with specially made telescopes. And we're just looking for that tiny drop in brightness to find planets that go in front of their star. So in that particular case, there's whole tons of information in this light curve. If you can measure this very precisely, you could learn the density of the star. You could look for moons as well. You could look for multiple planets by the different shape and depth and duration of the planet light curve. Believe it or not, in astronomy nowadays, you can do an entire PhD just on subtle factors in the planet light curve. And you can have data good enough to pull incredible things out. Now I'm going to get to some real data. And how many of you have heard of the TRAPPIST-1 planet? So the TRAPPIST-1 system is a breathtakingly amazing planetary system with 7 planets. So I'm going to give you a little more insight into it by showing you this data. It's hard to believe that this created such a huge attention in the media. But this is actually what it was, what we saw, astronomers saw. And what this is showing you is a data set taken from space. So it's no longer you imagining yourself in your backyard with your telescope and your camera imaging a star field. It's now a telescope in space called the Spitzer Space Telescope, which, if you haven't heard of it, we sometimes think of it as Hubble's infrared cousin. It works in the infrared. It's in an Earth-trailing heliocentric orbit. And the good thing is it doesn't have a day and night, because it's out in space far away from Earth now. And this data, if you can look at the bottom, which is time, it's taken over 21 days. So 21 days and 21 nights, a space telescope stared at one star. This telescope's about 80 centimeters in diameter, its aperture. And what you can see is look at the y-axis, or the relative brightness, normalized to 1. You can see it's very precise photometry. So we're measuring the brightness time after time, minute after minute, essentially. It looks like there's some gaps in the data when the telescope wasn't working. But can you see the transits here? They're actually all squished together now. But these transits typically last an hour to a few hours. And look at them. Actually, they're all marked for you by those color curves. Well, if you were to take this data, oh, by the way, do you see a rise? Does anyone know what this is? It's like the opposite. You guys are good. Some people said it's a flare. We'll keep that in mind for later. So if we could take all this data and spread it out and overlap all the like transits, that's what we get, is this TRAPPIST-1 system. And if you look at the plot on the left, you can see the different planets, TRAPPIST-1b through 1h. And they all are showing you a slightly different shape. The ones that are closer to the star, they're by Kepler's third law, are orbiting the star faster, so the transit is shorter. And the ones further away have longer eclipses. The depth corresponds to the planet area, and from knowing the planet, the star's area, we can extract the planet size. So the size so you can admire the data for a moment. It's truly amazing that there are so many planets all orbiting the same star. But what you may not know, or might have forgotten, is the TRAPPIST-1 star itself. And that star actually is shown in the cartoon picture, right beside Jupiter. And can you see our sun illustrated in that same picture? So look how small that star is. It's barely bigger than Jupiter. TRAPPIST-1 is so small and dim and cold. If it was any smaller, it wouldn't be a star. Any smaller and any lower mass, it wouldn't be able to sustain fusion in its core, and it would actually be a dead brown dwarf. So this is pretty remarkable, and the team that set out to find these ones actually purposely went after the very, very smallest stars. Because in our search for another Earth, we have what we call the race to the bottom. And the point is that we have stars of all sizes. We have blue-white supergiants, red giants, illustration of our sun is right there, and then we have small red dwarf stars, of which TRAPPIST-1 is one of. Now, do you see the little planet that I put in front of our sun? I want you to look at it now in front of the red dwarf star. It's actually the exact same size black disk, just copy and paste. But when I look at it, to me at least, it looks way bigger in front of the red star. It's an optical illusion, but I just wanted to convey to you what we're doing and why. Why we're doing this. Do you think we're doing this because we think they're the best chances to find habitable worlds and signs of life? Or do you think we're doing it because it's absolutely the easiest thing we can do? Yeah. That's why we're doing it. And so I wanted for a moment to take you on a virtual trip to a planet around a red dwarf star. So imagine for a moment we could get in a spacecraft and zoom to, I heard a couple questions about interstellar travel, but let's pretend we can do that. We can zoom away to one of these worlds. Here's a bit about what it might look like. Imagine for a moment we're around a planet orbiting a red dwarf star. That star might be very, very big in the sky because the habitable zone, the so-called zone around that star where the temperatures are not too hot, not too cold, but just right for life, would be very close to the star. And in some cases, that sun or that star would be very big. The artist here has taken an artist's license to make the sky red and to show you other planets in the same system, even translating that star. One thing about these planets, they're so close to the star that tidal forces over millions of years or billions of years, we think it's made all the planets tidally locked. Just like the moon shows the same face to Earth at all time, the planet would show the same face to the star at all time. Right? That means that it's rotating one time for every time it orbits. That's what our moon is doing. So we think, you know what that would mean if we could go to this planet? Believe it or not, it would mean that that star, that sun, is in the same place in the sky at all times. So you could choose to go there. Now, would you go and visit where it's always daytime? Because you would go to the night side where it's always dark. You can do astronomy. Or you could go where the sun is always setting. I actually would go to where it's always setting to see the green flash. How many of you have seen the green flash? I would just go where I could just watch it kind of last as long as it could. So that would be my favorite thing. Now, about these planets, they're so close to the star that they go around the star quite quickly. So it would be going around. This particular example would be going around in about 13 days. So if you're a child, your birthday would be every 13 days. Can you imagine having a birthday party every 13 days? It'll drive your parents crazy. Okay, so another thought, going to this planet, even just as a visitor, might not be so great. Remember that little flare we saw in the data? Those of you who saw that little rise? Okay, that was a tiny, tiny little flare in the infrared. So that particular star, which is somewhat quiet, would have also been flaring much more at visible wavelengths, at ultraviolet, at X-ray, all type of particles that are very bad for us. This will make the kids laugh. It would be very bad for your phone. If you flipped your phone out and a highly charged particle hit it, it might destroy it. So yeah, it wouldn't be so great to visit because the kids wouldn't be able to play on their phones and we would just, yeah. So these M stars, we're kind of concerned about them for a lot of reasons. It's easy to find planets around them. We don't know if life would be there. People are constantly in the astronomy community fighting back and forth about what's going to happen. Is the ultraviolet radiation going to kill all life, prevent it from developing? Is the X-ray and the winds going to blow the atmosphere away? We don't even know if these TRAPPIST-1 planets have atmospheres. So we're actually opening up a whole new chapter in exoplanets by finding planets around these very low mass, very cold stars. So just one more thing, if you'd like to try to find planets, do you know that some folks in exoplanets, we do look at all their light curves. I mean, we have very sophisticated computer codes that go through like tons and tons of data from the Kepler Space Telescope, from other space telescopes. We get raw data and we have to clean it up because as stars drift around and the telescope heats and cools down, or on the ground day and night, we see a lot of artifacts in our data we don't like. And believe it or not, even professionals will remove the artifacts without always knowing their physical cause. But once there's a cleaned up light curve, you could actually download it yourself and look through it. Or you can go to planethunters.org. Have any of you been to planethunters.org? You can actually look through the data and look for transits. And here's an example. I just pulled this off this morning, but if you start to go on it, it'll put you through a tutorial. That's really fun because you can look for dips in brightness and they kind of collate all of this crowdsourcing stuff. But once you go through the initial one, it turns out that, they actually put fake transits in to train you. So you sort of feel like you might have found a planet and then it was just training. But if you go through the data, it's just absolutely fascinating to see all the different types of stars and how they vary and try to find planets. So now I'm moving on to the middle section of my talk about our quest to find the true Earth twin. because in my mind, we'll do our best to find the planets around small stars, we'll study them and look for water vapor and signs of life in their atmospheres, but ultimately, I think as a human species, we're always after the true Earth twin. And so I'm now going to tell you a bit about that. Oh, actually, no, I'm not, because I forgot I was going to mention this test first. Okay, so I wanted to tell you about one of the many projects I'm involved with, and this is called the Transiting Exoplanet Survey Satellite, or TESS. TESS is an MIT-led NASA mission. It's going to launch in 2018, actually, next March. It's an all-sky survey to find transiting planets, transiting bright stars. Now, there are many ways to find planets, and the transiting one is just kind of the most popular one today. But should I come back here in 10 years, or 10 years hence after that, it'll be a totally different technique. So I'm going to tell you a bit about this mission. There are 4 identical telephoto lenses, cameras attached to one platform that goes on one spacecraft. And it's going to cover the whole sky, the southern hemisphere first, starting in 2018, and followed by the... Oops. Okay, I just wanted you to see the full size of it. It's not really that big of a spacecraft, actually. This is the whole spacecraft. You can see an antenna there. It's just made as an illustration, so you can see the size of the telescope. This bus, the spacecraft bus, actually is being built by Orbital ATK. Beside me is the PI. His name is George Ricker. The next slide is going to show you this is taken from a few months ago, but this actually is the structure of the spacecraft. We're going to launch on a SpaceX Falcon 9 rocket out of Cape Canaveral. This is actually the real spacecraft structure that will eventually house the cameras and all of the insides of the spacecraft, the batteries, radio, etc. Here's one of the cameras. This was a prototype, actually. This isn't one of our real flight cameras. But we put our smallest person with the camera, so it looks as big as possible. The aperture is only about 10 centimeters. And what you see on the outside there is a giant baffle. Actually, it's ribbed on the inside, so in starlight, we don't want to get stray light coming into the actual camera. It's actually not just the camera. You could go to the vendor exhibit and purchase. It's completely specially made, custom made, to have no vignetting, none of the effects that you would want to worry about. The camera is athermal, so it doesn't heat up and cool down in an awkward way. It has specialized 16 megapixel detectors at the bottom there inside. So just to show you how large of a field of view TESS can cover at one time, I have a series of slides courtesy of Zach Berta-Thompson. So this is 1 degree in the sky. Okay, and I think as astronomers, you're all relatively familiar with scale. And these are simulated images. We're trying to simulate our exact data set, so when our real data comes down, we know what, we practice finding planets in advance, trying to understand our very specific instrumental effects and what they're going to do to our planet finding and other astronomy goals. And also, so when the data comes down, if it doesn't match up, we'll be better off trying to find out what's wrong. So it's 1 degree. This is one of our detectors. 12 degrees, so the little square in the top corner, that was the slide from before, 1 degree, so now this is 12 degrees. But we actually have, each camera is about 24 degrees by 24 degrees. Again, this is simulated data. And remember I said there were 4 cameras, right? So 1 camera would fit within Orion. It's big. And remember I told you that there are 4 cameras, right? On the 4 identical cameras. Telephoto lenses with detectors on the bottom. And that's showing you 1 strip of the sky that will be observed for a 1-month period. So the cameras are just pointing, see those blue arrows? They're just pointing in such a way that they're covering a whole strip of the sky. And after 1 month, we'll move to the next strip, etc., etc. Now you can see the glass half empty or half full, so we like to see it mostly full. But you can see there are gaps on the sky that TESS won't cover. So people start to worry, is their favorite star going to fall on silicon or not? We don't know yet, because we won't know until we launch and get into our orbit. Now the poles will be covered. You can kind of see from this figure, right, how the poles are going to get overlapped. And in those poles, we'll be looking for hundreds of days. So we're going to be finding planets with the transit technique, looking at literally hundreds of thousands of stars, millions of them, really. We're also getting full-frame images, and we're going to just be flooded with data. So the fast track to habitable worlds, that's small planets transiting small stars. And that's kind of one of the takeaways. Okay, so now I really am going to move on to the next part of my talk. And that was the future. When we're finished mining the entire sky, imagine that we could find literally every transiting planet around a small star. That would be pretty amazing. But transits are the first part of a long story because we're limited to planetary systems with a fortuitous alignment. We think that stars have rotational axes, and the planets, we're not 100% sure, but we're pretty sure that most of them, except for some rare exceptions of hot Jupiters, that the planets orbit in the plane. So some of them will be lined up just so that as viewed from the telescope, the planet goes in front of the star. But actually, most of them won't be transiting at all. And so we're limited to, because of kind of probability, most of our transiting systems will be quite far away. And if we want to study Earths around the very nearest stars, even Earths in general, Earth is quite far from the star. We don't necessarily feel far from the star, but we are compared to the TRAPPIST worlds. They're very rarely to transit, okay? So this TRAPPIST world, if we wanted to find a transiting Earth, an Earth going in front of a sun, it's about 1 in 200 probability per sun-like star. So you might have to look at 200 stars to find a transiting Earth, but if not all stars have an Earth, it's many more actually, and more stars are further away. So the goal is actually to do another technique, we call it direct imaging. And in direct imaging, we're going to block out the starlight so we can see the planets directly. And here, there just happen to be a few planets in this fake illustration. Now we can do direct imaging already. And some of you, if you read about exoplanets, you'll read about direct imaging where we block out the starlight, but we're seeing planets like far from their star, like at Pluto's distance. And the stars we're seeing are giant young hot planets that are still hot, still luminous from their birth. And so those particular objects are not the Earth twin. They're definitely a step in that direction, but it's not there quite yet. So we do face an incredibly interesting problem when we're thinking about direct imaging, because we want to think about blocking out the starlight so we can see the planet directly. But if we imagine putting a giant circular screen in space or a little tiny block coronagraph inside the telescope, the problem is that the light itself diffracts and acts like a wave. And what you're seeing here is, let's imagine for a moment we could put let me think for a second, a perfectly shaped circular screen in space to block out the star. We wouldn't block the star out actually. We would see rings, as you're seeing on the right, an area ring pattern. And what's happening is that the light is acting like a wave, and it's bending around the edges of this hypothetical screen in space. And those waves there, like the first couple of waves, they're actually far brighter than the planet we would be looking for. This is analogous to dropping a pebble in a pond. And you see ripples. So that's the thing with light, is that it can act like a wave, and it can make ripples that are brighter than the planet we're looking for. So now I want you to imagine we don't put a big circular screen in space or a small tiny little coronagraph inside our telescope, but we put a specially shaped object. That's what's showing you on the left, a mathematical construction of a kind of star shape. Then instead what you would see, blocking out a point source of a star, you'd see the image on the bottom right. Most of the image would be very, very dark. And the light would be diffracting, but interacting with itself in a mathematically prescribed way so that the light is all pushed to the edges. This would be analogous to dropping the pebble in the pond. But instead of seeing ripples, the water around your pebble would be perfectly smooth. And all the ripples would be pushed to the edges. Now, believe it or not, this idea was first written about in the 1960s by Lyman Spitzer, the person who helped us get Hubble launched, and who the Spitzer Space Telescope that discovered the TRAPPIST worlds was named after. And it's just incredible that every decade people revisited the idea. And now it's actually nearly a reality. So I'm going to show you an animation that's going to show you what the star shade is. It's called the star shade. And you can imagine possibly launching a star shade and telescope together. And the petals unfurl from their stowed position. The central hub can expand with the petals undergoing the second stage of deployment. And there they go, they snap into place. Now, in order to block out the starlight to see a true Earth twin, remember I told you it was 1 in 10 billion? Yeah. Well, this specialized star shade has to be made extremely precisely. The petal shape, the relative position of the petals to each other, and the formation flying, because it's blocking out that starlight so that the planet light will go directly into the Space Telescope. And they have to be precisely aligned at many tens of thousands of kilometers. Starshade's one of the main projects that I'm most excited about. And here's a few pictures from the Starshade lab. So you're supposed to start thinking about what that is. So there's a petal in that picture. Look at that long tip. And there's myself and two of my team members. This particular version is built at JPL. There's a different design being developed at Northrop Grumman Corporation. Well, here you can see how big this petal is and how big the Starshade would be. And the shape has to be manufactured. So there's like a two-pronged approach to working on the Starshade. One of the ways is actually to demonstrate that we can manufacture the Starshade to the tolerances required. So if we want to block out the light to 1 part in 10 billion, the shape has to be just so, and it has to deploy just so as well. Okay, just a second. There's actually one more picture I was trying to show you, but I guess it didn't show up. Let's see. I'll try to pull up the other picture for you in the Q&A. But before I do that, I wanted to show you this one.
Remember I told you about the Starshade?
Believe it or not, this is one that has been used for real to test. This is a 1% Starshade scale. And it's been used in the desert in Death Valley by people from Northrop Grumman to test it out to see if it actually can work the way it's prescribed to. And what they did was they spanned a baseline of about 3 kilometers. They had an LED that was a star and a planet, and then they had their camera another kilometer away. The Starshade was approximately in the middle. And they try to measure and see whether they can block out the starlight and see the planet directly. And in fact, they would make defects on the Starshade. They would make defects on the Starshade to see if that matched their mathematical models. People also do demonstrations in the lab with much smaller Starshades, 0.1% scale, to try to show that it all works.
Okay.
All right, so the search for Earth twins, we need to go to space above the blurring effects of Earth's atmosphere, and we have to really go to a whole new level in terms of blocking out the starlight and seeing the planet directly. And I've only told you one method. There's another way where we use a specialized space telescope and put a chronograph, a special shape, on the inside of the telescope, but they're both very, very challenging. So in the last section of my talk, I'll move on to why we're searching. And believe it or not, one of the questions that I get asked most often when I talk to anyone, actually, is we're looking for these planets, we're going to find an Earth, we found some, maybe that are like Earth. Can we go there? And so that actually is the question I get most often. I decided not to cover that with you because I'm pretty sure you all know in this audience that we're not going to be able to travel to those stars anytime soon. And in fact, I think that was the question for the last speaker. So what I answer to them, if you ask me, well, why are we looking? That's the next question. Why do we look? If we can't go there, why are we trying to find these planets? And one of our main reasons, believe it or not, is the whole search for alien life. And we're not talking about like the arrival, that we're going to meet aliens. We'd like that. That's what we really do want to have happen, but we're not expecting that. We're starting at a very, very basic level with the astronomers' tools that we have before us. So when we talk about the search for alien life, it's not necessarily for intelligent beings that can send us radio signals or come here in their specialized pods, but it's a search for signs of life, for gases in an atmosphere, gases that don't belong, that we might be able to, with some probability, attribute to life. And this picture is of bacteria, because we don't know, ultimately, if we find this life, we won't know a lot about it. We won't know if it's big or small, if it's simple single-celled bacteria, or animal-like things, or plants.
There is
so
not
that,
another field of human contemplation so
science
wonderfully
fiction got something
rich
wrong.
as astronomy.
Because the Star Trek
It is so easy to
Enterprise had to
reach,
travel at
so
incredible
responsive.
speeds over vast distances to orbit other worlds, so that Spock could look at the surface and see if there were life forms. And sometimes, you get the speakers visiting, and it sounds super exciting what we're working on. Like that Starshade, people have been working on it like a little bit every decade, and for the last decade, huge amounts. It's going to take us at least another decade to launch it. So I was thinking, like, if they made a TV series about the regular scientist's life, it would be incredibly boring. It would just simply be like watching paint dry. So we don't go places, we don't look for stuff, but actually, we look from here. And this is a real image of Hubble Space Telescope from the last servicing mission as it was backing away. And the last servicing mission, they actually put on Wide Field Camera 3, which turned out to have a very stable detector. Hubble orbits Earth every 90 minutes. It goes through orbit day, orbit night, so it heats up a little bit in orbit day, it cools down a little in orbit night. It's not ideal for looking at planet atmospheres, but we actually use it for that. The whole astronomy community, people who work on exoplanets, actually use it to observe planets. And what we do is we look at spectra. And just for those who don't know what a spectrum is, I have a few slides to convey it. This is showing you a rainbow. And you know what? If you could look at the rainbow closely, zoom in on it, you would actually see that parts of the rainbow are missing. Little teensy little parts of the rainbow are missing due to gases that absorb. And here's an image of the solar spectrum. So this is taken not with raindrops spreading out sunlight into rainbow, but it's taken by a special telescope and a special instrument called a spectrograph that splits up the light. And do you see the little pieces of the rainbow missing? Believe it or not, each one of these, or a set of them, a fingerprint of lines, the set of lines actually correspond to gases in our star's atmosphere, in our sun's atmosphere or photosphere. And you actually, if we sat down with a catalog, a library of lines, we could actually do this real thing together and work through which are calcium lines or magnesium or silicon or other things actually. And this is what most of professional astronomy is based upon, is in some things you do, you might call it narrowband imaging. You know, you just want to get a simple, very narrow wavelength range. But we want to break up all of the light and study the light at different wavelengths and look for gases. And we are doing this with exoplanets as well. But spectra are required to do any more than what I've talked about up until now. Because, for example, with transits, the transit finding technique, Venus and Earth would look the same. If there are intelligent beings on a nearby Earth looking back at us with an equivalent to Kepler, and they're looking for those tiny drops in brightness as our Earth goes in front of our sun, they would see Earth and Venus and call them equivalent. They're about the same size. If they could get a mass, they say, oh, they're about the same mass. They are receiving different amounts of energy from the sun, but if the hypothetical aliens wouldn't know that Venus has a massive carbon dioxide atmosphere with a huge greenhouse effect. On our Earth, we're worried about adding parts per million of carbon dioxide, which might warm our Earth. But actually, imagine we have an Earth out there that has 100 times carbon dioxide that we have, or 1,000, or other greenhouse gases. So until we can study the atmospheres of the other worlds, we don't know actually what their surface temperatures are, and whether they are indeed too hot, too cold, or just right for life. So we're looking for atmospheres on other worlds. Further than that, we actually aim to look for gases that might be produced by life. We call them biosignature gases. Our own Earth's atmosphere was modified incredibly a few billion years ago by cyanobacteria, and today we're here because we can breathe oxygen. But without plants and photosynthetic bacteria, we would have virtually no oxygen in our atmosphere. Yet our atmosphere is filled with oxygen to 20%. So astronomers love the idea of looking for oxygen on another planet. It's so highly reactive, it shouldn't really be there unless something is producing it continuously. So I think I just have one, let's see. I just put in one technical slide because I know some of you are in the know and keep up with all the news on exoplanets. And I wanted to just very briefly explain to you that we are measuring atmospheres of exoplanets right now. Now you don't have to understand this slide to understand the rest of my talk, so it's going to be a little detailed. But the one way we study atmospheres right now is we look at the transiting planets, the planets that go in front of the star. And what we're looking for is the starlight that shines through the atmosphere. Just like shining a flashlight through a fog. Some light makes it through, some doesn't. And by looking at how much light makes it through at different wavelengths, we can actually identify gases in exoplanet atmospheres. This particular graph is data taken from the Hubble Space Telescope Wide Field Camera 3 of a hot Jupiter planet. It's a planet that orbits its star in about 3 days. It's very hot, like 1,500 degrees Kelvin. It's not a rocky world. It's not going to have life. But this is the type of planet whose atmosphere we can study right now. Now what we're looking at is wavelength in microns, and then we're essentially looking at the size of the planet in percent, basically, the depth, transit depth of the area of the planet in depth. And what I want you to think about, and this is the hard part to understand, is that when the if you imagine the planet for a moment with no atmosphere or a transparent wavelength, the starlight makes it through, and the planet appears a certain size. Now think of another wavelength where the atmosphere is very strongly absorbing. The light doesn't make it through. And so that little thin annulus, the little thin, like the onion skin on an onion, now makes the onion, or that little thin atmosphere makes that planet a tiny bit bigger, because the atmosphere is blocking starlight. And so what you're essentially looking at is the planet getting bigger and smaller as a function of wavelength. And we use that to tell us whether or not the planet has an atmosphere. And if the planet looks a little tiny bit bigger at a wavelength that corresponds to like a library of a known gas, we actually can identify that as a gas in another planet's atmosphere. So what you're seeing here is the black points with arrow bars are data from the Hubble Space Telescope, and the blue and red lines are models. And if this planet had no atmosphere, all you would see is a straight line across. So all you have to agree with me is that what you see here in these points is different from a straight line. I'm just smiling because this actually really is among our best data for exoplanet atmospheres. And we see this peak, and that peak lands right where water vapor actually is absorbing. And this hot giant planet has water vapor. Now this field of exoplanet atmospheres is one of the main fields I work in. You can ask me questions about it later. It's a very detailed field, and we're really pushing the limits of what Hubble was designed to do and what data analysis techniques can do in order to extract as much information as possible. So in terms of exoplanets, there's so many molecules and so little time. Water is required by all life as we know it. So our first goal for the TRAPPIST-1 planets and other planets like it is to look for water vapor, a sign of liquid water. Our next step will be to look for oxygen. Earth's atmosphere has been highly modified by life by creating so much oxygen. Lots of other gases have been studied. Some you may have heard of, some you might not have heard of, like methane, nitrous oxide, methyl chloride, dimethyl sulfide. We have a growing list, actually. And there's this whole new field of exoplanets flourishing, making models about what gases could we detect with the James Webb Space Telescope or other telescopes, and which ones, how will we know whether they're produced by life or not? That's a growing field right now. And so we require really big telescopes to try to do this, because planets are so small and their atmospheres are even smaller. And there's an image of the James Webb Space Telescope, and on the right I put the 30-meter telescope, one of the 3 extremely large telescopes astronomers are trying to construct on the ground right now. So to summarize, there are thousands of exoplanets are known to orbit nearby stars. Most information we have about them is limited to their sizes, masses, and orbits. And remember at the beginning I showed the chart with all the dots? That's actually most of what we know. Our fast track to the search for habitable worlds focuses on small planets transiting small stars. Our next generation telescopes will study exoplanet atmospheres for the search for water and biosignature gases. Now I know a lot of you help out with star parties. You go there and you set up your telescopes and you show other people. Well, what we're aiming for is that one day in the near future, we'll be able to take our friends and family and children to a dark sky site. We might need binoculars, but we hope we'll be able to point to a star and to tell them that star has a planet like Earth. Thank you. Okay, so while you're asking questions, I'm also going to scroll through because I wanted to show you a couple of other pictures of the star shape. And I just want to let you know that after the talk, we're going to move the petal. This is, in case you didn't guess, I was hoping everyone figured out what this is. It's the petal of the star shape. The star shape design this goes with has 28 petals. And those would attach to a 20-meter inner hub. So we're going to move that outside, and you can come over and ask questions, or you can take your picture in front of them. Okay, questions up there.
The Washington Post yesterday reported on a star GJ 1132b having a atmosphere with scientists from the Max Planck Institute. Is this the same sort of study that you're doing, analyzing the light curve and breaking it down?
It is. Now I'll give you, I don't have a figure to show you, but that, in the abstract of the paper, it said a suggested atmosphere. And what they had was, for people who work with data, when you make a detection on any plot, okay, it could be this plot, it could be like the stock market rising or falling, the points have to be well separated. So if I were, for example, to add all these points together and add their error bars in the proper way, and these points. You have to make sure those points are very far apart from each other with no overlap. So that particular study, if we could pull up a figure from their paper, the points, the error bars do overlap. And I do not think that the authors intended to say, yay, we have made a new discovery. They said, here's a new method, we've worked really hard from the ground-based telescopes. Here's as far as we could get with what we're doing. It's close enough to kind of suggest there's an atmosphere, but world, here it is, please build on this and do better. You can't get that. So that's partly why I showed you the TRAPPIST stuff, because I wanted you to see what's behind the news report. Yes?
Is there any correlation between the exoplanet research and the SETI surveys?
Okay, is there any correlation between the exoplanet research and the SETI surveys? Oh, coordination. They said correlation. Yeah, it's okay. We hope there's a correlation, because we hope we're going to. Okay, yes. It's not so much a direct coordination, but the SETI searches, searching for radio signals from exoplanets, when new exoplanets are discovered, they can do targeted survey. So Proxima Centauri b, which was announced in August of last year, SETI could then, the people, different people working in that field can actually point their telescope to Proxima Centauri and just listen for a while. So that's how coordinated it has been. Yeah. Yes?
Besides the all information and the data that we have as a planet, as a scientific people around the world, as a person, as a human being, what do you think is possible life in another part of the universe? Because I think, in my personal opinion, ignoring that must be life in another place is be a big mistake, because it's a huge universe. What is your personal opinion, besides the data or the information?
Okay, he asked my personal opinion, so scientists never like to give a personal opinion. It's very unscientific. I'll say that aside, I absolutely believe, I share your view, the universe is so huge. We have billions of stars in our galaxy. We think there are billions of galaxies. So billion times a billion is a pretty big number. And if every star has a planet, then that's, wow. Some of those must have life. But in my day-to-day life, when I get to work on the search for other planets, we ask a slightly different question. And that's, is there life on a planet around a star very near here? So let me ask you for a moment, who here believes there's life somewhere out there in our whole universe? It's a self-selected audience, because you came to the talk, so I get that. But now let's say another question. How many of you believe there is life around a planet, around, let's say, one of the nearest 1,000 stars? Because that's what we're going to have a chance to look at. Okay, great. Well, it's very optimistic. Okay, yes, question.
Is anybody in MIT working on quantum mechanics, wormhole travel?
Is anyone at MIT working on quantum mechanics, wormhole travel? Not to my knowledge. No. The thing is, I just want to say something to that question. Okay, so every decade or so, questions that were laughed at, we call it the giggle factor. So is your comment or question or what you're working on, can it pass the giggle factor, right? And so that's changing rapidly, I just want you to know. So if we come back here, let's say 20 years from now and ask that question, it could be it could be more of a mainstream. Like, we got that question the last talk about the Interstellar and the billionaire Yuri Milner giving $100 million to build those little tiny, you guys, someone asked that question, I don't know if you were here, but there's effort to try to build little tiny wafers, like literally this big, that giant laser banks on Earth would be launched into space, and giant laser banks on Earth would accelerate them to 20% the speed of light, accelerate them without ablating them, without vaporizing them. And they would then zoom away, and some of them would make it, thousands would be launched, some of them would make it to the nearest star, and look at that planet. So none of you are laughing. You can laugh. It's very ambitious. That's what the previous speaker said, right? It's very ambitious. I'm just saying that like 10 years ago, if we talked about that, it would just get laughed at. So just things are moving rapidly in the field of exoplanets and everything that surrounds it. Yes, question there.
Why did TESS leave those gaps in observing?
Why did TESS leave those gaps? I don't think that TESS intended to leave gaps, but I just think the configuration of the cameras, I don't think they could find a way to cover the entire spherical sky in a way that was efficient enough to cover the whole sky. But hopefully through your head you're having a better idea. And you can suggest it for our hopeful extended mission. But actually, whenever you launch a spacecraft, you always hope that it will get extra time. Tests can live on. It doesn't, it doesn't need to. It's in a stable orbit. It doesn't need to do a lot of things with the fuel it has on board. So if it can go another year or two after its prime time 2-year mission, we'll look at the rest of the sky. We'll cover the ecliptic. We'll cover those. We could potentially cover those gaps. Yeah. Any other questions? Okay, I'll start moving back there. Yes.
I'm curious about how difficult is the orbital choreography between TESS and the choreograph?
I mixed two things up. TESS is going to orbit Earth, and the Starshade is not a planned mission yet. It would launch in the future, and it would go with its own telescope. I'm glad you asked that, because I zoomed by both. TESS is one thing with 4 cameras. The Starshade is a future project. We hope that it will launch within a decade. And we actually hope that any big telescope, not as small as TESS, but any telescopes like the size of the Hubble or larger, would be Starshade ready. And we're trying to get NASA's next telescope after James Webb, it's called WFIRST, be Starshade ready. So it would have to go with its own telescope very far from Earth and work together.
Could I apply my question to that?
Sure.
How does the orbital choreography work?
How does the orbital choreography work? Good question. The Starshade and telescope have to line up incredibly precisely. If I told you how precisely, then you would laugh. So that they actually communicate with each other, and they have to be far away from Earth's gravity. Earth's gravity is bad. We couldn't figure it out. Very far away, like in an Earth trailing orbit or else at L2. And then the gravity is not a big deal, actually. But they have to line up properly. They can communicate with each other. The Starshade itself would have an LED bank so the telescope could see it. It would have a laser beam. And finally, when the starlight blocks out the starlight, red light that's not used for planet finding would leak around the edges, and the telescope would see that. So there's a very special, timed choreography, and they can talk to each other as well. They can communicate and close the loop in that station keeping. And then every time the Starshade needs to look at a new target, it would have to fly around the sky, move over, take a week or two to move to its next target and line up with the telescope. More questions? Anything in the back? Okay, over there.
Moving now I would imagine that moving the Starshade around would require some kind of thrust. Wouldn't that necessarily limit the lifetime of the mission?
Yes. Now, one thing about the animation I showed, it didn't show that the Starshade has to have its own spacecraft with its own fuel. And the Starshade retargeting, the fuel that moves it around, yes, it's very limited. And when we think about the mission and how many stars we can look at, there's a sweet spot between how many bright sun-like stars are near enough for us to study well, and how many times the Starshade can move from star to star and back to any stars with planets. And solar electric propulsion, that also got mentioned in the last talk, that might help us extend the mission lifetime. Yes, any other questions? Yes?
Starshade, when it's changing positions to look at different stars, does it furl itself back up? And then
Oh, good question. Does the Starshade furl itself back up to move on? That would be efficient, but it does not do that. Aerospace engineers are terrified of deployments, and we don't want to fold it back up and roll it out again, although it's technically possible. Yeah. Any other questions? Okay, there's one question there, and then I'll come to you. Yes?
You alluded early on that we had not yet found any systems like our own, but starting with Earth, it takes a year to orbit, and every planet beyond that is multiples of years. Are there any plans for long-term observations of a given star or group of stars that would allow for finding something similar?
Good question. Are there long-term programs finding something similar? Unfortunately, not as much as we want. We got crazed over these M-dwarf stars. The periods of the habitable zone planets are 1 day, 2 day, 11 days. And so more attention has been given to short-term excitement over long-term investment. And that's kind of downer for us, because the easiest thing for us to find right now in terms of a solar system copy is another Jupiter. Well, Jupiter takes 12 years to orbit the sun. So if you want to set out on a 12-year project, you're not going to see any, you won't be sure, probably for 18 years, because you want to see it go around once and go around a little more. Well, people have been looking easily for 12 years, 20 years, 25 years, or longer even, but just not with the precision needed to find a Jupiter around maybe more than a few stars. So your concern is also our concern, and we're trying to make sure people are having what they need to look a little bit longer. But it's partly that we need the resources, but it's just hard. I mean, we have Jupiter, which is far from the star. We have Earth, which is so small. Venus isn't helping us, neither is Mars. Mars was a topic earlier today. It doesn't help us for exoplanets. It's so small and dark. Yes, back.
What
back.
role do you think our moon had to do with the development of life on Earth, and does that influence your work?
The question is, what role do I think the moon had on life on Earth, and does that influence my work? I don't worry too much about the moon. It's in the category of is this easy or is this hard? But the moon, we think, played some role because we think that changing conditions on our planet were necessary for life to develop. Because you can imagine molecules forming, maybe they can start to self-replicate. In order to push something and to make it change, where it would have a chance to evolve into something else, we need change. And so one of the big kind of theories is that the tides were very helpful because you had tidal pools and they were changing conditions. So that's really the kind of current thinking. I'm not so worried about the moon. I mean, the other thing is the moon stabilizes Earth's axis. Without the moon over time, our pole would start pointing towards our sun. And it would kind of go back and forth. But that change would happen over many tens of millions of years, so it wouldn't be abrupt. So I'm not too worried about it. But on the other hand, we don't really know for sure. We still have time for a few more questions.
Radial velocities, may be used to detect exoplanets?
Radial velocities. This is the wobble technique when the planet and star orbit the common center of mass. And radial velocities are still being used. They're the way we found planets initially, because we measure the line of sight motion of the star as the planet's orbiting the star. But remember I was saying that transits are all the rage today. It's our best way right now. But 10 years from now, it won't be transits. It'll probably be microlensing. 10 years after that, it will be direct imaging. So for those in the know of radial velocity, I'd say it's still working, but it's playing more of a supporting role now in terms of if you find a transiting planet, you want to measure it with a different technique and see if you can see its mass. Okay, I'll take 2 or 3 more questions in the back. Yes, yeah, right there. How about you first and then we'll go there, yeah.
Something that our own solar system is, we're now, 5 or 6 bodies that have subsurface oceans. And I'm kind of curious how the exoplanet stuff, obviously it's not their way unless they have an atmosphere to observe, but how would these, icy surfaced oceans reflect into what they'd be looking for in exoplanets?
Yes, the question is about the icy worlds. And do they reflect an exoplanets at all? And the answer is, that's one example where we can't use it for our search for other life on other planetary systems, because these moons have no atmosphere, and if there's life beneath them, maybe one day we'll find it by going to Europa and landing and maybe drilling down. But it's a closed system where nothing's coming on the outside that we could observe with traditional astronomers' tools. We do use the moons in a way that's probably not related to your question, but we imagine scaled up versions. What if we have a planet like Ganymede or Europa that's a scaled up version that would be 50% water by mass? We think that they might be out there because we see planets that have a mass and size and an average density that can correspond to those worlds. We call them water worlds. And in those cases, they would be warm enough and massive enough to maintain an atmosphere. And so we do kind of use it in that way, as thinking about scaled up versions being pure water worlds, but we don't really have a way to detect those or study them as far as exoplanets are concerned. Okay, just hold one. Yes.
Me?
Yeah.
Okay. 2 questions with regard to looking at planetary atmospheres. With regard to oxygen, I can't think of any way that oxygen would end up in a planetary atmosphere other than by light. But you've been studying this for a while, so do you have any ideas as to?
Yes, I can answer that one.
What?
Yes, I can answer that one.
The other one was what kinds of signal noise ratios do you end up needing overall to detect these tiny changes in spectrum?
Okay, I'll just answer those, and then I'm going to have to wrap up. But as I said, I'll be outside with the Starshade pedal, and you can, if you have a technical question, you can ask more. So with this thought that the habitable worlds are out there, TRAPPIST, maybe them, we'll probably hear about more. We have Proxima, Centauri B. Everyone got really excited about oxygen, and then started coming up with all the ways that it could be produced without life. And I'll just give you a very quick one. And that is that, imagine for a moment we have TRAPPIST-1. Okay, TRAPPIST, this very cold M-dwarf star, they have a very long teenage phase before they can stably fuse hydrogen. And during this crazy teenage phase, it's like 100 million years. They actually are very hot and very bright. So any planet in habitable zone today of TRAPPIST For like 100 million years, it was baked. And people think that water evaporated from any oceans that might have been there, hydrogen escaped to space, and oxygen was left over and reacted with the surface, so oxygen was gone. But then water in the mantle kind of diffused up, and that ocean after ocean after ocean was evaporated, the whole planet became desiccated, and finally, because the surface was saturated with oxygen, it could no longer react away, but stayed in the atmosphere indefinitely, causing a massive oxygen atmosphere. And the second question was signal to noise. We always make one, and then we say we have to observe it, but we'd say we'd want a signal to noise of 5, if you happen to know what that means, or 10, but essentially we do have, we try to make it as high standard as we can, and then design our observing program or instrument to that. And I am just going to take one more question right here, if you still have a question. Yes, last question.
What are you detecting everything from life other than dead standard carbon actually is? Like perhaps we would exist in oceans of multi-meter stuff which is not H2O.
Okay, was the question, can we detect any life that's not familiar to us, like non-carbon based life? Was that the question?
Non-carbon active life, like maybe carbon that is water or that is carbon.
Oh, okay. The question is, can we detect any life that doesn't use water or isn't what we expect? That's a tough one. We're really stuck on that. I'm not sure if that was this question. We think life could exist in any liquid, not just water. Like on the ethane lakes of Titan, maybe life could be there. But for now, we're very fixated on our astronomers' tools and what we can actually see and study. And that limits our creativity on what we think might be a sign of life. We're just right now trying to find the planets and make the observations to find life out there. Well, I want to finish by thanking you for your enthusiasm and for your optimism in the search for life. Thank you.
Thank you.
take a picture of it too.
An hour and a half. Go. Yeah, I have like an hour and a half on my card. Yeah. I was telling that kid, I'm not bringing the lights back up on the and it's dark. I have my iris cranked way all the way open. I have to bring the gain up. I said, well, I'll just let you know that these guys are not on top of the lights. They got to bring the lights back up after, the presenter says, I got a video to show. I don't want them to turn around and go. It's dark. No. All right. Right. Don't want them out. it doesn't matter as long as my name is on the camera, it's on the tape. So, yeah. Take part 1, part 2, part A or B. Yeah, you gotta also put part A and part B. Alright. Yeah, you gotta know, you gotta know which part first, which part the ball goes with. So they have to know which part A, and that's part B. And then we'll just day 1 and time. Yeah. Better. All right.
Ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, welcome back, everybody. Well, this is a great finale for us here for the first day at NEAF, and again, we certainly hope you all had a great time. And we're doing this program again for you, the audience. A lot of people are working. I'd like to give a shout out to the production crew and the folks that are behind the scenes making this all happen. Thank you very much. So our last, and really going to give you a good keynote speaker here today, is the principal investigator for the Project Juno Probe mission. And he has previously worked as the chair for the Titan Science Group for the Cassini-Huygens mission. He has received several accolades from JPL, the Individual Award for Exceptional Excellence in Leadership, and received numerous NASA awards. Please bring,
there is not another field of human contemplation so
Dr. Scott Bolton.
Thank you for having me.
Everybody may not be a chemist. Everybody may not be a geologist.
So,
but
not exactly part of my talk, but we can incorporate it.
Want to be in a modest, personal way, an astronomer.
So, I'm
or stargazer
about Juno, and
is a great medicine
program
for the soul.
So I have some exciting results to show you. We've been in orbit now a few times. We're running 53 days in 5. So we're around a few times. 3, 2, a lot more to come. 0. But what I do want to say, sort of with caution here, is I'm going to present to you some results.
We're now going to take you on a journey to the outer reaches of the solar system.
So I have a favor to ask, and that is I have an arrangement with people that public announcements that are about 50 science papers that come out next month. And of course NASA is very, it feels very important to have the press releases at the right time, say the right things. So I need people to not take photos and post them.
So I would appreciate your indulgence in that, and that would be to show you some results, and maybe tell you some things that are just guesses as to what we're learning that haven't gone through the scientific process yet, and it may be wrong. So don't go rewrite the textbooks yet. Okay, so I'm really happy to be here, and so I'm going to go ahead and get started. What you can see on the screen is one of the images. All of our camera pictures that we take, which you know are posted on our website, and I'll show you some of those toward the end of this talk. And they basically go out raw. And the public, people such as yourself, classrooms, amateur astronomers, they pretty much create their own images and post them back on our website with explanations of what they did. And almost all the
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be and ought to be, in a modest personal way, an astronomer. Or stargazing is a great medicine for the soul.
Questions on that? 5, 4, 3, 7 to help.
Today I want to take you on a journey to the outer reaches of the solar system.
Okay, so you see a picture of Gino up here. By the way, I'm here. So even this device is a little high risk. They told me not to touch this button, so it's just a matter of time before that happens. But one thing that you don't know is that there's a person back here that's really making all this happen, making it work. So we're really dependent on him. And he's made all this possible so that he minimizes the risk that I'm going to ruin it. Okay, so here you see a picture of, not the scale.
Great conference.
However, it is very large. So those solar arrays, there's 3 of them, they're 8 amperes by 8 feet. Okay, so this is one of the largest solar arrays. Even with all those giant solar arrays, there are many of them, and they're very advanced. They only produce about 600 watts of power at Jupiter. So it's a very efficient spacecraft. That's part of the technology. So it's about the power of a microwave oven, right? Of course, it gave off a lot of power when we were near the Earth, and we had to get rid of that power. And so there's massive radiators on it as well. And so that goes through space cartwheeling. So it's spinning twice a minute all the time, ever since launch. And the object in the middle, which you probably know, is a high gain antenna. So that's basically like a very fancy DirecTV dish. Sends the signals back to the Earth.
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be and ought to be, in a modest personal way, an astronomer. Or stargazing is a great medicine for the soul.
So that we don't measure magnetic field
Five, 4, 3,
far as probably the workforces that we're now learning that we hadn't anticipated that are actually disrupting.
Today I want to take you on a journey to the outer reaches of the solar system.
Great to be here.
So here is not my highest resolution with you, but helpful star sort of nebula that's out in the galaxy. Use this why we're
What a great conference.
main objective learn about how Jupiter represents the most even view that means really busy with the mission. The planets are formed out of interstellar clouds, coming from interstellar clouds, which are mostly clouds of helium and hydrogen, mostly hydrogen with a little bit of helium and a smidgen of all the other elements. And these clouds collapse and they form stars. And then there's leftover debris. And that debris goes into the first planet. And so they're dusty regions. We see young stars forming out of these regions. And so there's a delay to this button, or it doesn't work. Okay.
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician. But everybody may be, and ought to be, in a modest personal way, an astronomer. For stargazing is a great medicine for the soul.
Because of that, it represents a very important the rest of the leftovers after Jupiter, that's us. We're the leftovers. 5, 4, 3, 2. Try to teach that to my kids weekend after lunch. This is the leftovers, but you'll
Today I want to take you on a journey to the outer reaches of the solar system.
Back in the history of the solar system, here's a horizon looking down.
It's great to be here.
We know Jupiter formed very early. It was mostly hydrogen and helium. You can see when you look at these planetary nebulas that once the star forms, the star moves on a blow basically the hydrogen and helium gas envelope away from each other. So you have to make Jupiter so it had to form very early. Scientists also learned from other space.
What a great conference.
That Jupiter was enriched. I was much even here, and I'm really busy with the mission. And so the key to understanding how we came to be and how planets are made is to understand that process. How did Jupiter get enriched? What happened that allowed it to get more of the heavy elements than the sun has, percentage-wise? Okay, and of course that's important to us. We may not know exactly how that happened, but we know that we're made of the stuff that Jupiter has more of. So whatever process went on, that eventually leads to the existence of Earth and the other terrestrial planets and even life itself. It started right away when you were making Jupiter.
There is not another field of human contemplation so wonderful.
Abundance of heavy elements.
We can take a picture of it too.
What Juno's about is to try to explain that. Okay, so we have two kinds of measurements that tell us about the origin of Jupiter. One is the gravity science, and we're looking to see if Jupiter has a core.
Look, Mommy, we took a picture of the moon.
And the other is the water abundance. We don't know how much water, which is really how much oxygen is in Jupiter. Those two things discriminate among different theories. I'm supposed to stay on this blue, but I don't want to block people from seeing it. So what we want to do is learn about that water abundance. And a lot of scientists believe that the way Jupiter gets enriched is ices start to form in the nebula, and they trap the other heavy elements, and then they go in, icy planetesimals, if you will, sort of small, dirty comets, went into Jupiter when it was forming. Maybe that's how it got enriched. That may not be the case, but that's one idea. And the other ones are the core. Why is that core important? Well, because Jupiter has a core of heavy elements, sort of rocky stuff in the center, and it meant those things formed in the early solar system before Jupiter started. And Jupiter maybe was built around those. If Jupiter has almost no core, then maybe it formed more like the Sun did before that stuff was there. And because if you form a Jupiter like right now and you throw a comet or an asteroid at it, it doesn't sink to the middle, right? It heats up and evaporates and burns up and mixes into the molecular envelope of the gas itself. So you can't make a core now. Okay, so back in 1995, NASA sent a satellite to Jupiter called Galileo, and it dropped a probe. Here's an artist's concept of that probe falling through the atmosphere. Its primary job was to measure the composition. What was the ratio of those heavy elements, and how much of them, which one was in Jupiter? This is a picture of the probe. It looks like something out of the 1950s science fiction. I mean, this thing is a submarine named for Jupiter, right? And these are the sensors. This is an actual photo of it before it was launched. Okay, so the results I'll show you in a minute, but what it's really after is this chemistry table, right, that we all learned in high school or maybe junior high school. Hydrogen and helium are up at the top. On the far right-hand side, you have the noble gases sort of in a different color. They're important because they don't do a lot of chemistry. They're noble and they don't mix with a lot. And then you have some of the basics like carbon, nitrogen, oxygen, sulfur. You may have a favorite element here. My mom's favorite is gold. But we knew that carbon and nitrogen were a little bit enriched, and the question was, what's the real ratio of all of those, as well as the noble gases? And that can tell you sort of the secrets of how maybe Jupiter was made. And so here was the data from 1995 that sort of puzzled everybody. It took about 30 minutes for this probe to fall down through the atmosphere of Jupiter. The way you read this chart is on the bottom, across the bottom, or the horizontal scale are the different elements. You got some of the noble gases, argon, krypton, xenon, carbon, nitrogen, sulfur, oxygen. And then on the vertical scale is the ratio to the sun. So if everything fell on one, that Jupiter was made the same as the sun. If it's below one, it's obviously depleted in those elements. Above it, it's enriched. In the 30 minutes it took to take this data, every single theory of solar system formation and how you make planets was proven wrong. There wasn't a single theory that could explain this data. And the puzzle was that all of the elements were enriched about
we can take
the
a
same
picture
level,
of it too.
about a factor of 3 or 4. And each one of those elements has a different sort of volatility. It gets trapped or freezes at different temperatures and pressures. And so what was expected was that depending on where and when Jupiter formed, that there would be some difference in the element enrichment, because some would get more easily trapped in those icy planetesimals than others. So that was a puzzle that they all came out even. So nobody's really figured out exactly how to explain that, except one idea is maybe this migration is true, that planets are migrating and Jupiter formed really far away where it was cold, came back in.
That's one idea. Nobody knows if that's true. The other thing that puzzled people was that water, which was supposed to be the source of the enrichment, was actually depleted. So here I have all the elements enriched the same, which nobody can explain. And on top of that, the thing that was supposed to carry them in, there's less of it. So the explanation out of the water measurement is that maybe we got unlucky with this air those theories would still be right. And so theorists were hanging on to the idea that Jupiter really isn't like this, we just got unlucky. So the answer was go back with a whole bunch of probes so we don't get unlucky again and go really deep. That was very hard to do, and so the idea and the questions went on the shelf because these were investments that we weren't able to do that kind of a mission right away. And then we came along with Juno and we thought of a way to measure that water very precisely all over the planet remotely. And that's sort of the secret of how it is. And so what are we really after with Juno? And it's sort of the recipe of a solar system. What's the recipe to make planets? So I show this can of soup up here because all of you probably had that can of soup at one point in your life. And maybe you liked it. You tasted it. Certainly most kids like it. And you look at it and you say, okay, maybe I could make this at home. And the first thing you'd do is you turn the can around and you'd say, what's in this? And so the first few ingredients you recognize right away. Water, chicken, vegetables, maybe noodles, and you'd say, okay, so there I'm starting to get an idea of how to make this soup. It may also have ingredients in soup that you can't pronounce, and maybe that's why it's better to make it homemade. But you basically get the idea of the recipe by looking at the ingredient list. And that's the same thing that NASA's space program is doing in trying to understand the recipe of the solar system, is we're mapping out the ingredient list of all the objects that we can. Comets, asteroids, the different moons, the different planets, and Jupiter holds this special spot because it was the first planet, so that gives us that first step of that recipe, right? Okay, so there's more to Juno than just that measurement. There's different, I have the science is divided into 4 different categories. The origin, which I already kind of covered, but then the whole interior structure, how does Jupiter spinning underneath? Is it all solid body? Is it moving in concentric cylinders? Nobody really knows. What is the deep atmosphere like? Or how deep is the roots of the great red spot go, or the zones and belts? And then finally, we're over the poles, and so we study the polar magnetosphere, which is the home of the greatest and most energetic aurora in the entire solar system, the northern and southern lights of Jupiter. And here you can see a Hubble image of those.
Awesome!
And so we study all of those things with Juno. I think this button is, whoops, no, I didn't close. No, that's okay. So here's the trajectory. We launched in 2011 from Kennedy Space Center.
Look, Mommy, we took a picture of the moon!
Todd actually was working with me early on in the Juno mission. We went on an Atlas 551. I don't know if you saw his talk. He talked about payload fairings. The top of the rocket is different sizes. We were taking the biggest one, 5 meters. That's what the Atlas 551. First is the 5-meter fairing. The next is 5 solid rocket boosters. And then finally, you have the most powerful
as astronomy.
At that time.
It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician. But everybody may be, and ought to be, in a modest personal way, an astronomer. For stargazing is a great medicine for the soul.
Juno spacecraft, 5 rocket
The thought is from what complex 41, a Bible. The forecast is essentially unchanged from what we've been all week. Just a 30% chance. It takes everything we know to get off this planet. So while everything that NASA does, building the Juno spacecraft and exploring Jupiter, is all high tech, I think a rocket launch represents the extreme of that energy.
The energy in the room on launch day is stressful, but in a good way. It's a good feeling. It's almost electric. Everybody's excited and nervous, and I've seen people before you fighting their names.
A rocket launch is one of the most amazing things to see. It's truly a cosmic event.
Go. Rain, weather, and final clear to launch. Let's go. LC is one. Go ahead. LC, you have permission to launch. Roger.
The launch is probably our single biggest risk in the entire mission.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
When you see it, the first thing that you're impressed with is just the amount of energy. You feel it because the ground is shaking and you're miles away and the waves are coming through the ground like an earthquake would. You're canceling gravity. Gravity's pulling you down. You've got to get to a certain speed, and then that's the escape velocity to leave the Earth.
Execute. Boosters throttling up for on schedule. Engine response looks good.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
You're watching something going from one planet to another.
And we have solids 1, 2, 3, 4, and 5 jettisoned. Visual indication that all solids are separated well. Current altitude is 45.8 miles. In altitude, downrange distance 69 miles. Velocity 5,413 miles per hour. And we have payload frame jettison. And CFR jettison. We have retros and spacecraft separation. This concludes the post-com commentary for the AV-29 Juno mission.
So I show that because I'm really excited about energy. And going to a launch was one of the most exciting things I've ever done because you feel it and you realize it is not easy to leave the planet. So I encourage all of you, you're all into astronomy obviously, so if you can get out to a launch, try to go as close as you possibly can. But be careful because it is rocket science and it's high risk. A few weeks before this, I was, moving around in the middle of the night, looking at the spacecraft and doing things, and there was a big rocket sitting there, and I was like, why am I so close to this? What's going on? And then some guard came up, and I was there with a couple of other of my team, and they said, what are you doing here? And we said, I don't know, we're just driving by. And they said, you have to get out of here. This is launching in a little bit. And we said, how do you go? Where do you go? And they go that way. And they go, well, wait. And he goes, I'm not waiting. I have to get out of here. And he left. And we're like, oh no, where's our car? It's dark. And we, hid behind a tree. And NASA doesn't know any of this happened. But it was exciting. I was closer than I should have been. Okay, so the payload on Juno is the science instruments, and here's a list of them. I won't go through them all. But basically we have gravity science, which is measuring Doppler shifts, so it does radio science and gets the interior of how the mass is distributed. The manpower the microwave sees through the atmosphere and beat. And then we have a series of instruments, energetic particle, auroral distributions of waves. They're all looking at the magnetosphere, the
We can take a
Jupiter.
picture of
and
it,
then we
too.
have a UV camera and a spectrograph and an infrared camera and spectrometer, and then finally JUNO-CAM, which is the visible light camera. And so here you see also an image of sort of what the magnetosphere looks like.
Mommy, we
One
took
of
a
the big
picture of the
things about
moon.
Juno is that Jupiter is very dangerous and has intense radiation belts. So Juno is very much like an armored tank. That's why it weighs so much. There's 200 kilos of titanium making up a vault in the middle of it that the electronics are sitting in to shield them from the radiation. And then the sensors are poking out to the sides with shielded cables to try to make to get the data. So it's never really been, no space shuttle ever designed that way. There's a follow-on mission, not follow-on to Juno, but in the sense that it comes later in Europa, which will go to study, and I'm part of that team as well. But it's sort of taking some of the design ideas that we had on Juno.
There is not another field of human contemplation so wonderfully rich as astronomy.
Okay,
It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, in a modest personal way, an astronomer. For stargazing is a great medicine for the soul.
So the trajectory is we go very close to Jupiter. That's the key thing. And so the whole idea is to dart in and dart out. It's like a dive bomb mentality. Move it about 5, 4, 3, 2, 1, 0. So do that quickly so that we don't get much radiation. And we go really close to the slope that we're in.
Today I want to take you on a journey to the outer reaches of the solar system.
So far, so I'm really nervous, but basically we go really, really close to Jupiter. So we're about 5 minutes when we are close to Jupiter. So, and the idea is to map out the planet. So each time we go by, we do 32 orbits. Each one is a different orbit. We time that. The orbit takes 53 days, but each time we go by one particular one, and the next time we go by one away from that. Forward now. Laid out a track that's, sort of every 90 degrees. And now we're going to start filling in. Try to do it wisely and add all the motion and the air. That means that being a busy with the mission. Of course, now. We'll find out. Of course, one of the close approach part is we're making a map of the gravity and the field and the atmosphere. So it's sort of like I want to make a map of the Earth. I need to get every continent and every part of the ocean. Okay, so some of the data that you see right away, there's sort of a theme that I'm going to go through here, and that is that Jupiter is not like we expected. You saw there's a large payload and a lot of different kinds of science. I would say that every one of them has surprised us in fundamental ways. And so we're very much rewriting the textbooks on how giant planets are. A lot of the things that we had ideas on need to be corrected. This is the first data set. We're looking at the magnetic field. I've had 3 of these, 4 now altogether. This is just the very first pass last August. And what you see here is on the bottom is time. So this is a couple hours. And on the top is the strength of the magnetic field. The blue lines are all models, different models of what we expected to see. The black is the actual data. Magnetic field falls off as the distance squared. So when you see a jump like this, it's very hard to produce in a model. I mean, the model is way off to have this happen. 2 of the things that make this very significant is 1, this is much higher than anybody expected for the strength of the magnetic field. Jupiter is a planet that's on steroids. Everything about it is extreme. here, and the new peak was right when we got the closest approach. That means it's very, very different than we think. What this means is that the magnetic field may be being created closer to the surface than anybody had anticipated. So the Earth has some strange magnetic fields, magnetic anomalies, South Atlantic anomaly and things like that. But people did not think Jupiter had this big of a disturbance. So what it tells you is that because these things can exist very close to the planet, it's very important for us to map all the longitudes to understand how that magnetic field is actually being created. And so the other data sets that I got, 2 of them matched the models, and then the third one didn't. The fourth one didn't. So we have 2 that seemed to be okay and 2 that didn't, and that makes it even worse. Right? Because now the model is, it's even harder to construct. This is a scientist's dream though, so everybody that gets this data is like, oh God, this is great. The theorists are the ones that are disturbed. Okay, so I have another video that I'll play. I'll need your help in starting this one. This one talks a little bit about the core. I think you'll recognize the fellow talking.
We can learn about what's inside an apple by slicing it in half. We can learn a lot about what's inside a planet by slicing it in half. But they're planets, you can't really slice them in half. So how will the Juno spacecraft find out what's inside Jupiter? We don't know what's inside Jupiter. Jupiter could have a core made of heavy metal, sunk to the center.
We can take a
Or it
picture of
might
it
be
too.
that Jupiter has this exotic material that's hydrogen squeezed down to such a high pressure that the hydrogen acts like a metal, metallic hydrogen. Now, we can't cut Jupiter in half. We don't have that capability. Instead, we have a happy little spacecraft in orbit around Jupiter. I'm a happy spacecraft. Now, as it orbits, we strongly believe that there will be slight variations in its path due to tiny variations in the gravity of Jupiter. And that will help us figure out what's inside. Now, how would we measure the tiny variations of the orbit of a spacecraft around a great big planet millions of kilometers from here? Well, we would do it by measuring the frequency of radio waves. Radio waves coming from the spacecraft and radio waves coming from Earth.
There is
We
not
can
another
measure those
field of human
variations
contemplation
like this,
so
using the
wonderfully
Doppler
rich
effect.
as astronomy. It is so easy to
Listen
reach,
to the sound
so responsive to
as
every
the alarm
move,
clock moves
so
towards
stimulating, uplifting, abstracting, and infinitely
Now
consoling.
listen to the sound as the alarm clock
Everybody
moves
may
away.
not be a chemist. Everybody may not be a geologist
As it's moving
or a
towards you,
mathematician.
the sound gets
But everybody
higher.
may be,
As it's
and ought
moving
to
away,
be, in a modest
the sound
personal
gets
way
lower.
this far.
Now this effect, or this
Or stargaze.
phenomenon, was described
It's a great
first
medicine.
by a man named Christian Doppler. And to this day, my brother would like to have a rock and roll group called Christian Doppler and the Effects. But my brother's first name isn't Christian. So, we believe that by precisely measuring the path of Juno as it orbits Jupiter using the Doppler effect, we'll be able to determine from Jupiter's gravity the nature of what's inside. Is it heavy metal? Is it metallic hydrogen? Or is it
Take you on a journey from the outer reaches of the solar system.
with these buttons? Watch some more videos. And this one is...
But, so Bill Nye, I'm sure you all know him, but he did about a dozen videos for us around that. And we're going to do some more and we're getting some updates. And he's great. He's public. Okay, so he already explained a little bit about how the Doppler works. And so the Doppler frequency is used. We have a very advanced system, 2 frequencies. It's the first time we're using like that. It's very much more precise than any other spacecraft that's flown. And we're looking to see how Jupiter.
What a great conference.
And it is two-way. So we get data from the Earth, set up this of the mission. It's just a wedge cut out. You can see the top layer is this helium core region. It's almost all hydrogen. And then you go to this metallic hydrogen region, which is like a conducting fluid, right? We don't have hydrogen like that on our planet, but and we really can't make it in the lab, but under incredible pressure, like 2 megabars of pressure, you can start to squeeze out the electrons from the protons and you get this metallic hydrogen. I believe the magnetic field is created. So one of the questions is how close to the surface is that metallic hydrogen, and how do I make the magnetic field? And to do that, we have to map out the magnetic field. At the very bottom, you see that the pressure is like 40 megabars, and this is the center. So if there is rocky material in the middle of Jupiter, it's not like the rocks in our backyard, right? It's under 40 megabars. For those of you that don't know what a bar is a unit of pressure, and at sea level on the Earth, you feel 1 bar. That's the atmosphere weighing down on you, right? And so 40 megabars is obviously, your ears would hurt a lot. And then the top part of the atmosphere is, where all the convection is going on and what we think is maybe a radiative zone. So this kind of describes that what Juno is about is probing 3 different ways, 3 different depths. The microwave that I'll go into kind of samples the little region on the side there, the upper part of the atmosphere, and then the magnetic field goes into the orange and red regions where the metallic hydrogen, and the gravity field measures all the way down. Okay, so here's some data. I'd love to be able to say I can explain this, but I can't, except to tell you, you see the star over there where all the models are, and then you see where our data is. Okay, so what this is, this chart shows something on the bottom is J4, and on the vertical scale is J6. So what are those J's? So when you can take a mathematical sort of expression, when you want to look at the gravity field or the magnetic field, and you can express it in spherical harmonics. So it's just a big equation of harmonics and the mathematical field. And the J's are the coefficients in front of higher and higher order. So the easiest way to understand that is if I can, nature works this way with vibration, cycles, resonances, and I could take a guitar string and I can pluck it, or a piano string, and it'll vibrate. It's vibrating in different resonances. I could take the same math and describe that vibration as a unit of a bunch of sine waves, right, that are going through the guitar string. And there are certain resonances based on the frets and where you put your finger on and all that kind of stuff. But it's basically, now that's a 2-dimensional thing, so I don't need spherical harmonics, I just have 2-dimensional harmonic math to that. When I go to Jupiter's gravity field or anything in the galaxy or whatever I want to study, I have to go to spherical because it's 3D, right? But basically it's the same idea. So this is telling me how much power is in different harmonics. And that helps me understand. Now, Juno's measurement goes way beyond J6. It'll measure things all the way out to probably J14, which is very high orders. But we can't even make the J4 and J6 work yet. So we've got to struggle here. We can take a picture of it too. But you can see the data. One of the ideas is that maybe there's deep flows going on that we didn't anticipate. So one idea is, what does that mean about a core? Well, instead of the core being compact like on the right and left side here, the core may be distributed. Maybe it's half the size of the planet and partially dissolved into the molecular envelope. We don't know. We've also seen very deep motions, asymmetries that don't seem to make much sense. So it could be that while we thought, because Jupiter was spinning so fast, that everything would be symmetrically distributed, that in fact there may be blobs moving around inside of Jupiter. That most theories did not account for. I'll come back to that because that also may help fit and explain the magnetic field signature that we're seeing. Finally, somebody sent me a picture of a cake they made, which was a pretty good-looking cake, and it looked a lot like Jupiter. I was impressed. They'd cut open a piece. I didn't get to taste it because I only saw pictures of it. But I had to tell them that already I know they're wrong. That if they're going to make the cake again, I don't think they should have the chocolate and vanilla in the middle like that. It should just be mocha. But the idea may continue to evolve, and there may have to be some nuts or something put in. Okay, so the next thing I wanted to talk about is this thing called a microwave experiment. We have an instrument called the microwave radiometer. This is a new kind of instrument. This was basically invented for Juneau. The purpose was to go in and be able to measure the water. So microwaves can work to measure water because water absorbs microwaves. So that's why your microwave oven works at home, right? I stick in a bowl of wet spaghetti or old Chinese food that's got moisture, and turn on the microwave oven and it will heat that food up. If I stick in dry food, it doesn't really heat up, and that's because the microwaves are being absorbed by the water molecule and causing the water molecule to vibrate and start to heat up. So we use that trick in reverse. I look at the microwaves coming out of Jupiter. I don't have to make them because Jupiter's emitting microwaves. It's something called black body radiation. So we all emit in infrared because we're warm. So if I had infrared glasses, and maybe some of you have seen some of these detectors, you'll see the person kind of glowing, right? Something warm. Jupiter's not as warm as we are, and so it glows in the radio rather than which is the microwave. So I know it's glowing, and I'm measuring the microwave, and I can then turn back and say, how much do I see at different frequencies at the same time? So the MWR instrument is 6 different frequencies, and I can pull out how much water must have been in the path. I can also learn and use that to measure the ammonia. So here's another way to look at how that instrument works. Is I look into Jupiter here, and here's ammonia cloud, water cloud. These are just theoretical. I already know this is wrong. And the high frequency only sees right here because there's so much, the high frequencies get absorbed by the water more, and so they don't see very deep, right? I think one down here can't get out of that frequency, it gets absorbed. But as I go longer and longer frequencies, ones that are pretty far down can escape. So we make measurements all over here. And you can't do this from the ground, although we could build microwave antennas on the ground, and we do. We have radio telescopes. But around Jupiter are these relativistic electrons, the radiation.
We can take a picture of it too.
Microwaves. And that's what this is a map of from the VLA, showing it's wobbling because Jupiter's magnetic field is tilted with respect to its rotational axis. And so as it spins around these microwave radiation belts, wobble. So these things are so bright that you can't see into Jupiter to see how much water's in there. And that was the idea, to get a spacecraft between these and Jupiter. You can see why we had to go so close and make the measurement. So when I first thought of that idea, a lot of people thought I was insane. And indeed, then later I realized I was crazy, but then they started to believe it. So we did it. And this gives you a little bit of the resolution. Okay, so we're really close to the planet, so the resolution is a little bit better here. When we're over the poles, we're further away, and so the resolution is basically a beam pattern of an antenna. Here's what it looks like in a little
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, in a modest personal way, an astronomer.
So even though it's small compared to the size of Jupiter, it's very deep.
Is a great medicine for the soul.
Okay, so here's the first data that came down. And I can explain this, but I can't. I can tell you what it is, but I don't know why. So here's the first channel. The first thing you can see is the zones and the belt structure.
3, 2, 0.
Take you on a journey to the outer reaches of the solar system.
Great to be here.
New data, which I just got see if you can explain it away, because that's easier than changing your understanding of atmosphere. But eventually you figure that out, whether it will be real or it won't be. My guess is that we'll discover another way.
I'm a chief engineer, and that means that I'm really busy with the mission here.
This is another way to look at this thing. Here we have latitude on the bottom, right? Most never seen before. I still have pressure. Now the color has to do with how much ammonia. So I taken the temperature that I measured and converted it to ammonia abundance. Right away, this told us something new that we also don't understand, but it's exciting because this giant orange thing sticking out means that there's sort of like a fountain of ammonia coming out of the middle of Jupiter. And that was not expected. And it goes pretty deep. And the other thing that's puzzling is if the ammonia is rising here, it must go back down. And we haven't found out where it's going down yet. It could be that it's coming down over the poles. And maybe that other blob that I mentioned earlier may be part of that explanation. But what we see here is that one, the ammonia abundance is different than we thought, but it's also distributed very differently than anybody had thought. And so something is happening in the equator of Jupiter that is causing all of this. Okay, so here's a little movie, if you can start that, Ori. This is an infrared map of Jupiter. So what's dark is cool, and what orange or yellow is a little warmer. And so you can see which storms are cold. That usually means they're higher up in the atmosphere, and the warm stuff is seen down deeper. This is the South Pole in the infrared. So we had only seen half-lit versions. We went over with the infrared, and we saw that. And everybody went, "What is that?" It's beautiful, but it's pretty amazing. Again, the dark is a little cooler. These are giant cyclones. These cyclones are half the size of the Earth. For some odd reason, they're in the shape of a pentagon, and there's one in the middle, which is the pole of Jupiter. The North Pole was a little different. It seemed to have an octagon. But again, these cyclones are moving up and going toward the planet. Here's a close-up of one of those in the infrared. So these are very massive storms that are quite interesting. Here's a aurora from the UV. Just showing you, the auroral oval where the Isle footprint is, Europa. You can see the footprints from the satellites hitting, and then here it is with respect to the Earth size, and that's to scale. This is the first picture of the South Aurora. This one's in the infrared. The previous one was in the ultraviolet. And here's a whole bunch of maps in the UV in the top four, and then infrared on the bottom. And then this is part of the plasma wave data that as we go over the poles, we look at the radio basically. And so on the bottom is time, the other side is frequency, and you can see different regions as we got close. So you can see electric and magnetic fields. So this is electromagnetic radiation, and I can take that and I can turn it into sound. So that's
Take a closer look
here. Colors are how loud or amplitude the radio emission is. On the side is frequency, kilohertz, and on the bottom is sound.
Awesome!
There is time.
We can take a picture of it too.
Start that movie. It'll play with the sound.
Look, Mommy, we took a picture of the moon!
So that sounds kind of spooky. Sounds of Jupiter. You can find these things on YouTube.
Sounds like Forbidden Planet.
It does sound like it, and of course there's an evil side of me, and this came down in August, and I do a lot of stuff at Halloween, and so we incorporated this into our motion detectors, and my daughter would stand looking out the window and say, "Look, there's another kid running, they dropped their candy bag." She'd run out, she'd say, "I don't have to go out trick-or-treating, I can just stay here and collect the candy." So it was very useful. This I thought you guys would appreciate given your background. So this is a star tracker. The way we navigate spacecraft in space is we look at the stars. We sort of like the old navigation of ships, right? We look at the stars, you figure out where you are. And so there's maps of the stars inside the spacecraft computer, and it takes a picture of the stars, tries to find the ones that it knows are bright and what colors roughly they are. It can make some estimate and try to get an idea of which orientation is the spacecraft properly oriented, or is there some problem. This was taken very close to closest approach to this image on the star tracker, looking out. So the stripe in the middle is actually Jupiter's ring. And we had never seen it from the inside looking out. So I thought that was interesting to show you. The more interesting thing maybe for you guys, and you probably know better than I do about this, although I do know, I did take astronomy and in fact taught it and stuff like that, but you probably know more about it than I do, is these are the stars that were in that field of view. And I think this is Orion's belt. And probably looks the same and different from what you would see in your own telescopes, right? Look at what the sky field is. And so this is a little proof that no matter where you go in the solar system, the cosmos stays the same. So this is the star field if you were living on Jupiter and looking out. And this was my way of making sure I understood what I was looking at. So this is a picture out of Sky and Telescope. And so this is the website for the camera that I had mentioned. And so this was an old version of it, but basically you can do the planning. All these things that say coding are already there. This is all in it. But the discussion and the voting and the processing, again, I want to encourage all of you, because you have valuable data on Jupiter. If you do look at Jupiter and make a picture, sign on our website and post it, please. I'm now going to show you a bunch of images. Maybe I'm not. Let's see, this was a movie. What movie is that? I don't remember that movie. Try it. Let's see.
Look, Dad, there's the moon.
Okay, can you pause it for a second so I give an intro? Okay, this is a really important movie to show you. I'm almost out of time, but I think you'll appreciate this movie. So on the way to arrive at Jupiter,
We can take a picture of it too.
We realized that we could see Jupiter in the field of view of the GeoCam camera for a few weeks on approach. Remember, we're spinning, and we keep the solar rays pointing at the sun, so we don't always choose our orientation.
Look, Mommy, we took a picture of the
coming in from
moon.
the side, right? And so when we're coming in from the side, we're lined up, and inside GeoCam's field of view, far away, was Jupiter. So I said, oh my gosh, we got to make a movie. So we made a movie for about 2.5 weeks, maybe 3 weeks altogether. And we took a picture every 15 minutes. Now, you're looking at a camera very far away, and it has a wide field of view, specifically designed so that when we go over the pole, we can capture a picture of Jupiter's poles. I didn't want to have to make a mosaic over the pole, because that would take too long. So its framing is basically like your smartphone, which is sitting on the spacecraft somehow on its phone. Looking out, you have your smartphone. This is the movie that you make for your vacation. So what we see was Jupiter and the 4 galaxies. The first time that humans have been able to watch the motion of any
not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every mood, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, a modest person of astronomy. Stargazing is a great medicine for the soul.
Find that video on YouTube. There's a couple different versions. That one's 3 minutes. We made some really short ones. I don't recommend them, but they were mainly for news agencies that needed 20 seconds or something. So now I'm pretty much out of time, but I'm going to go a little longer because now I'm going to just show you sort of in rapid fire images that have come down. Most of them, or almost all of them, are processed by the public. What you will notice is that people are expressing themselves. Some are very scientifically figured out, like this one, and they're all pretty spectacular, but some are more art than science, which is okay. You can post anything, we don't restrict it. I mean, we screen it to make sure that somebody's not doing something appropriate. But we let almost any image up there, and so you'll see that Jupiter is quite beautiful.
Not because they are easy, but because they are hard.
And of course you see, sometimes the scan gets skinny because we're going farther and closer to the planet as we go by. This one was, somebody was very clever just a few weeks ago did this. They took pictures that were of course half lit over the pole and stitched together pictures from different flybys. Because each time we flew over the pole, we took a picture and it would be half lit, right? Because the sun's on the side. And they wanted to see what the whole thing looked like in daylight. So they stitched together different ones and I saw for the first time as anybody else what it looked like if it was all lit. It is a strange place. It does not look the same as when you look from the side. I mean, I think if you look at this picture without knowing what it was, you would never guess that that was Jupiter. At least I wouldn't have. And all these are on our website. So these are all public domain. There's nothing embargoed here. I don't have to worry about that stuff. So here's some that people just make beautiful pictures. Here's a movie. This one may not be posted yet, but this was our way of trying to figure out. We just took 2 or 3 pictures together and see if we could understand which direction the cyclone was moving, cyclonic or anti-cyclonic. So you can see these are twisting sets. Cyclones go one direction on the north and the other way on the south. And that's the same thing that happens on Earth and every other planet. Some are, like I said, are just sort of strictly art. Here's one where you can compare the size of the Earth with one of the cyclones, and you can see this is not even the great red spot yet, right? It's almost like a Van Gogh painting or something. In fact, somebody sent me the Starry Night with one of our pictures instead of the sky, and it was amazing. Sometimes you take it, they process it in a way that you almost think you're looking at sand, or something geological, because obviously oil gas. Some are really artistic. And that's okay. They're getting into
awesome!
We can take a picture of it too.
Some they made a blue one. Sometimes they put the spacecraft in it. Or they just do something that's very artistic.
Look, Mommy, we take a picture of the moon.
And I think that would be a cool astronaut thing to do. And some showed us a picture of what it might look like if you were on one of the moons, looking up at Jupiter. Some people ask me if we have any passengers on board. These are the closest thing. They're Lego minifigures that Lego made for me. I collaborated with them, and we put them on to help inspire kids. And we have a tribute to Galileo as well. So we have 3 Lego minifigures. They're having the ride of their life. And there's our website, and the NASA website if you want to go check it out. I think that's the last slide. Yep. So thank you, and I'll take questions.
The other thing, not because they are easy, but because they are hard.
One small step for man, one giant leap for mankind.
So most of those I can't tell you I know the answer to. Nobody knows why it's shrinking. Nobody knows why it's the color it is. So the question was about the great red spot. Why is it spinning in the direction it is? Why is it shrinking? How is it maintained? So we don't really know the answer to that. What I can tell you is that on July 11th, will fly right over the great red spot to the first time. So we will take measurements for the first time and see how deep the roots are, and we'll learn some of those things. But the truth is that we don't understand how that storm can be maintained for so long. What about the problems that we had with the propulsion system? So what he's referring to is that the original plan for Juno was to go into a 14-day orbit. We're in an orbit that takes 53 days right now. And the plan was last October, around launch of the sample, things like that, we would fire the rocket motor and slow down again and shrink how far away we are from Jupiter so that it goes around in 14 days. Juno was in an elliptical orbit. And so what that means is near closest approach, the thing that you saw in the design is 5,000 kilometers or so, a few thousand miles above the cloud tops. The other side of the orbit, the apoapsis, or in the case of this, it's called apogee, is out really far out.
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every move, so stimulating, uplifting, abstracting, and infinitely consoling.
Spacecraft rockets. We have a rocket on
Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, in a modest personal way, an astronomer. For stargazing is a great medicine for the soul.
As we were approaching and get ready to fire the rocket, we opened the valve to pre-pressurize the system, and we noticed that one of the valves, the fuel side, was stuck. It got sticky. It opened, but not where it was going.
5, 4, 3,
That's a good issue. Massive deal for many decades now that valves go up in the system.
Today I want to take you on a journey to the outer reaches of the solar system.
Great to be here.
Fire the rocket, and then the valve sticks again. More oxygen will go into the fuel, and that means you burn it hot. Like you run on cars, whatever you're playing around with, you want to carburetor, do something with the oxygen, right? I played with little cars when I was a kid, so I said, rich mixture, doesn't that mean it's oxygen? Yeah. I said, well, how close are we to the we're at the area.
What a great conference.
Burned a little warm. It wasn't clear what was happening. One of the things that was happening was I
was a chief engineer, and that means that I'm really busy with the mission.
inside the spacecraft. So we said, don't do anything. Let's evaluate. So while we were evaluating ways to burn the rocket safe, we also evaluated the impact of the science. It turns out that science doesn't impact it. You can get all the same science at the 50-day orbit that you could at the 14th. And that's because most of the science is collected really close, and the geometry really close was identical. Basically, the thing that was distant was the thing that was different, and there was of less importance. Then we looked even further and realized that there were actually scientific benefits to leaving it in a long orbit. We were getting measurements that we otherwise wouldn't be able to get because geometries we could sample that we couldn't sample otherwise. To explain to you the real purpose of going to the 14 days was to finish the mission faster. One, my impatience. I wanted the data as fast as I could. I like the idea of every other Wednesday being Science Day, so I wanted to go around Jupiter every other Wednesday. It seemed like a good thing. But you also, back in the days when we were first proposing the mission, the budget for operating in Jupiter was embedded in my total budget. And the faster I went, the more money we had for science analysis rather than operations. But now we were in trouble. We were like, okay, so if we could cause a problem if we fire the rocket, and we've already successfully got the spacecraft, the asset is there, the instruments all work, we can collect all the data, don't push our luck. It does take longer. If we're more patient, we'll get everything plugged in. So I made the recommendation to leave it in the orbit it's in, don't take any more risks, don't change the orbit. The valve was never going to get fixed. But there was really no impact to the science. So NASA agreed with me last February and we decided to leave it alone. So the short answer, without all the explanation where everybody else might not have known, is there's no impact. In fact, the science is a little bit better. But I wanted to explain it all because many of you may have read little pieces of this, and this way you can understand where it came from. Your question was next.
I was wondering, what powers Jupiter? Is it the sun? Is it radioactivity, gravitational collapse, residual thermal? What keeps all that energy going?
What's powering Jupiter? So it's still cooling off from its formation. So that's why it's hot inside, giving all that. Of course, it receives some sunlight too. But it's basically cooling off from its contraction. And so that's where the energy is really coming from. It's really squeezed in the middle, right?
Awesome!
We can take a picture of it too.
So what was the flicker? So there were two reasons for the flicker. The big flicker that you during that movie, right?
Look, Mommy, we took a picture of the moon.
So one, you saw the satellites blink on and off because they were going into the shadow of Jupiter, literally going behind Jupiter, right? You also saw other flickers that I chose not to fix, and that was because some of those satellites at that distance were basically 1 pixel, right? Sub-pixel. Now you guys are all astronomers, so you know what I'm talking about. So when I get something down to like the level of a pixel, it doesn't always come through clear, right? So I could have enhanced that and fixed it, but I chose to just leave it natural so that it wasn't Hollywood produced. So that was the reason you saw the flickering. They were all real, but some of them because of the pixel size.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Okay, so the question was, will Juno's magnetic field data give us some insight into other magnetic fields in the solar system? And the answer is yes. In fact, the magnetic field experiment on Juno is going after very fundamental physics. Not only do we want to understand how Jupiter's magnetic field was created and how it's arranged, but we don't really understand how magnetic fields are generated anywhere, including here on the Earth. There's a theory called the dynamo theory, which is not very well understood and doesn't seem to fit everywhere. And Jupiter and Juno are our chance to really understand that. The reason is that you can't study the dynamo or how Earth's magnetic field is created by looking at the Earth. We've had many satellites that study our field, but the problem is that the Earth's crust is permanently magnetized. And so as you start to map the magnetic field down, you only can map down to the permanently magnetized crust, right? And so beneath, where the molten stuff is happening and flowing and you're getting the magnetic field generated, you can't see what it's like in there. Jupiter is all gas. So the hope was, and I believe this is right, is that we would be able to map the magnetic field all the way down to through and see how it's being created and maybe at what depth. Not only does that help us understand solar system magnetic fields like in Saturn, Uranus, Neptune, Mars used to have one. Venus, Mercury still has one. They all had them at one point, or some still have them. But it also will help us understand how dynamos work outside the solar system, because they're everywhere. It's a very important physical phenomenon. Great question.
What's the current release of Jupiter? How many did you discover? Your Juno discovered.
How many moons?
Yes.
So I don't have a number for that. So we're still analyzing that. We went by, we saw a lot of things that could be moons, but we're trying to verify that they aren't pieces of dust or some little pebble that's close to us that happen to go by versus a moon. And so that's TBD. It'll come out sometime in the future. I don't have that number yet.
Take a closer look.
But I believe that we are seeing a bunch of stuff close, probably associated with the rings, but I don't know how many. And my guess is the number will keep going when we get all that analysis done.
We can take a picture of it too.
I don't know the answer to that myself. That was a star tracker.
Look, Mommy, we took a picture of the moon.
Sort of an engineering exercise. I thought you'd be interested in it, but my guess is that the rings are symmetrical, but they're being illuminated, right? And so when I'm looking at the starlight, his question was, why are the rings asymmetric in that one image? And my guess is that you're seeing an illumination factor that's coming in, whereas the stars are emitting the light, right? Those are reflecting light. But I never asked that question, so I don't really know the answer for sure. What about the water abundance? How much water is in Jupiter? One of the biggest questions I get from scientists. We haven't done all of that yet. That's a very tricky data reduction and calculation
We choose
that
to
has
go
to
to
go
the
into
moon
that.
in this decade and do the other
This
thing.
instrument, as I said, was brand new, and it's produced so much results that the entire team is absorbed in just gorging on what I would call low-hanging fruit. We've never seen it, and it's like, wow, what is that? And so I basically said, let's make sure we understand the ammonia, the temperature, how the instrument's working before we go in and tackle the water abundance, because I don't want to have to correct myself over and over again as I announce the water abundance. So I don't have that number yet. My guess is that we won't have that for at least another 6 months. Very, very a lot of educated scientists that are waiting for that number. And I know if we say something, it's so long. And so we want to make sure that Jupiter, the spacecraft was orbiting like this, if you're the sun, right? So I'm always in the sun, whether I'm close or far. Now, as the orbit, as time goes on, and the original mission was going to be
there
about
is
a
not
year
another
or so,
field of human contemplation so wonderfully rich as astronomy.
Jupiter was going to move.
It is so easy to reach, so responsive to every move, so stimulating, uplifting,
so it would move a little
abstracting,
bit like this,
and
and
infinitely
our orbit
consoling.
would pretty much stay fixed
Everybody
in
may not be a
space.
chemist.
So
Everybody may
now,
not be a geologist
the
or a
orbit,
mathematician,
of Jupiter,
but everybody may be
all the way around
and ought to be
in there for
in a modest personal
years.
way an astronomer.
So there is a place in the orbit,
Or
I forget
stargazing
exactly what date, where we
is a
actually
great
go
medicine
into
for the soul.
go into the shadow of Jupiter. We had a plan for that. When I said, you know, we stay in the 50-degree orbit or not, that came out and was a major showstopper. It would have been mission ending. But of all the engineers and scientists I've worked with at JPL and
Today I want to take you on a journey to the outer reaches of the solar system.
So they solve all that.
Great to be here.
And they figured out a way to change the inclination. So you miss the inclination a little bit, and then the next orbit change the inclination back. Basically jump over. And I was like, wow, you see how that works? And it worked. I mean, it really worked. Now the trick is that they warned us, if you fire that rocket and we go, let's say we want to go to try to change the 14 days and we don't make it. As soon as you shorten the orbit below about 45 days, you can do this trick. And I was like, oh, that's another factor into this decision. Because so anyway, we jump over the answer to your question is we basically never go into the shadow. We're always in sunlight. Now what we have to do is we turn the spacecraft to make sure the solar arrays are clean, and sometimes we turn it a little bit away from the sun, but it's never completely out of the sun. And we can tolerate a couple of hours.
The other day I
Jupiter's red and orange colors aren't exactly certain that they can either be phosphorus compounds, sulfur compounds, or hydrocarbons. They don't really know. So my question is there any best guess from the results that they can also the compounds that
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every mood, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, in a modest personal way, an astronomer.
However, when we go to look at the
Or
depths of the
stargazing
zones and belts,
is a great medicine for the soul.
going on, we may end up with tell us what conditions exist and what don't. And so in that sense, we may be able to shed some light on it. But as far as measuring sulfur dioxide, it might be
5, 4, 3, 2,
we have some idea
0.
of the composition.
Today I want to take you on a journey to the outer reaches of the solar system.
Great to be here. Thank you. Wow, there are a lot of people.
Yeah, so the question was about the 53-day orbits and the fact that the radiation is really defined by radiation. That was something I should have brought, I should have folded in this explanation. So the radiation that we accumulate is pretty much a total orbit. So it's not for
What a great conference.
53-day orbit actually gets a little bit less radiation. And a 14-day orbit. The reason that is that the orbit's a little bit bigger. Most of the radiation direction. But after 32 orbits, we expected to get about the same amount of radiation as we would have done otherwise, maybe a little bit less. So the promise to be able to extend and last longer is there, and it's not negatively affected by the fact that we're in a longer orbit. Did that get the answer you're looking for?
Go beyond that. Do you have indications that the spacecraft will last beyond the 32?
It's early to tell if the spacecraft could last longer than 32 orbits. Right now, it looks like our shielding and armored plating is designed correctly, and we're surviving. We can see when we get hit by very high energy particles, and
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every mood, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, in a modest personal way, an astronomer. For stargazing is a great medicine for the soul.
So we generally try to stay away from this. I don't want to have to crash. Could you fly by one of those? My guess is that we will go over 5, 4, 3, and try to get it.
Take you on a journey to the outer reaches of the solar system.
Great to be here. Thank you. Wow, there are a lot of people.
So we don't want to get So we know there's some moons like Alabama and other ones that are sort of near the rings, and we may be able to get a little bit closer to them. But things that are a kilometer side and smaller, we're generally trying not to go. Of course, we may get one of those without knowing. We don't know at all.
What a great conference.
That would always be helpful, yes. Yes, sir. The question about Shoemaker-Levy 9, when it impacted Jupiter, it made some very visible effects that you could see dark spots. Many of you may have seen that. We don't see any hints that that's still going on. That there are effects left over from that. However, one of the things that we are looking at is to see if we see any effects from a recent hit that maybe we don't know about. And that's where a lot of you come in. If we see something, we'll go look for it. Maybe there'll be something. We saw some dark spots. You'll see them on our thing. One of the NASA people asked me, is that possibly caused by an impact? I mean, I think we don't know the answer to that, but the Shoemaker-Levy 9 made very dark impact spots on Jupiter that were very visible. Of course, that was a really large comet. But almost anything could do that. So we're searching for that connection, and that's certainly some science that would be sort of serendipitous if we were able to do it. But we can only do that with your help. We only get a couple of global shots far away, and from far away, we're not going to get the resolution that you can get from ground base. So it helps to have the map and They do, absolutely. And so the question is, what about the magnetic fields of the moons? Are they interacting with Jupiter's magnetic field? So the way I always think of things is that magnetic bubbles. And so magnetic fields have the property that they exclude other magnetic fields, as opposed to a gravity field, which never gets to them. It just kind of adds up together. The magnetic field excludes the other one. So the sun has a gigantic magnetic field and fills what we call the heliosphere with its fluid. It's solar wind, plasma, charged particles that are coming off the sun's atmosphere and filling it, and in many ways that defines the edge of our solar system. And the Earth and Jupiter and other planets that have magnetic fields have their own magnetic fields. We can take a picture of it too. Or a bubble that are flowing around inside of the sun's giant heliosphere. Okay? And we get our aurora, our northern lights, because of the interaction of the sun's charged particles with the Earth's magnetic field. They creep up the tail on open field lines. Our magnetic field is a dipole, and the solar wind pushes on it, stretches it, and pushes it out of the tail, and the field lines break when they get weak enough. And then particles that are from the sun that are charged can slide up those magnetic field lines and hit our atmosphere and make our aurora, or our northern lights and southern lights. Jupiter is no different. Well, I should say it's very different, but it's got some similarities to that in the sense that it has a giant magnetic field that's also being pushed and stretched out by the sun's impacting wind. And some of its aurora northern lights are made by solar particles that appear. Most of the aurora that you see on Jupiter is made internally by its rotating magnetic field, which is somewhat governed also by its satellites. So we know of one moon, in particular Ganymede, that has its own magnetic field, and it must make a cavity inside of Jupiter's magnetosphere that's called the Ganymede magnetosphere. And it's flowing around and definitely affecting Jupiter's charged particle population as well as the dynamics of the magnetosphere itself. but each of the moons are spitting out particles. So Europa has an ocean. It's believed that that's pouring out water geysers, right, which are filling the magnetosphere with what starts off as neutral water, or oxygen atoms and hydrogen atoms, among other things, and then they quickly get charged up and they start to affect that. Io is the most volcanic body in the solar system. It's spewing out sulfur and other kinds of things that are getting charged up and finding their way into Jupiter's atmosphere. So one of the pictures I showed on the Hubble of Jupiter's aurora, you can see what's called the footprints of Io, Europa, and Ganymede, and Callisto. And these are the satellites affecting Jupiter's magnetosphere directly and atmosphere. What's happening is that the magnetic field line is like a flux tube. It's almost like an umbilical cord connecting Jupiter to the satellite. The satellite is going around at a different speed than the magnetic field, which is spinning an hour. The satellite, as you saw in that movie, some of them are a day and 4 days, and a week. They're moving around slower, but the magnetic field lines connect to them and then connect them to Jupiter. And then the particles that those satellites are losing travel up the field lines and crash into the atmosphere of Jupiter and make their own aurora in the shape of the satellite. And so the Hubble telescope can see these, and other infrared telescopes can track these things and see, and you can see it in the infrared as well, that basically you know where the location of the satellites are. So the early models of the magnetic field of Jupiter use that as constraints to say what was the magnetic field configured like, because they knew this field line that was connected to the planet was here, at the same time it was where the satellite was. So they are definitely connected and interacting with each other.
Look, Dad, there's the moon.
Let's take a closer look.
Awesome!
We can take a picture of it too.
So the reason was how did we end up going solar? So the reason we were solar powered was there was no nuclear fuel available.
Look, Mommy, we took a picture
Really
of the moon.
Okay, at the time that I was putting together the Juno mission proposal, NASA promised that they would build new nuclear power capability for the spacecraft, and to just trust them, it would be ready for launch. And so I went along for a while, and then looked at the schedule and said they were falling behind, and that if I didn't switch to solar, I didn't think it was going to be able to be, it would happen. And so we did a study to see if solar power was possible, and decided it was, and it was roughly the same cost. We had to make the spacecraft more efficient a little bit, because we were power constrained, and we had to make a design so that the solar panels could be facing the sun all the time. That meant I had to worry about orientation and things like that. But other than that inconvenience, there was really no compromise. We didn't give up any science for it. We made our life a little more complicated, but in the end, now, of course, years later, I claim, well, we were green before it was in to be green. But the truth was, there was just no nuclear fuel. The last nuclear power sources were used at the Mars landers. And now they're developing new ones. I'm not sure they would be good for what we were doing with Juno, but we paved the way because other missions now were going to use turbines that are designed for solar power. Maybe that was good. And pushing the efficiency of solar cells.
Standby mode, first pass.
The first pass, you mean when we were going to fire the rocket in October? The question is why did we go into the standby mode? That was human error. And computers are great, but their one flaw is they do what they're told. And so you have to be careful what you tell them. sure that you told them all of those right things. And so we demanded something slightly incorrect, basically making an estimate that was a little bit wrong. And spacecraft sensed that, this condition is not what the humans told me it would be, and shut everything off and said, I better wait. And so it was a safety measure. We have an elaborate piece of software on the spacecraft called fault protection. And what that does is it checks. And if there's a minor thing going wrong, it'll shut off just one little thing. But if it doesn't think that that little thing will help enough, there are different stages. And one of them is shut off all the science instruments and only keep on what you need to stay alive, because live for another day, so to speak. And then the final one is shut off everything except the most essential and face the sun. Don't even try to aim anything. Just face to the sun. The Earth can't be far. And get power. Positive. And
let's take a closer look.
That was it was a human error.
Can't fire a rocket. How do you move in space?
Awesome!
We can take a picture of it too.
There's a big rocket that is used that can be used to change the orbit, and then we have little thrusters all over the place. And so the difference is the rocket ignites, right? It sends out a very large thrust. The thrusters basically just throw the fuel out, right? And move because I've thrown something that way, I move this way, right? So I can steer things. And you can move quite a bit that way. We are designed to be able to change the orbit enough that we can go into Jupiter at the end of the mission for planetary protection on thrusters only. So we didn't need the rocket for that. So basically, the thrusters are able to be used to change the inclination, they can change the orbit. It can change the orbit from 53 days to 14. That's too big of a change. But it can do small changes and it can steer. All the way in the back down.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
One small step for man, one giant leap for mankind.
The question is about the core and the oblateness, and it was kind of a long question on what we're doing all, but it had to do with learning these things. And so Jupiter is oblate, it's fatter in the middle than it is at the poles, and that's because it's a giant ball of gas spinning quite fast, right? So it gets flattened out. The Earth is also that way. We're not perfectly spherical, and so we can use that by the fact that we measure the shape very, very precisely as one of the constraints to define whether we can work on the core and what type. There's a big mass in the middle. The flattening effect will be affected by the fact that it's not all gas. Saturn also has a core. In fact, we know we've been able to measure and constrain Saturn's core. The models from data from Jupiter are not sufficient to it could be zero, or it could be quite large. What Juno data is finding is that there's probably a core, but it's not like we thought. It's not very compact in the middle. It may be distributed and partially dissolved. We don't really know exactly. It could also be that it appears that way because there are deep winds and convection going on, and that there's actually still no core, but there's a lot of motion going on that is affecting its oblateness and the other gravity terms that we're measuring. So my guess is that as we learn about Jupiter, interior and the core, we will apply that to the other planets like Saturn, and they evolve our understanding of those as well, based on what we've learned from Juno.
Look, Dad, there's the moon.
You know, when we go to the intrusive core of Jupiter, as I pointed out, it's like 40 megabars of pressure is what's estimated down in the center. Jupiter's mass is more than 300 times that of the Earth.
We can take a picture of it too.
So we're doing some fundamental science, like I had mentioned about the magnetic field. The gravity field is also doing fundamental physics in the sense that there's something called the equation of state, which is
Look, Mom, we take a picture of the moon.
Properties for the state of matter at very high temperature and high pressure. We don't really understand how a hydrogen atom would behave at great pressures like in the middle of Jupiter. We can't create that here in the lab, or we can't make a little piece of Jupiter, and especially the middle of Jupiter here on the Earth, to test that. So there are theoretical models, and then there are some that go on. Mostly things that are tied to fusion reactions, where we're trying to learn and trigger a fusion reaction and bombard it with lasers. It goes under incredible pressure. So while they're doing that, it's what the fundamental physics of machine around. The lab trying to say, what would that threshold look like? What do you guys do? Thanks. That was a good tip. One question. I should really take somebody that never asked one. There's a guy. Everybody's pointing at the question. Figuring out exactly what those are.
for 2 hours. Well, we've been recording all day. We record 8 hours. That's too far.
Oh, I see.
We can take a picture of it too.
Hey, who's running?
I just formatted them anyway. You think that's it? Yeah.
Thank you.